Oh, Frank Bryan. I'm a co-chair in the Ocean Working Group.
I'm Ian. I'm co-chair of the Ocean Model Working Group.
And I believe Gustavo's here. And we'll see him later. Gunter, would you like to go ahead and introduce Seiler?
Yes. Good morning, everybody. Welcome to this joint session between the Ocean Model Working Group and the Land Ice Working Group. Just before I start introducing speakers, I would just like to remind everybody that this is a courteous space and that please, when you ask questions or when you give feedbacks to a talk, please offer constructive feedback and show appreciation and consider new idea when you do so. So with this, let's get started. Each talk will be about for 15 minutes, and I will give you a 2-minute warning when you've reached 11 minutes so that we can leave time for questions. So it's 30 minutes talk, 2 minutes questions. And we will start with our first speaker, Zaire Sileves, who's at Los Alamos, and who is going to talk about very preliminary analysis of the Marine Ice Sheet Ocean Model Intercomparison Project first phase. Go ahead, Zaire.
Okay, so I discovered just a moment ago that I can't quite go full screen with my slides because the latest version of Ubuntu shows them at half size. So I will have a not quite full view. Can you see that okay? Hearing nothing, I'm going to continue on. So I just want to emphasize very preliminary. I still need to work with all of these wonderful co-authors to get a bit more information about these models before we can really proceed too far with this analysis, but I just wanted to give you a flavor. And there's only so much I can do in 13 minutes anyway, so I guess a bit of very preliminary analysis is quite appropriate for the Land Ice Working Group. So I want to tell you a little bit about MESOMIP, the project, just so you have a feel for what that really is about. So the Marine Ice Sheet Ocean Model Intercomparison Project is a CLIC. It was a target activity. I think they're now separating out the MIPS a little bit, but CLIC is one of the WCRP projects, and it's all about climate and cryosphere for those who don't know it. ISMIP6 is another CLIC MIP, for example. So we're focused on both idealized and realistic MIPS. And there are some basic goals. So especially for the idealized configurations, just model evaluation. For the more realistic ones, in addition, we want to do model verification with observations to the degree that we can. And then one of our ambitions is future projections, and you'll hear more about the realistic MIPS in just a second from Nico. The focus area is sort of maybe the Amundsen and the Weddell sectors, and so even the idealized configurations kind of have that in mind. So Nico will tell you about the realistic stuff. I'm going to focus on these idealized simulations. So we went through a series of these idealized setups. So MISMIP Plus comes out of a tradition of doing ice sheet model intercomparisons, and it's the third phase of that. And so basically kind of an idealized bathymetry was designed for that project. It's got a steep trough, as you can see in the 3D view, or also in this overhead view. It's got a little bit of a polynomial shape to the bed so that you can get kind of maybe a marine ice sheet instability, at least the possibility, but it's also, because of the steep sidewalls, quite buttressed. So that's kind of the idea behind the ice sheet setup. And then we did an ocean setup where we used ice sheet geometry generated from one of the MISMIP Plus simulations to basically design an ocean domain with an ice shelf cavity. And then what I'm presenting today is the coupled experiment. So it's basically putting these two together with ice sheet and ocean coupling. So why are we doing all of this? Well, we wanted to provide a set of relatively simple experiments that make it possible to compare models. So that's kind of the first obvious reason one would do a MIP of this type. But a big part of our motivation was that it's pretty hard to design coupled ice sheet ocean models. So we wanted basically to create a series of steps where you could, add an ice shelf cavity, but not have moving geometry in your ocean model. Then add moving geometry, but not worry about the details of coupling to another component yet. And then finally get to full ice sheet and ocean coupling. And so that's kind of the progression of these MIPs. And then lastly, we wanted sort of a platform where you could do parameter or process studies and kind of say, okay, here's a base setup that people know about, and it's pretty easy to branch off of. And so my collaborator Dan Martin and I have done a ton of different parameter studies based on this setup. So okay, I'm not going to go into MISMIP Plus too much. There's a great paper last year from Steph Cornford you can take a look at. What I'm just going to focus on is that one of the experiments in MISMIP Plus uses a melt parameterization to do some grounding line retreat, and then turns the melt off and allows the grounding line to re-advance. And so we're going to kind of focus on that one because it's the most similar to the MISMIP, the MISOMIP1 set of experiments. And of course, there's no ocean model or basically any sort of way of getting melt, of computing melt in a sophisticated way. So there's just a simple depth-based melt parameterization. And we added a little element of that melt parameterization that melt kind of shuts off near the grounding line. And that's just because that's what the ocean models seem to do. Not that we know that that's physically realistic, it just, we wanted to mimic the ocean model behavior to some degree. Okay, I'm not going to go into the ocean-only experiments too much because there's quite a bit of detail. The gist is, though, that basically we have a prescribed ice sheet geometry on top, ice shelf geometry, and then the cavity. So we're looking at a section through the middle of this domain, and we're looking at the temperature field. And then this is a progression in time. And we have some experiments with fixed geometry, some with variable. And then we also do various things with the far field forcing. So we might start off with a warm cavity and warm far field forcing that spins up really fast. We might start off with a cold cavity and warm forcing, and then that basically spins up to a warmer state. And then we have some experiments where the geometry changes in time, as I mentioned. This is that same type of idea, but for the coupled experiment. So in this case, what we do is we start off with a cold cavity and some sort of steady state ice sheet geometry that's consistent with zero melting or very low melting that you would get in this cold cavity. Then we change the far field forcing so it's warm, and we let basically that warm water propagate into the cavity over time, and presumably melt rates increase dramatically and the ice sheet geometry evolves accordingly and you get some retreat. Then 100 years later, we shut off that far field warm forcing, switch to something cold again, and the melt kind of shuts down and the ice sheet is allowed to re-advance. So pretty similar to the MISMIP Plus experiment that I mentioned before, but with far field ocean forcing rather than direct changes in melt rates. Okay, lots of people participated in this, which is fantastic. It wouldn't have been possible without so many collaborators. So that's just been really exciting to see, and people have put a ton of time into this. You can see that there are 8 different coupled models that have participated, and many of them submitted more than one configuration. For the most part, I'm focusing on only one of the submissions in this particular talk, but there will be some exciting analysis to do of different configurations that people have offered. So I'm just going to give a few details on the ice sheet models and the ocean models that make up these coupled models, because it's kind of relevant to the analysis that I'm going to present. So there was a choice about basal friction. You could either do what's called a Wirtman sliding law, which is basically like a power law, or you could do something that's Coulomb limited. And there's there's kind of debate in the community about which of these is more physically realistic. My sense is that people are turning toward this Coulomb limited version, but we basically allowed people to submit both types, and we'll take a look at what that looks like. Most of the stress approximations in the ice sheet are pretty similar. There's either a bunch with SSAs, the shallow shelf approximation, or some slightly fancier variants on the same, but they're pretty similar. I have some results on that I'm happy to share, but I'm not going to have time to do that in this talk. But the gist is that there's no real difference between the models with those different approximations. Most of the ocean model vertical coordinates are quite similar, z level. We have one terrain following ocean coordinate and one that's a hybrid. So it's terrain following at the ice shelf surface, and then it's z level outside of the ice shelf cavity. And that'll be relevant at one point. And then we have various types of coupling intervals. So that's also kind of interesting in terms of seeing how the coupling behaves with these different ones. Okay, so I mentioned basal friction in the ice sheet is potentially interesting. So in the Mismet Plus experiments, it was seen that this power law, the Wortman basal friction, produced a lot less retreat, and then basically a readvance from this position of less retreat, and then the Coulomb produced significantly more retreat and a somewhat faster readvance, perhaps. It depends on the model. We see something pretty similar here. So basically the 4 models that did the Coulomb friction all have much faster retreat or are similar to the fastest version of the power law. So we see the same kind of behavior. Basically, the coupled system also sees that that the friction law in the ice sheet model really matters a lot, and you can kind of distinguish models based on just that one characteristic. Interestingly, and I haven't looked at this in too much detail, the models that have the Coulomb friction law also have some of the highest melt fluxes. So this is just the sum of all the melt under the ice shelf. So they're not always the highest, but they're amongst the highest. And that could just have to do with the ice sheet geometry, or it could be some sort of feedback between these two. And that'll be interesting to explore in the future. Okay, so the different ice sheet models have, the different ocean models rather, have somewhat different ways of treating the boundary layer under the ice shelf. And I don't have time to go into that in too much detail, but most of the Z-level models do kind of the same thing. They just have a fixed boundary layer thickness. This model ROMS that has a much lower melt rate has quite a different way of treating that boundary layer. And MOM6, this yellow curve, also has a different way that I'm sure Rob Hallberg would be glad to tell you about. He's one of the designers of that method. So what we find in the coupled system is similar to the standalone ocean that I was just showing, that basically the highest melt rates are all for these models with a fixed boundary layer thickness. And so they kind of somewhat at least herd together. And these two models that have a more sophisticated or at least more scale aware boundary layer thickness tend to have lower melt rates. And I want to emphasize that I'm not saying that any of these is sort of the right answer. We definitely need to do more research in our community to have a better sense of how to parameterize the boundary layer thickness, and probably this common fixed thickness is not the right way to do it. Okay, I'm going to just breeze through the coupling intervals because my opinion is that there's not a huge amount of difference between coupling at sub-monthly, a few month timescales, or a year. I will point out, so we see a lot of variability here in this monthly coupling. This is melt rates in the ocean model, so you might expect a lot of variability just because of ocean dynamics. We do see some kind of longer period behaviors. I'm going to guess that that isn't to do with coupling interval because we see it in ones with very short coupling intervals and longer ones. So here is a sort of intermediate coupling, so anywhere between 2.5 and 6 months. Qualitatively similar variability, I would say. And then the one model with the longest coupling time has this longer frequency of variability. And that could have to do with coupling. We'll have to investigate that further. But a parameter study I did suggests that this also could have to do with lower ice sheet model resolution. So we saw this kind of variability when the ice sheet model was a bit too coarse. So that could be interesting. And then lastly, just to leave you with something to take a look at, I wanted to show that you get some pretty interesting ice topography that's a result of feedbacks between melt patterns in the ocean and the basically changes in the ice thickness as a result of those. And many of these patterns, I'm not really able to show it in a PDF, but many of these patterns advect nicely along the surface. And so you can really see the feedbacks taking place. You get, say, really steep features and these even kind of overshoot features as strong melt rates occur. So there's a lot of future work to do, some parameter studies probably to get a handle on some of these differences, some more quantitative comparison between the coupled and standalone. And once I have a bit more of a handle on it, talking to my all of my co-authors who submitted results, I'd like to explore some of the stuff that I was just talking about, where maybe the ice sheet or the ocean resolution really matters a lot for these results. So thank you very much.
Thanks, Tyler. Right in time. So we have a couple of minutes for questions, and please either post your question in the chat or raise your hand.
So I have to figure out if I can see the chat.
I can see the chat.
Sounds good. I think I'm going to stop sharing screen so I can more easily see it.
No questions for Zyder? Robert, go ahead.
Thanks, Tyler. I think that was really fascinating. One of the interesting things that you bring out is that there are differences both in the ocean component and the ice components in all of them. Has anybody scoped out whether there will be any prospects for mixing and matching to see if we could kind of explore some of the hypotheses you laid out about the relative importance of the different physics, the different ice, the different ocean, and so on?
So many of the components are actually the same. I unfortunately stopped sharing my screen, but for example, MIT GCM is used as the ocean model in 3 of those setups. NEMO is used in 2 of them. The Elmer ice sheet model is used in 2 of them. So there's some mixing and matching already happening. What we found in the standalone MIPS, at least on the ocean side, was that 2 different groups configuring the same ocean model to ostensibly do exactly the same experiment end up with different results. And it was very hard to pin down exactly why that was in a lot of cases. So even that can be tricky. There is also a really great coupler called PhysOc that is designed by Rupert Gladstone, and a lot of the models are using that. And because they're using that same coupling infrastructure, it's certainly feasible that you could mix and match basically the components that go into PhysOc. And so I think there is some hope that would maybe not be done as this phase of the MesoMIP1 project, but like as a follow-up. We found on the ocean only side basically that it was easier to have kind of a follow-up study that delved into a certain process or something like that.
Great. I think that's a really nice follow-on. Thank you.
Thanks. In the interest of time, we're going to move to the next speaker. Thank you, Tyler, for a great presentation. Our next speaker is Nicolas Jourdain, who is joining us from France in Grenoble, and he's going to talk to us about the follow-up of the MesoMIP experiment. So the title is Plans for the Second Marine Ice Sheet Ocean Model and Turf Erosion Project. The floor is yours, Nico.
Okay, can you see my screen?
Yes, we can.
Okay, perfect. So thanks for inviting me to your working group. I'm going to speak about the second phase of MesoMIP. So the first phase is not finished yet, but we are already thinking about the second phase. If you have comments and suggestions, it's very welcome, because we are just thinking about the protocol and what to do in this new MIP. And I'm going to start with a bit of motivation. So the thing that there is, we've done some intercomparison of ice sheet projections recently, and we've seen that there is a very huge uncertainty that is related to the ice shelf basalt met parameterizations that are used in the ice sheet models. We've also shown that there are strong feedbacks between the ice shelf geometry and the basalt melt rates, and we also know from now several studies that there are strong feedbacks between the ice shelf and the iceberg melting and the rest of the climate system. So for many people, the ice sheet ocean couple models are viewed as the gold standard for future ice sheet projections. But the thing that, as you've seen in Xyla's presentation, we are only starting to do this kind of coupling, and there is little perspective on the skills of these coupled ocean ice sheet models. So that is a motivation to go further in the MISOMIP intercomparison project. So together with Jan de Ruut, Yoshihiro Nakayama, and Ralph Timmerman, we are preparing a realistic version of MISOMIP 1. So the aim, something that works very well in MISOMIP 1, was the interactions between the ocean and the ice sheet modeling communities. And the first aim of this of the MISOMIP 2 is to keep favoring these interactions between the two communities. Then in terms of the scientific aims, what we want to do is we want to investigate the robustness and biases of realistic ocean ice and ice ocean models in a range of Antarctic environment. So the first step of MISOMIP 2, the step that we are designing now, is to compare an aggregated outputs from a variety of realistic ocean ice and ice ocean models. And we will focus on the Amundsen Sea and the Weddell Sea that are two very specific environments in Antarctica, to a warm, an environment with warm cavities and an environment with cold cavities. And we also want to introduce a comparison to observations, which was not possible in MISOMIP 1 because of the idealized configuration. To minimize the number of new simulations that we ask the different groups to provide, and also because we don't really know what would be an idealized realistic configuration, it will be a come-as-you-are approach. So any model will be welcome to join the model intercomparison as long as ice shelves are included in the ice sheet or ocean simulations. So something that we will do to make this easier is that we will provide a MIP kit. We will provide a kit of observations that are processed for the ocean and the ice sheet components. We will do that for the Amundsen Sea and the Weddell Sea. And for example, what we will provide is a few temperature and salinity values from CTDs that we will plot on maps together with the model outputs as the examples that you see on this figure. And we will do the same for a few vertical sections. So we will do that for only a few years because we don't have so many data, but these few years will enable a comparison to several years with different conditions, more or less cold or warm conditions. So it will be very interesting to see if the different models at different resolution and with different forcings are able to reproduce this interannual variability that we see in the observations. And we'll do the same for the Weddell Sea. So the person who is working the most on it for the Amundsen Sea is Yoshihiro Nakayama, and the person who is working on it for the Weddell Sea is Ralph Timmerman. So for the Weddell Sea, we have data going back to 1995 and until 2018, and we will use again 4 years with again horizontal sections and vertical sections to compare the models to these observations. Okay, then we will have a few planned experiments in a similar way as what was done in MISOMIP 1 and ISOMIP Plus, MISOMIP Plus. We will do experiments for the Amundsen Sea and the Weddell Sea, so there will be regional models and there will be global models. but we will ask people to provide data either or both in the Amundsen Sea and the Weddell Sea. The aim of the first experiment will be to assess the ability of our community to represent the observed interannual variability. What we want to do is, of course, comparing two observations, but we want also to describe the model spreads, the common biases, and see whether there are clusters for the different resolutions, forcing, and model physics. So the time windows is constrained by the observations that we have. So it will be at least 2009 to 2014 for the Amundsen Sea and 1995 to 2018 for the Weddell Sea. But we will also welcome longer simulations as long as they are forced by a reanalysis, because we don't want like ocean atmosphere couple model. We want to keep something that is more or less in phase. The outputs will be on a standard grid. So all the models will have to interpolate themselves their outputs on the common grid. And they will be asked also to interpolate the result directly on the vertical section that we have in the MIP kit. So it will make our job easier to compare everything to the observations. So we will provide common NetCDF format and a list of variables to save that will be quite similar to the standards in the ocean community. Then we plan a second set of experiments in which we want to make a step change of the ice shelf geometry and see how the ocean reacts to that. It has been shown in several studies that there can be strong feedbacks due to ice shelf thinning or grounding line retreats. And we want to see if the different models have the same kind of feedbacks related to the geometry. And the time window will be similar to the one in the previous experiment. It just has to be long enough to let the ocean adjust. And then for the outputs, it will be also very similar. So it will be quite straightforward for most of the models probably to run this experiment if they have already done the first experiment. Then we will go to ice-only experiments. Here, the aim is to assess the ability of our community to represent the observed evolution since the 90s. This is currently quite challenging for the ice sheet models. The trends in the historical periods of ice sheet simulations is usually quite different from the trends that we have observed. And the aim is also to do a kind of model verification through intercomparison, again, to describe the model spreads and see whether there are clusters for different resolutions or boundary conditions. The time windows is from the 90s to 2020. And as it is quite short for an ice sheet model, we will also do longer perturbations, imposing negative or positive melt perturbations to see if the different models behave differently in a realistic environment for similar perturbations. We don't want to overlap with ISMIP 6 or ISMIP 7, so the aim of MISOMIP 2 is again to understand the behavior of the models, to discuss about really what is in the models, and the aim is not directly to provide projections that can be used in the IPCC reports, for instance. Then, of course, there will be coupled ice-ocean experiments, and the aim will be quite basic at the beginning. It will be to assess the ability of our community to represent the observed ice-ocean evolution since the 90s. So the time window is from the 90s to 2020, and there might be an extension to for a few decades under persistent forcing to see the longer time response of the ice sheet, because it's for the first decade, it probably depends a lot on the initial state, more than on the emission scenario. So it could be interesting to see a slightly longer evolution of the ice sheet. So the timeline has changed a bit. There has been a first meeting in September online. We discussed the protocol with a few participants. Then we are already late. So we plan now to write the protocol and to freeze it like later this year, mid-2021. then we can ask a participant to send their simulations. As it's a come as you are approach, we expect that many people already have simulations to send. So we probably don't need a very long phase to let the people set up a common design and a common configuration and so on, as it was the case in Mesomip 1. And that's it for the moment. I hope to be able to speak to you again in 2 years and to show the results as Xyla just did for Mesomip 1. So if you have any suggestions, it's very much welcome.
Thanks, Nico. You put us right back on time. So are there any questions for Nico?
I have a question for Nico. At the Splinter meeting, there was some discussion of global models as well as regional models. Could you say something about the possible role of global models in these experiments?
Yes, so the global models are welcome to participate. They will just have to interpolate their outputs onto the command grid, which will be quite high resolution, but it doesn't matter. You can just interpolate your coarse global ocean model onto the command grid. I think it would be very interesting to have a full hierarchy of models, even like the intermediate complexity, low resolution ocean models that are used to drive ice sheet models. It would be very interesting to see how these different models are able to reproduce the interannual variability and the evolution over the last decades, I think.
Okay, thanks a lot. Is there another question for Nico?
So I'll put on my video. I have more of a suggestion, kind of something that had come up at a previous discussion that I just wanted to kind of bring up again, which is that one of the things that made Mesomip 1 pretty tricky is that I didn't come up with visualization tools until well after people submitted their results. And I think what I learned from that is it would be really helpful to have those visualization tools as early as possible so people can find their own mistakes rather than the coordinators having to find the mistakes.
Yeah.
In the chat, someone is Dan Goldberg is agreeing with this statement.
Yes, we will do that. I think it's important, and it's also important because we are providing MIP kits. So we are providing a set of observations in a format, and the models will be in the same format, and we will provide, I guess, Python tools to plot the observations on the command grid together with your model outputs. And then it will be easy for everybody to compare their simulation with observations. And then after, of course, we should provide tools to plot all the simulations together, I guess. So yes, we will do that. Thank you.
Thanks. Let's move on to our next speaker. Our next speaker is Soteria Georgiou, who is from the University of Delft. And she's going to talk about the impact of increased atmospheric CO2 on the 3D structure of the AMOC in the North Atlantic Ocean. So Soteria, the floor is yours.
Thank you very much. I hope you can see my screen.
Yes.
Yes, that's great. So, hi everyone. My name is Soteria Georgiou, and recently started working at Miren's Vizcaino group at Delft University of Technology. And this presentation is about the impacts of increased CO2 on the 3D structure of the AMOC. So the focus will be on the North Atlantic Ocean. Yes. So I will start with a quite familiar figure that shows the AMOC in a depth latitude perspective. It is known that as the surface northward flowing waters going towards the north, they are getting denser due to atmospheric cooling. They get dense enough to sink, and they return as a southward return flow in the deeper layers. It is known that the water mass transformation takes place in the North Atlantic Ocean is described by the process of deep convection. However, during deep convection, the downwelling that happens within plumes, it is balanced by upwelling between them. Therefore, there is no net downwelling in the convection areas, so in the interior of the ocean. Instead, the theory predicts that significant downwelling can take place close to the topographic boundaries. And the study of Spoll and Pickard in 2001, they derived this expression here. I hope you can see my pointer also, and which relates the amount of near boundary sinking to alongshore density changes. So this scaling relation that I've shown you before is mainly introduced in conceptual idealized models. A recent study have shown, tried to investigate the validation of this scaling relation in two simulations performed with a global ocean model. The main difference of the two simulations is the horizontal resolution. And in the upper panel, you see the vertical velocity at 1,000 meters depth in the higher resolution model, as you can imagine. And in line with theory, they show that strong vertical velocities take place near the continental boundaries. And they also show that the scaling relation in this higher resolution model is valid, except apart from some areas in the North Atlantic Ocean. The analysis of the coarser resolution simulation, it showed that enhanced vertical velocities are found also in the interior of the ocean, where theory does not predict that, and that the scaling relation of Spoll and Pickard does not hold in this coarser resolution model. So the results that I will show you are motivated from this study, and I mainly want to identify the locations where we have strong vertical velocities in a climate model, that we know that is the resolution is quite coarse. So the simulations analyzed here are performed with the CESM 2, which includes an interactive Greenland ice sheet component. The ocean component is POP version 2. It has 1 degree of nominal horizontal resolution. And I'm analyzing two simulations, one which is described as the control run and is the pre-industrial run, and an idealized scenario at which the CO2 is increased by 1% every year until it reaches the 4 times level from the pre-industrial run, and after that is kept constant. So here we see the AMOC in depth latitude view and averaged over the last 10 years of the pre-industrial simulation. And what we can see here is that in the North Atlantic Ocean, there is of about 10 vertraps downwelling. And it is found that the AMOC peaks at a depth of 928 meters. So if here we see the vertical velocity at the depth at which the AMOC is found to be maximum, so at 928 meters. And we see that in line with theory, the near boundary, we have near boundary strong vertical velocities. Strong signals are found at the overflow regions along the coast of Greenland and at the Labrador coast. We see a lot of upwards and downwards motions. However, if we integrate the vertical velocity at this level over the whole domain, we get tens vertraps of net downwelling. So in line with what we saw in the OMWG view. So here we can see the response of the vertical velocity at this depth at the 1% simulation. And these are averaged over 25 years. And we see that in the beginning, it shows a similar pattern with the pre-industrial run and what we expect from the theory. So, and as the time passes, we see that the magnitude of the vertical velocities are strongly getting weaker and weaker. And by the end of the simulation, we have some small signals at the regions of, at the overflow regions. And yeah, so in order to analyze the along boundary downwelling, I define the path that follows the 928 meters isobath. This path starts from near the Scotland and it goes all the way to the Labrador coast and about around 47 degrees north. The red dot shows 20 segments of 20 points. And these lines here show the cumulative vertical transport along this path. So we start, this is averaged over 10 years for the 1% run, and the black line is the average over the last 10 years of the pre-industrial simulation. What we see here is that the first years of the 1% simulation and also the pre-industrial run, we have a net cumulative vertical transport of around 14 vertraps. We see that we have a strong vertical downwelling at the overflow regions here in the Iceland Faroe overflows and the Denmark state. And the strongest change happens between the Denmark and Cape Faroe. After 70 to 80 years, the magnitude of the cumulative vertical transport along this path goes to half of the values that we had in the pre-industrial run. And by the end of the simulation, the cumulative vertical transport along this path is almost negligible. So we have strong changes in the North Atlantic Ocean. So according to the simple scaling relation that I shortly described in the beginning, the alongshore density changes seem to be a key parameter to define the magnitude of the along boundary downwelling. So this panel the upper panel show the density profile along this path, and the lower panel show the density anomaly at each location with respect to the starting point of the path. So what we see here for the first 25 years of the 1% run is that we have a signal at the surface of buoyant waters that entering the Labrador Sea from the Davis Strait. And by looking at the whole water column, we see a densification of the waters along this path. And if we, so it seems that the scaling relation works also in this climate model, so that the densification of along this path gives us a strong net downwelling.
2 minutes.
Yes, thank you. I will be in the fast forward. So as the time, as the CO2 increases and a lot of things happens in the ocean, the North Atlantic, it's getting fresher and fresher. And by the end of the simulation, now we don't see a strong signal of densification of the waters along this pathway. This is the last figure. I want to close this presentation with the response of the AMOC to increasing CO2. Is quite well known in many studies that the AMOC will get much weaker by the end of such future scenarios. And to summarize, we saw that in the pre-industrial realm, the near boundary downwelling is well represented in this climate model simulation. I will focus that then there is a negligible net downward transport in the North Atlantic after 70 years of increasing the CO2 levels. And what I'm working now is to see whether the scaling relation is valid in this climate model simulation, and also to investigate the role of the freshwater fluxes on the downwelling dynamics. Especially, I want to compare to see the differences with a simulation without an interactive Greenland ice sheet component, in particular to see whether the timescales or the magnitude of the downwelling differs a lot from the simulation. Thank you.
Perfect timing. Thank you.
Yes.
Are there any questions for Satya?
Gunter, I have a quick question.
Yeah, go ahead.
This is Frank Bryan. The model, the POP model has a overflow parameterization, which involves a mass transport that's not visible in the Eulerian velocity field. Did you account for that vertical mass transport in these integrals?
No, I only check the vertical velocity at the moment, but that's a good comment.
Mm-hmm.
Yeah, and I want to mention that this is not related with dipycnal mixing or water mass transformation. It's only the W analyzed.
Thank you.
Thank you. Any more questions for Satya? If not, in that case, thank you so much, Satya, for your presentation. And we are moving on to our next speaker. Dan Goldberg is giving the next talk and from the University of Edinburgh. And he's going to talk about the effect of ice shelf melt on the biological productivity of Antarctic coastal polynyas. Dan, the floor is.
Yeah, thanks, Gunter. Hope everyone can hear me. And I just want to say, thanks for letting me talk here. This isn't a sort of subject that maybe is generally talked about in these meetings, and it's certainly not a subject that I generally speak about. A bit new to biogeochemistry, biogeochemical oceanography myself. But Bill Lipscomb asked me if I would, if I wanted to submit a talk to this, and I thought it would be nice to talk about a paper that my PhD student Entry 12s recently read, which I thought was quite interesting. Looking at the sort of list of attendees, I got quite nervous because I know next to nothing about biogeochemistry, biogeochemical oceanography, but the talk that I'm going to give is kind of light on that anyway. So broadly speaking, this is regard in terms of productivity, biological productivity, this sort of plot of fixing of carbon by phytoplankton around the world kind of suggests that photosynthesis, biological production is kind of low in the Southern Ocean, despite the fact that the nutrient levels there, this is nitrate, are very, very high. And it's thought that this is due in part to the limiting of iron, dissolved iron, which is needed as a catalyst. I think that's kind of my word. I understand that iron is not sort of like taken into the organism, but sort of just used in photosynthesis, and then sort of it just is given up and then sinks. But it's due in part to the limiting of that. Upwelling in the Southern Ocean does bring a lot of nutrients to the surface, but there's very little dust deposition just because of remoteness and not a lot of sort of land for exposed land for winds to blow over. So there is iron limitation. So there's low productivity, but there are a number of polynyas, basically holes in the sea ice around the coast of Antarctica that are some of the most productive regions in the Southern Ocean. Among those are the Amundsen and the shown here, and the Pine Island polynyas, for which productivity rates are an order of magnitude above that of the rest of the Southern Ocean. And it's in part because there's limited ice cover is sort of removed in a polynya, exposing light, something that's needed for photosynthesis. But it's also due to a source of micronutrients, that is iron. This is just showing the immense amount of chlorophyll that's seen in front of the Dotson ice shelf in the Amundsen polynya in a given year. So ice shelf melt has been implicated as an important source of iron in the upper ocean in these polynyas, an important source of this productivity. And it's thought that there's two potential pathways by which iron kind of gets to the surface. One is that very likely, and for under most ice shelves, there's entrained sediment, which is just sort of picked up by the ice sheet sort of flowing over land. And that sediment might be iron rich. So melting of that sediment out of the underside of the ice shelf exposes dissolved iron, which is then carried to the surface. And there's just more higher iron concentrations in the circumpolar deep water, which is exposed to a lot of ice shelves around the coast of Antarctica. And when that causes melting, that adds buoyancy to the circumpolar deep water, which sort of comes up to the surface. And that's another way that iron is thought to arrive at the surface. This observational study by Goringa in 2012 just did a kind of a lot of measurements of iron around the Pine Island polynya and looked at all the possible sources of iron that could be bringing iron to the polynya. And they kind of rejected all possible sources except as being not big enough to fuel the biological productivity aside from the melt of Pine Island ice shelf. So it sort of brings up these questions, and the aims of this research are to, for one thing, determine the degree to which ice shelf melt plays a role in polynya production. Two, and this is red because it is a research aim, but I realize that I don't have time to talk about it, to investigate the competing effects between iron and light limitation. And three, to investigate the response to differing levels of basically climate, differing levels of radiance and differing levels of ocean temperature, and see what that does to productivity. And the framework in which my student decided to study this was an idealized one, simply because I kind of steered him in this direction, but it was because it was the first time using MITG's first time using an ocean model, and a small idealized domain is a lot easier to use than a large realistic one that can result in week-long runs that can then crash. So the domain is sort of it's an abstraction of kind of the Amundsen Sea, it's just sort of in a box. We can kind of see it over here on the southern edge. There's a single ice shelf which flows into a trough, not unlike the trough that Dotson kind of ice shelf kind of flows into. There's an ice tongue to allow polynya, and there's periodic boundaries on the east and west, just to kind of mimic the idea that nutrients coming out of Pine Island ice shelf, Pine Island ice shelf might sort of be flowing into Dotson ice shelf and circulating there, or at least the region around it. At the northern edge, Andrew imposed boundary conditions, which are quite simple on ocean temperature and salinity, kind of these profiles here, and irradiance at the surface with a sort of seasonal cycle, getting bright in the summer, cold and dark in the winter. And the sort of these bounds here are just to emphasize there were experiments that varied these things. And when I talk about the CDW layer rising and falling in the forcings, I just mean this sort of height, this height of the thermocline. So Andrew coupled MIT GCM in this domain to Bling, biogeochemistry with light, iron, nutrient, and gas, sort of, which has been implemented within the MIT GCM model as a package. Dynamic and thermodynamic sea ice component is used, as well as thermodynamic interactions between the ice shelf and the ocean. And yeah, that's pretty much it, just to say that the idealized domain allows a large number of experiments. So I'll just show a few results. The sort of first main one was just testing, what happens if melt is taken away, or melt as a source of iron is just taken away from this ice shelf system. And so these time series here show sort of total productivity, those are the green, and total iron in the upper ocean, those are the orange. And you can see that without any melt at all, there basically is no productivity because there's no iron in the upper ocean. And these two different sources of iron that I talked about were tested. The melt pump refers to iron contained in CDW only. GMW iron experiment refers to CDW iron plus iron coming out of contained in this sort of ice shelf and sort of being melted out of that. And it's interesting that adding glacial meltwater, GMW, increases the level of iron by about 50%, but only increases the level of productivity by about 20%, sort of emphasizing that there's these diminishing returns. When things become less limited, they have a smaller impact. Yeah, so that's about that for the sort of baseline exercise. So that is to say, melting is important for productivity. The next set of experiments that I'll just mention are the kind of the variation of climate forcings or external forcings. Rather than show, this is really 9 experiments here being shown here, not 3, but in order to sort of like save on space, the way Andrew sort of structured this was, each plot, each profile here corresponds to an irradiance, and then within that there's 3 different profiles of melt rate corresponding to different temperature forcings, different levels of CDW. So this wasn't really too interesting, just to say that, the sort of bulk melt rate is roughly linear or symmetric in the ocean thermocline depth change. Raising the thermocline increases melt by about the same amount that lowering the thermocline decreases melt. And there's quite a small impact of irradiance on melt rate. The only real impact is sort of in the upper parts of the ice shelf. That's because in the summer, warmed water from sort of the sunshine is able to sort of get down under the ice shelf. Sorry, I'll try to hurry up. But this is the response in productivity to those experiments, or basically to these melt rates. And this I thought was a little bit more interesting. So this is the sort of baseline melt that I showed before. The 3 sort of curves in each one of these images just correspond to different levels of irradiance. So that didn't have a really large effect. It's been thought that irradiance is, different variance in irradiance is thought to be sort of the leading factor in controlling productivity in these polynya, but that wasn't shown in this experiment. Rather, the increase, the increase in ocean temperature, or the raising of the thermocline, did lead to quite a large increase in productivity, which wasn't a surprise because it raised the levels of iron as well. The decrease in the lowering of the thermocline led to a decrease in melt, a decrease in the amount of iron, but also a massive increase in the amount of productivity. And a very qualitative difference as well, because this first peak, we see this two-peak structure in these two experiments. There's only a single peak here, only the later peak shows up. And yeah, and I think that, well, what we are pretty sure about is that this is largely determined by a strong jet that sits in front of the ice shelf, which is as a result of fresh water just being poured out, coming out of the ice shelf. Where ocean temperature is highest, there's a very strong boundary current, shown in this figure over here. And in this case, productivity is sort of like close to the coast. Well, the highest productivity is. As CDW drops in level, the circulation becomes more gyre-like because that's what the winds are telling it to do. When CDW is lowest, the sort of boundary current is not very strong, allowing quite a strong gyre, allowing this sort of meltwater containing iron to spread to the center of the polynya, where it's sort of most needed for productivity. So the productivity peak is now sort of far away from the boundary as a result of the jet not being as strong. And that's why the productivity is actually higher than in this experiment. So these effects are seen in realistic models as well. The one that I knew of, that I do know of, is an experiment by Toshi Kimura in 2017, modeling the Amundsen, and this is just a profile of temperatures in front of Pine Island. In high melting years, the outflow from Pine Island stays very close to the ice shelf. In low melting years, it is able to spread sort of into the center of Pine Island Bay and the Amundsen. And so a similar thing might be going on in these simplified experiments. So the conclusions are just the ice shelf melt is shown to be crucial in the upwelling of iron in the coastal polynya. Feedbacks of melt on ocean circulation can influence the spreading of nutrients and productivity. And one thing that we was not included in this study was the interannual variability of winds, which may be important for controlling the size of the polynya, which is actually a pretty strong determinant of productivity, as remote sensing observations have shown. So for that reason, the next stage is to sort of like investigate these same processes in the context of a realistic model of the Amundsen. So we've got sort of a realistic physical model of the Amundsen provided by Paul Holland within MIT GCM. And these are just some preliminary results showing the impact of biology on CO2 fluxes into the sea, well, at the surface of the ocean. So that's all. I don't have a closing slide, but thank you very much.
Thanks, Dan. Do we have time for one question? Anybody have one?
Hey, Gunter, I was just wondering if you might like to look at the chat and repeat Keith Lindsay's reply to my question.
Yes, thanks. So the question from Bjorn was, for CSM BGC expert, is there any mechanism in CSM that would mimic an iron source for nearby ice shelf melting? And the response from Keith Lindsay to this is, not at present. Ocean BGC and CSM has a riverine iron flux that is read from a fixed file. One could imagine adding a new land ice to ocean iron flux to represent this process.
I don't know if that's directed to me, but I can't really speak to it. But it seems that seems like, all I can say is that it seems quite important for representing these processes around Antarctica.
Yeah, I don't think this was necessarily directed to you
okay.
Specifically. Okay, thank you so much, Dan, for your presentation. Let's move on to our next speaker, Don Martin from Lawrence Berkeley National Lab, and he's going to talk about the impact of improved bedrock geometry and Antarctic vulnerability to regional ice shelf collapse. Dan, the floor is yours.
Hi. So we're going from Dan to Dan.
Yes.
Well done. That'll keep things easy. There we go. So this is sort of a work in progress. I'm gonna talk about some work we've been doing trying to figure out the impact of improving the bedrock geometry on how we can conceive of how we understand Antarctic vulnerabilities to regional ice shelf collapse. This is joint work with Steph Cornford. The basic idea is back in 2019, we had a paper in GRL. Basically, the idea was to try to understand where the Antarctic ice sheet is vulnerable to forcing from warm water incursions under ice shelves by dividing Antarctica in sectors. We have 14 sectors here, and then clobbering the ice shelves with this really extreme melt in each sector in turn. And then we ran for 1,000 years and then compared with the control to figure out where the vulnerabilities lie. And what we found was basically, it didn't really surprise anyone. There were 4 sectors that had really extreme vulnerability, like multi-meter vulnerability. The Ronnie Ice Shelf, the Edmonton Sea, the East, and the Ross. And basically, what these all had in common was they all had a pathway to this sort of vulnerable area in West Antarctica between the 2 big ice shelves. And basically, that's what happened. For each of these cases, what happened is you got in there and you basically just clobbered this sort of very vulnerable area. Then there were some regions with intermediate vulnerability of between half meter to a meter of sea level equivalent, and those were basically sectors 6 and 7, and then also maybe down here in Outsland. And then the rest of the regions basically didn't really do much. They were they had very small contributions. And so, but that was we did that experiment using BedMap2, which was data from like 2012. And since then, there's been a sustained campaign of observation. And then the quality of the data sets has improved tremendously through use of things like the mass conserving bed techniques pioneered by people like Matthew Mulligan and Steph Cornford and Dan Goldberg. And so there's a potential for greatly improving the quality of projections of the Antarctic response to climate forcing by using these newly improved data sets. But the question is, it'd be good to get a handle on how much we're improving things. The other thing to realize is that to leading order, the marine ice sheet instability is almost completely dependent on bedrock geometry, right? It depends on whether you can find a place where you can trigger this instability and where you can create these pathways to vulnerable regions. And along the same lines, Scott Weibel and his collaborators demonstrated that the magnitude and rate of grounding line retreat can be really dependent on the details of bedrock topography. So then let's see what we can do. We can try to evaluate the impact of these improved data sets by rewriting the same experiment and comparing the answers, what we get. So this is sort of comparing the two sets of calculations. The first ones we use BedMap2 geometry. We'll do the same thing again using the BedMap machine geometry circa 2019. We used a temperature field from Frank Patton in the old ones. We actually got a temperature field from Matthew, which matched his data set. And then we'll initialize the basal friction in the previous run to match the Rignan velocities, and then we'll initialize the basal friction to match the current best estimate of velocities in the measures velocity field. We use the same surface mass balance field because it really doesn't make that much of a difference. And then because we're going to use bicycles, which is an AMR model, we'll start with an 8-kilometer base mesh, and then adapt and refine to 1 kilometer fence resolution where we need to, so we can follow the retreat of grounding lines, for example, as they evolve. Well, we're going to do things a little bit differently because one of the things we found was that we had this weird sectors 4 and 14 in the original map. The left map is the original sector map, and the right one is the one we're using now. It turned out that this Western Ross was really it was super vulnerable if you could get because it kind of it touched a little bit of the Sable Coast, which gave us a pathway to this sort of vulnerable region between sectors 4 and 5. So rather than try to make that work, I just basically said the Ross catchment made it a gigantic sector 4. It made things a lot simpler in trying to set things up, and I don't think it changed really the results much. So for each sector, once again, we'll subject the model to extreme local melting of all floating ice in the sector and evolve for as long as we can. In this case, we're still getting started, so only 50 years. Then we also ran the control with no melting, and then sectors where we just clobber all the ice shelves in every sector, just for comparison. And then we'll subtract the control to compute the effect of regional ice shelf collapse. So if you look at volume of rotation, the leading or the broad behavior, this is a figure showing the change in volume of flotation over 50 years for the new runs, which are the purple runs with bed machine, and then the previous examples, which were bed map 2. And they're to leading order, they're pretty similar, which is actually pretty reassuring that we didn't get, things haven't changed that much, right? The bed map 2 wasn't super horrible in some place that caused massive things to be different. If you looked at what happened overall, though, we see reduced contribution of sea level rise of about 5.5%, which is, it's something. When you're sitting in a house by the beach, that probably makes some difference. Gives you a couple more years. There were some notable differences. Some sectors had notably more than BEDMAP 2, particularly sectors 5 and 6, which are these Ronnie Filchner facing sectors. And then some sectors had presumably a fair bit less. Sector 2 is the Amundsen Sea, which I'll go back to in a second. Sector 4, the Ross, and then Sector 7, which is this recovery region here. And then if you look at the grounded area, we see something very similar, but actually same patterns, but basically we see much bigger differences in the grounded area differences than we did on the change in volume of rotation at 50 years. So particular sectors 4, which is the Ross, showed a lot more grounding line retreat in bed machine than it did for BEDMAP 2. And the same is also true for sector 6, which is this sort of Filchner trough region. And then sector 13, which is the road slam, was much more vulnerable in BEDMAP 2 and much less vulnerable for bed machine. Let's see. So if you look at all the sectors, like I said, this is showing the rate of change, the change in volume of rotation for purple is bed machine, and green is BEDMAP 2. So you can see it's a fairly smooth difference, but it sort of continues. It smoothly grows, and the difference continues to grow as you go. And then this is this also shows the impact, the difference, the ice thickness change after 50 years for the bed machine case. So it's what you expect, basically. Everything, it retreats pretty much everywhere, but more around places that we know are vulnerable. So looking at sector 1, which is the Antarctic Peninsula, we actually see a pretty big reduction. We see a 34% reduction in vulnerability. It goes from BEDMAP 2, we saw 16 millimeters after 50 years, and bed machine we see 10. I think that the Antarctic Peninsula is one place where the geometry got a lot better because it was kind of a mess in BEDMAP 2. So this is kind of nice to see. And this plot on the right, once again, the green line is basically the control. The purple line is just a sector 1 run. The yellow line is BEDMAP 2, and then the blue line is when we turn on all the sectors. So you can see if you go from yellow to purple, it's actually a fairly big difference. I'll just go through all the sectors in turn. The Amundsen Sea, it's a little more busy here. The control here is yellow. All sectors is green. We saw a 20% reduction in vulnerability here, and a fair bit less retreat. It seems like things are basically going a lot slower in the Amundsen Sea, which is nice to see because that's one of the more vulnerable regions. Then looking at sector 3, that's the Getz region, 22% reduction in vulnerability after 50 years in sea level rise. Sector 4, the Ross Ice Shelf saw a 17% reduction in sea level rise after 50 years by using the better geometry. Sector 5, actually the Ronnie Ice Shelf saw was pretty much the same. It saw like I think that's actually a 10% increase, not a 1% increase. But yeah. And you can see that the Ronnie is basically, it's the big impact here is the rut for ice stream. Actually, let me make mode here. Hang on. Presentation. There we go. That's better. Sector 6, the filter ice shelf saw a 20% increase in vulnerability, mostly because it got down this region down here, as it's these sort of regions where it was not well constrained in BEMAP 2. Sector 7, the recovery region, was also saw a 10% increase in vulnerability. So because this region also was not very well constrained in BEMAP 2. Sector 8, not much happens, and not much happens in either one. Sector 9, same sort of thing, is actually a 17% reduction in vulnerability and in sea level rise concentration, but it's basically still pretty small. The Amory was slightly more vulnerable, about 10% more vulnerable. Shackleton was actually a big change, but basically a big change from not much. So, it doesn't really commit to it wasn't very, very vulnerable. The first one, it's still not very vulnerable. It's just even less vulnerable. The Aurora Basin, this was always a surprise to us. It's less vulnerable. It's about 13% reduction. And we were actually surprised that this wasn't more vulnerable in BEMAP 2. So this is a region which you get a lot of, where you don't, where there's a lot going on, but maybe it doesn't mean much in the long run. And the last one, Oatsland down here, saw 16% reduction in vulnerability. So, like I said, overall, yep. So overall, the improved data set that we have now from in the form of bed machine, we generally see slower rates of grounding line retreat and lower contribution to sea level rise when you sort of apply these massive forcings to them. We suspect that's due to basically you have more detail in the bed. It's a much rougher bed, and that's similar to what Scott Waddell saw as well. Is that when you add a lot of detail, the grounding line tends to hang up on these features more, and so you tend to slow the retreat down. There's no big question of whether bed machine requires finer resolution to get it right. Because some of what we're seeing now looks a lot like what we saw when we were slightly under-resolved before. So in 2016, we did this convergence study where we demonstrated that you need 1 kilometer resolution or better for this experiment for BEMAP 2. But BEMAP 2 is especially a 1 kilometer data set. So maybe we were seeing an imprint of the actual data set resolution there. And then, so we're exploring that now by trying to do a 500 meter, 1 kilometer and 2 kilometer projection to see what the convergence slice looks like that's taking a little time because 500 meter resolution runs take a while. So the next steps are, the first thing we do is we go back and we're still trying to get a good initial state. If you may have noticed, our current control case actually gains a fair bit of ice. Establish resolution requirements for bed machine Antarctica, run for a longer duration, and then start to try to understand what the sources of the differences are, if there are features in the bed that are leading to these differences. And this work was supported by the Department of Energy, and we used the nurse computers to do these runs. And that's it. Thanks.
Thank you, Dan. We have already some few questions for you. Heiko, I see your hand is raised. Go ahead.
Yeah, hi, Dan. Thanks for this talk. It's really interesting stuff. I was wondering, you not only changed the bedrock, but also velocity that you're inverting to, and the temperature, I think.
Yes.
Is there potential to make an experiment where you clearly separate the different factors? Because now you will say, okay, this is like bedrock versus bed machine, but then how do you exclude that the other factors play in there?
Well, there are two answers to that. One of which is just what are the impacts of just having better observations, right? In which case all these things come into that play. But the other thing is, I think we're going to run it for much longer times, in which case the impacts of the initial velocity field fall out. I mean, because if you run for 1,000 years, what you're really looking at is bedrock. And the other things don't really matter as much. But it's an interesting thing. And we could try to use the original temperature field, but I think you have to use a consistent data set or else it doesn't make much sense.
Yeah, okay, that makes sense. But maybe then you should call it something else, like a new data set and not just bed machine versus BedMap 2. The other question I had is, so can you separate whether it's really the structure of the bed, or if you have a different bed, you also have more or less ice sitting there in the first place? So is there a way that you can separate this?
I think after after a long periods of time, then it comes down to the bed again. I guess one thing I didn't compare was the actual difference in the amount of total ice lost, or like I'm always sitting there and like sort of a percentage that I could look at that. I don't think there's that much difference though. I mean, the ice surface is pretty different, and I said the mean depth is actually fairly similar. It's the features that are different.
Okay, great, thank you.
Is there another question for Dan? I don't see any in the chat. Okay, thank you so much, Dan. And we'll move on to our last presentation for this first half of the morning. So our next speaker is Bill Lipscomb from INCAR, and he's going to talk about the SNP-6 space projection of ocean force Antarctic ice loss. Bill, the floor is yours. And Bill, you're muted. You're still muted.
Sorry about that. Is that better?
Yes.
Thanks. Sorry about that. Sharing results from a study that's now in press at the Cryosphere with co-authors, including Gunter and also Nico and Zeiler, who you heard from earlier this morning. This is a study that was, I'm going to use a different screen. This is a study that followed from our participation in the ISMIP-6 project. ISMIP-6 is the ice sheet model intercomparison project for CMIP-6, which consists of a number of experiments exploring future sea level rise due to mass loss from the Greenland Arctic ice sheets. It includes both standalone and coupled experiments, and I'm going to be talking today about some standalone ice sheet experiments involving the Antarctic ice sheet. And I will just mention that the ISMIP-6 lead is Sophie Nowicki, who's one of the co-authors on this study. And Heiko Gelser, who's here, led the Greenland projections for ISMIP-6, and Elin Sarusi led the Antarctic projections. I'll just briefly review the broad results of ISMIP-6 projections. A study for Greenland led by Heiko with submissions from 14 modeling groups looked at Greenland ice sheet mass loss from low emission and high emission scenarios, RCP 2.6 and 8.5. And as you'd expect, there's much greater ice loss from the high emission scenario 8.5. By the year 2100, you have 90 plus or minus 50 millimeters of sea level rise due to mass loss from Greenland when forced by output from climate models. This is mainly from increased surface melting in the summer. And there is some variation across models, but models are broadly consistent in having order 100 millimeters of sea level rise from Greenland, mostly due to increased melting, with a smaller contribution from iceberg calving at the ocean margin. With Antarctica, however, the picture's much different and the uncertainties are much greater. The study led by Elin from 13 modeling groups showed that when you force standalone ice sheet models with atmospheric forcing derived from several Earth system models, as well as ocean forcing used to derive thermal forcing and melting beneath ice shelves, you get a big difference between different models and what the Antarctic response is. In the lower left, this picture shows the regional variation, regional contributions to sea level rise. On the left is the West Antarctic ice sheet, which varies anywhere from almost no change in sea level due to mass loss to quite large changes up to 180 millimeters of sea level rise by 2100. For the East Antarctic ice sheet, in some cases you have sea level rise, in some cases sea level fall due to increased accumulation from snowfall. So these differences are largely dominated by differences in snowfall in the different climate models and some differences in how the ice sheet models treat the snowfall. And then in the Antarctic Peninsula, not much contribution. So the message here is that we have large uncertainties in what happens to Antarctica due not only to the climate forcing from different climate models, but also to how different models treat ocean thermal forcing and the resulting subshelf melting and ice sheet retreat. So the idea of this study was to test the hypothesis that ocean warming, which is projected to occur in this century, at least under the high emission scenarios like 8.5, could drive long-term retreat, mainly in West Antarctica, but that most of the sea level rise would occur after 2100, a time period that wasn't investigated formally in ISMIP 6, largely because we didn't have a lot of climate model output from after 2100. So the method is using the ISMIP 6 framework, including ISMIP 6 ocean thermal forcing, find how much the Antarctic ice sheet retreats and raises sea level under a variety of basal melt schemes, including the schemes that were recommended for participants of ISMIP 6, and also different ocean thermal forcing from a set of 6 different Earth system models. The picture on the right shows how the Antarctic is divided into sectors. In this study, we use 16 sectors, which are roughly color-coded here. And in each sector, we tune one parameter to help us get the grounding line in the observed location when we're spinning up the model. So spinning up, we use surface mass balance from RACMO 2. We use ocean thermal forcing from a climatology that was prepared by Nico and Zeiler and others. And then for each basal melt scheme that we used, we adjust, beneath grounded ice, we adjust a basal friction parameter to make the ice flow slower or faster. And that helps match the observed ice thickness. And beneath ice shelves, we adjust a basal melting parameter, one per each of these 16 basins, to try to match the observed thickness of ice in the region of the grounding line and to get to the grounding line and close to its observed position. And the plot below shows that at the end of a spin up of 20,000 years, we have observed surface ice speed on the left, model surface ice speed on the right, and good agreement in most of the ice sheet between the observed and model surface velocities. We also have good agreement with thickness. So projections, we did a number of melt schemes, so-called parameterizations and calibrations, which were suggested by ISMIP 6. Going across, the columns are labeled local, non-local, and non-local slope, which refers to 3 different ways of treating the subshelf melt. And non-local slope has a dependence of the subshelf melt rate on how steep the base of the ice shelf is. So steeper means more melt. That dependence is not included in the local and non-local parameterizations. The 2 calibrations are referred to as mean Antarctic or mean Ant and Pine Island Glacier or Piggle. And the Pine Island Glacier calibration leads to more sensitivity of basal melt to ocean warming. And what you can see from these plots, in each panel, you see a sea level contribution between 1950 and 2500. The sea level contribution generally starts low and then picks up. At the high end, you have about 1,300 millimeters of sea level rise by 2500. And at the low end, only about 150 millimeters. So you have about an order of magnitude difference in cumulative sea level rise, depending on which of these melt schemes you're using. And it's not clear at this point which of these melt schemes is the most realistic. Looking at spatial patterns, you can see that in these various scenarios, here we have the top 2 panels are from the HADGM2 model, which has relatively large ocean warming. The bottom 2 are from CESM2, which has more moderate warming. The left column has a less sensitive melt scheme and the right column has a more sensitive melt scheme. We see the greatest retreat from HADGM2 with the more sensitive melt scheme. Most of the ice loss is from the Filchner-Ronne region and the Ross region. That's true generally across simulations. And we were a bit surprised to find there's not much ice loss, not much grounding line retreat in the Amundsen sector, which, however, is the sector where we see the most retreat today. Then we did a number of sensitivity studies. we found relatively low sensitivity of results to the stress balance approximation. Most of our simulations used depth integrated velocity solver originally developed by Dan Goldberg. We also used a three-dimensional or so-called Bladder-Patine solver, didn't find much difference. We found moderate sensitivity to grid resolution with ice loss increasing as you go to finer resolution from 4, our standard resolution, to 2, which we did a smaller number of simulations at. That's consistent with earlier work. Also, you had, as expected, some additional sea level retreat if you prescribe some ice shelf collapse, but not a huge amount more. The greatest sensitivity we found was to the basal friction law. As Zeiler mentioned earlier, so-called Coulomb laws, where the basal friction goes to 0 near the grounding line, generally give you more retreat than power laws, where you have much larger friction near the grounding line. For the Amundsen sector, we found that the basal friction law we used was quite important. In particular, we did some runs where we had a Coulomb friction law near the grounding line, and we also treated our ocean thermal forcing anomaly a little differently to try to compensate for the fact that most of our Earth system models didn't have a very large thermal forcing anomaly in the Amundsen Sea. And the plot on the left shows that with the PIGL, the high sensitivity melt scheme, you have collapse of the Amundsen sector, including the Thwaites Basin and the Pine Island Basin, whereas with this lower sensitivity melt scheme, not much happens. So we see threshold behavior here. The plot on the upper right shows with the topography on the grayscale, and it shows grounding line evolution with the different colored lines. So the grounding line is shown at year 2100, and then year 2200, where it's hung up on the subsurface ridge, and then year 2300, where it's broken free of the subsurface ridge and started to retreat catastrophically, and then 2400 and 2500. And so the message here is that the topography, in particular this feature shown, in many of our simulations is sufficient to stop the grounding line in the Amundsen region from retreating very much. But if you get past that one feature, then you have what looks to be irreversible retreat over several centuries. So the message is that Antarctic mass loss in these standalone simulations is very sensitive to parameters that are not well constrained in melt parameterizations, and to the model providing the thermal forcing, and to the basal friction law. Projected sea level rise ranges by more than an order of magnitude, with as much as 3 meters, depending on how you set these various parameters and forcing. And we see that ice in several sectors, including the Ross and Filchner-Ronne, and possibly the Amundsen, could retreat irreversibly over the next several centuries when forced by ocean warming of the magnitude that's expected to occur in this century. So a lot of limitations and uncertainties in this study. We have not initialized the system as well as we would like, and we'd like to use velocity data to more effectively to have a better initial state. We also have some fairly crude or parameterized physics that we'd like to improve. One thing we've discussed with ISMA-6 organizers is having a follow-up project to these Antarctic projections led by Hélène, where we would do some longer-term studies and look more closely at thresholds for instability, as this particular study analyzed. And also, as Bill Sachs will talk about in a follow-up talk, we would like to be able to do experiments like this in coupled mode. And so Bill and others are now working to support Antarctic coupling with multiple ice sheets, in other words, both Greenland and Antarctica, in CESM, so that we could run these experiments with temperature and salinity provided by POP and eventually from MOM6. One of the main challenges being that global ocean models usually run at a resolution of around 1 degree, which is not nearly fine enough to resolve ocean circulation in and around ice shelf cavities. And with that, I would be glad to take any questions you have.
Thanks, Bill. Any questions for Bill? None?
Yeah, Bill, I'll ask
Rob.
you a question if it's all right. You mentioned
Bill.
the resolution issue. Do you have any idea what resolution would be required?
Well,
1
there's-
degree doesn't do it. What would do?
That's a very good question. I might ask Zyler to answer as well. There's studies that suggest a resolution of the order of 1 or 2 kilometers is what you need.
Yeah, I think so.
Yeah. So that's obviously out of the question for a global model. So then the next question is, can you develop parameterizations or simpler reduced physics models that get you maybe 80% of the way there to having a fine resolution model, but that you can afford to run in a global model forced by global ocean output. Would you like to add anything to that, Zyler?
Well, just to say that we're working diligently on E3SM, where we would have the ability to, with regional refinement, to have some degree of, I mean, we're not going to get to 1 kilometer resolution. That may not be a requirement. It would certainly be nice for a lot of the physics, but yeah, we'd like to get somewhere between 1 degree and 1 kilometer, and there's a lot of space in between there to hopefully make improvements. But yeah, it's very, very much an active area of research, and whether parameterizations can be a substitute is also not clear, but an active area of research.
Thanks. Robert, you had a question?
Yeah, so this is a sobering talk. 2 things come up. One, your 2 kilometer resolution, by the time you've taken into account the convergence of the meridians, is 1/10 of a degree ocean model, roughly. That's like 2.5 kilometers at 75 degrees south. So it might not be quite so out of the picture, given that we've seen some really nice talks with 10th degree models, and so it might be more doable than we think. The question, and this may be a little bit premature, noting that there's another talk coming up. Do we know exactly what the obstacles are at this point to achieving your vision of running with multiple different configurations? Is it agreeing on common coupling strategies along the lines of PhysOc? Is there something else, or are there just unknown unknowns that we need to be worrying about?
For coupling multiple ice sheets, for coupling Antarctica?
Coupling different ice sheets with different oceans, and again, leveraging the power of the community to explore these critical questions that you talked about.
Yeah, I think at this point, the obstacles, the things we know about are primarily technical and definitely solvable with a certain amount of work. Whether we see systems that go haywire when we couple them is something we don't know yet. We'll find out once the technical obstacles are overcome. You raise a very interesting point about the coming together of the meridians. I think having variable resolution as an E3SM, which Zyler discussed, is a great strategy. And it may be that even without that, with MOM6, with grids that are designed thoughtfully with the Southern Ocean in mind, we may be able to come closer to these target resolutions.
Thanks.
Thank you. So let's end the session here. If you'd like to talk with any participants offline or during the break, you can ask Elizabeth to be sent into a breakout room. Otherwise, we're going to reconvene in 25 minutes to have a 25-minute break at least. And so let's reconvene at 10:35 if that's okay with everybody. And thank you for a great first morning session.
Thank you, Gunter.
How did that go for you, Bill?
Oh, worked fine. There,
Good.
just a
did
couple of us
realize-
there.
Yeah, Trevor. I just didn't, I can't share sort of that like placeholder slide and see the chat with breakout rooms. So that's why it was just a little bit delayed. It's just that complication. Even though I have two screens, it's still the way that Zoom layers things. It's hard to manage.
Yeah, I haven't really figured out breakouts yet myself.
Yeah, I think as a co-host, do you see a button at the bottom that says breakout rooms next to record?
I do, yep.
Yeah, I think as co-host, you can set them up and run them as well.
Yeah.
Well, and we lost quite a few people after that first session too. Maybe they'll come back.
Now, did Gunter say come back at 10:30 or 10:35?
Oh, I was going off the agenda. That's
He
a
said
good point.
10:35.
Okay.
That's why. All right. How are you doing, Bill?
I'm doing all right.
That's a familiar office. I've talked to you there a few times before. I have my more formal, my less formal office. This is my more formal office.
Oh, nice. Yes.
but Emily is usually here during the school day, and so I got special dispensation today to have the office, and she's in the basement. But more often I'm in the basement.
Okay. This turned into my more formal office today. As you might notice, I cleaned off the this table space instead of having it piled up with junk.
I only get relocated from my office when there's a test for my son. Otherwise, he takes over the living room, which makes it awkward when sometimes I'm walking through to get more coffee and he gives me the like, I'm on, my camera's on.
Where is he in school?
We live in Arvada, so he's at Ralston Valley. He's a senior.
Interesting time to be a high school senior.
Oh, it's so stressful. Yeah.
So, Bill, I didn't clean off my.
That's all right. It at least looks more work oriented than the.
Yeah, they're piled. My desk is another matter, but over there it looks like.
Yeah, mine was just kind of junk. So
I have to get off of using paper so much, but I haven't yet. Elizabeth, I didn't realize I hadn't registered for this meeting, but it worked flawlessly. When I tried to get on Zoom, it just beep, beep, and I was on. So
Sure, yeah. The way Zoom is connected to our UCAR accounts as well, it kind of pre-fills in those spaces for you. So good. But I am worried that even when I send out a link that people still have to register, and that's unavoidable with cybersecurity. That's why I put that extra message in the Paleo message that went out.
Well, it was so quick, it didn't matter.
That's why I did say it just takes 2 seconds.
Yeah.
Gunter, are you standing by? We're about a minute from reconvening.
I'm just trying to find my Zoom window again. It appeared on me. What happened?
Are you able to share your screen, Gunter?
I've lost my Zoom window.
Huh. Hiding beneath other windows?
Oh, there it is. Okay.
Okay.
All right. I
Well,
will not touch this anymore.
all right. Well,
You
let's
should be able to see it in your tray at the bottom too, or I guess if you use a Mac, it's at the top, but the sort of like Zoom camera should show up for you.
Yes. So I should. Hopla. Can you see this?
Yes. So welcome back, everyone, for the second half of our session. We're going to start off with Gunter Legee, my colleague at NCAR, who's going to be speaking about marine ice sheet experiments with the community ice sheet model. Go ahead, Gunter.
Thank you, Bill, and good morning again, everybody. So I'm going to present some work that has just been submitted, is under review in the criteria discussion that we worked on with Bill Lipscomb and Valerie Davis, who gave presentations early on this morning. And it's about marine ice sheet experiments with the community ice sheet model, CESM. The main goal of what I'm going to present here is to try to understand more the numerics and numerical behaviors that marine ice sheet undergo in the community ice sheet model when they're subject to ocean forcing, in this particular presentation, basal melt. And what we're trying to achieve with this is to try to configure CESM with default for Antarctic simulation. And what we have in mind here is as we're moving ahead with ice-ocean coupling, what you're going to get when you enable ice sheet simulation with CESM. So in order to run these experiments, we're going to consider the MISMIP plus framework that I talked about this morning. So thank you for laying down the ground for me. And it consists in this bed topography that slopes as a polynomial at the bottom at the bed. And it's a big trough that has very high walls. And you can see a schematic of it right here. And eventually, so the ice is going to flow in this trough and it's going to reach the ocean eventually. This configuration has strong buttressing thanks to those big walls. The melt function that we would apply is the one given in Seattle 2018. It is capped at 0 meters per year for any basal shaft depth that's above 50 meters deep, and it's capped at 30 meters a year for any depth that is below 500 meters, and then it grows from 0 to 30 meters a year linearly with basal draft. We're going to use the same MISMIP plus experimental protocol in that we start by spinning up the model to reach a steady state that brings us to the year 0 in our experiments. And then for the first 100 years, we are going to start inducing melt under ice shelves. This should induce a retreat of the ice. And we're going to do this for 100 years. After 100 years, we have two subset experiments, one that just continues with inducing melt, and another one that will investigate what happens when we switch off that melt, in which case we should see, in theory, an ice sheet re-advance. This second set of experiments is run for an additional 100 years. And then a last set of those two experiments, continuing these two experiments for 800 additional years. In this experimental setup, we're going to investigate several parameters and dynamical configuration. And one of them is going to be different basal friction laws. And as Zyla and Bill already mentioned this morning, the community typically uses two basal friction laws: a Wettman friction law, which is illustrated here, which has a positive basal stress that discontinuity goes to 0 at the grounding line, which is the position where the grounded ice becomes afloat, or the Schoof, which has the property to smoothly decrease down to 0 at the grounding line. And we're also going to look at an intermediate state between the Wettman and the Schoof sliding law. And what the main difference is that the length scale over which it decreases smoothly to 0 at the grounding line happens over is smaller. So one of the main parameters here we want to investigate is the way we apply the melt rate underneath the ice shelf, and more particularly at the grounding line. And this is a subject of many discussion, of a lot of discussion in the community, and particularly how should we treat the grounding line as a cell containing the grounding line. So when the cell contains ice that is fully floating, there is no discussion. We apply a full melt rate in that cell. And when the ice is grounded, which is illustrated in brown here in this figure, we don't apply any melt. The blue, here considers this to be a fully floating cell. But in the cell containing the grounding line, which is this dotted line here, this is a topic of discussion. Typically, the grounding line does not lie on the edge of the cell. It's typically in the middle of the cell. And we diagnose this grounding line using parameterization in CESM. But how should we apply the melt rate in that given cell? Some argues that we should consider that cell fully grounded and not apply any melt, which would be the case for this parameterization, which we can call the no melt parameterization. And we can consider two other cases. One that considers that we should apply a melt that is proportional to the surface area of the cell that is floating. So it's a partial melt parameterization. Or we can also envision that given the location of the grounding line compared to the cell center, we can consider the cell to be grounded or floating, in which case we will apply 0 melt or full melt in that cell. And the question here is, which option should we use? Many modelers argue that we should use a no melt parameterization. In this experimental setup, we're going to vary several parameters, one of them being resolution. You're going to see results varying from 8 kilometers down to 0.5 kilometers. We're going to vary the basal friction laws that are introduced earlier and the melt parameterization. The steady state of the grounding line, the steady state of each ice sheet is tuned using the ice softness so that the grounding line lies at the position of 455 kilometers plus or minus 1 kilometer, which is in this part of the domain. And this is because bed slope topography has an impact on ice sheet dynamics, and we didn't want this to be an additional parameter to try to detangle our result with. We're going to consider 3 scenarios. One that the first experiment is going to be one that has moderate melt, and uses the melt from profile from CRCNO 2018 with a maximum melt rate of 30 meters per year. We're going to use a uniform accumulation of 0.3 meters per year. Then we're going to investigate what happens if we really force the model with a very high melt of a maximum of 150 meters per year with the same accumulation rate. And then we're going to finally investigate what happens if we apply a moderate melt on a very slow moving ice. And the way we're going to get a slow moving ice is by reducing the accumulation. So let us jump right in and start looking at results after 200 years. So what you're looking at here is the first set of experiment with moderate melt. And you're looking at the evolution of ice mass above flotation. In the rows, you're looking at result based as a function of basal friction law, Wertmann on top, intermediate in the middle, and Schoof at the bottom, with a different melt parameterization results in the column. And for you to remember what they are, here's the same schematic as in the previous slide. So FCMP, PMP, NMP, which are all aligned here. The different resolution are being highlighted in those different colors. So 8 kilometers black, 4 kilometer in orange, 2 kilometer in blue, 1 kilometer in green, and half kilometer in purple. So the first observation we can make by looking at the results is that results using the FCMP or PMP parameterization are very similar. And the other one is that using a Wertmann sliding law or in the intermediate sliding law also lead to very similar results. Now, in terms of convergence, and here convergence, I mean the result, how do results compare respect to the highest resolution of 0.5 kilometer? And we can see that using a Wertmann and a PMP parameterization leads to the fastest convergence results. This convergence is slightly worse using a Schoof sliding law. And you can see that results within 1 kilometer are the most accurate compared to 0.5 kilometer, which is not too surprising, but the results at 4 and 8 kilometer are very far apart in this configuration compared to the one in Wertmann. And for all results, the NMP, using NMP, the convergence results are always worse compared to the PMP parameterization. So based on what I said, we can now just focus on 4 panel, and for the purpose here of this presentation, we're going to focus on PMP and NMP and Wertmann and Schoof. This is a full 1,000-year experiment, so the continuity of having melt on and switching off melt. And you can see here that the qualitative results of the entire experiments are very similar during 1,000 years compared to 200 years. What we can notice here is even though after 900 years of not applying any melt, the grinding line has not reached its original steady state solution. And this indicates that the melting is strong enough to remove ice mass on a faster time scale than it can be restored through surface accumulation.
Gunter, you're at 2 minutes, please.
Yes. And so with this result, even over the 1,000 years, we can see that a resolution of 2-4 kilometers is sufficient when we use a Wertmann and PMP parameterization. And when we use Schoof, we need 1 kilometer. On a high melt scenarios, meaning the maximum melt rate is 150 meters per year, the results are very qualitatively similar to those as the moderate melt rate, besides the convergence is slightly worse in that we need more 2 kilometers resolution to better approximate the high resolution results when we use a Wertmann basal stress, and the condition of 1 kilometer remains valid for Schoof. In the interest of time, I'm going to move to this last case. So the low accumulation of slow moving ice is interesting in the sense that the argument can be made that on a quasi-static or very slow moving ice, if we apply some melt in the cell containing the grinding line, this could lead to artificial retreat. And so to test this, I said we lower the accumulation, which lowers the ice velocity by a factor of 6 at steady state. And we can see that this is not the case in CESM, that allowing some melt in cell, including the grinding line for CESM, remains beneficial as a convergence with resolution remains better compared to not applying melt parameterization. And also in this configuration, the Schoof parameterization, basal friction law, leads to better convergence results. Last on this slide, we can see that after 900 years of switching off the melt, the grounding line still has not started to retreat at all. And this indicates that the accumulation rate, rather than the buttressing, set the readvance timescale of a simulation, which could be important for us in future Antarctic simulation. So to conclude, for CESM, allowing some melt in the cell containing the grounding line is beneficial, and this is what you're going to have as a default configuration when you use the Antarctic capabilities in CESM. With a Wertmann law, a resolution of 2 km, agreeably 4, is adequate to accurately diagnose the grounded ice loss. With a Schuf law, the resolution requirement becomes 1 km, arguably 2, and the readvance of the ice sheet is controlled by the accumulation timescale. And so what we can learn from this lesson is that you need to test your model, because some model would argue that and also prove that not applying a melt rate is more beneficial for them. And we plan on redoing this experiment in more realistic setting later. Thank you.
Thank you, Gunter. I think we have time for one question, if anyone has one. Any questions? If not, Bill Sachs, would you like to go ahead and queue up your talk?
Sure. Yeah.
Thanks again, Gunter. Next talk will be given by Bill Sachs, also at NCAR. Bill was the Land Ice Working Group software liaison for several years and has come back to work on a project. He's come back to work on a project on Antarctic coupling. His talk is called Antarctic Ice Sheet Coupling in CESM, or actually the longer talk you have there.
Yes, I changed the title a bit. Can you see my slide all right here?
Yep.
Okay. Yeah, well, thanks for the introduction. And so I'm going to be giving a kind of technical talk on some of the technical needs that we've been needing to address in order to enable both running Antarctica out of the box in CESM with CISM, as well as enabling multiple ice sheets in a CESM CISM run. So for as long as CISM has been coupled into CESM, the only out-of-the-box support has been for the Greenland ice sheet, and more critically, we've only ever been able to run a single ice sheet at a time in CESM. And so I've been working with others, especially Mariana Vertenstein, Bill Lipscomb, and Brian Kaufman as well did some work a few years ago to add the support needed to both support running Antarctica out of the box in CESM CISM and also to run multiple ice sheets in a single simulation. The initial target of those multiple ice sheets will be running Antarctica and Greenland together, but the same infrastructure can be applied to extend this to other ice sheets, including paleo ice sheets. I'm also going to discuss in this context some related changes to software infrastructure that are just useful to be aware of that are coming down the line or have already arrived. So first, in this realm of kind of related software infrastructure, some of you may have heard of this, but if not, this is an important thing to be aware of. Within CESM, we are moving to adopt a new driver and coupling framework. And this, as I'll explain in a minute, is important to understand for these Antarctica and multiple ice sheet capabilities. But I just want to give a quick introduction to this so you can kind of understand what I'm talking about here. If you've seen the kind of hub and spoke architecture of CESM, this picture might be somewhat familiar. This is still, CESM is still going to be a hub and spoke architecture, but now the hub in that architecture is what we call either NUOPSI or CMEPS. So NUOPSI is a layer on top of ESMF, the Earth System Modeling Framework, that simplifies the creation of coupled modeling systems. And then CMEPS, which stands for the Community Mediator for Earth Prediction Systems, is CESM's new kind of mediator, or AKA coupler infrastructure that we are moving to adopt. And a number of people have been working on this over the last few years, and it's finally kind of coming to fruition. There are a number of technical advantages of NUOPSI and CMAPS, a couple of the key ones being that mapping weights between components are now generated at runtime, which means you won't need most of the mapping files that have historically been a pain to produce when you're introducing new grids to the system. It also brings an easy to see and modify driver run sequence. But some of the big advantages are really more kind of community oriented. So this is a community effort that extends beyond NCAR, so leverages a larger development community for new features, and also provides interoperability with other modeling systems around the US that are also moving to adopt this new NUOPSI and CMAPS framework. So why is this important? We've found that this framework greatly simplified the ability to bring in the ability to have multiple land ice grids within the system. And so Mariana Vertenstein over the last couple of months has extended CMAPS to support this, to support having multiple land ice components, which would have been much more difficult in the old MCT based framework. So that's kind of was provided the first key component that we need for multiple ice sheets. And I'll talk about some others, but first just want to let you know kind of the overall picture of this NUOPSI CMAPS status, since it is so relevant for this work. So right now this is available in the CESM development code. For the most part, the functionality that's needed by CESM is now in place and validated. There is a little bit of final functionality that's kind of coming in over the next couple of months, as well as some performance improvements. The plan is for this NUOPSI and CMAPS infrastructure to be the default coupling infrastructure for CESM 2.3, which will be the next release of CESM. The MCT, the older MCT coupler 7 framework will still be supported in CESM 2.3 for kind of pre-existing functionality, but new functionality is just being done within this NUOPSI framework, including all of this new land ice relevant functionality. So those who are interested in running with Antarctica or running with multiple ice sheets will need to switch over to using this new NUOPSI based infrastructure, and that's an easy thing to do, and I can work with people on how to do that. But it's basically just an extra flag on the command line right now when you're creating a new case, and then by CESM 3, possibly earlier, we will drop support for the older MCT coupler 7 for any application within CESM. Another kind of background software task, infrastructure task that was kind of a prerequisite for this work was converting CESM's nameless generation script from the old Perl to Python. And I bring this up mainly because this is potentially interesting to those, especially in the Land Ice Working Group, who are needing to introduce new parameters into the model. If you've done this before, you know that this used to be a somewhat complex process that involved modifying 3 different files. There were 2 XML files as well as a Perl script that you would need to change to bring in a new configuration parameter. The new Python infrastructure is more data-driven and dynamic, and allows you to just edit a single XML file to add a new variable, and then that is picked up dynamically by the script. So here's an example of one arbitrary parameter in CESM and what it looks like to introduce a new parameter into the system. Okay, so that's kind of it for the background infrastructure work, and then let's get on to what was actually needed and what is needed for bringing in Antarctica and multiple ice sheets. So the first piece of this has involved bringing in support for Antarctica grids and comp sets. So far, we have we've extended the comp set specification to allow you to specify whether you want to run with Greenland, Antarctica, or both. We have not yet finalized the kind of grid resolution specification and how that will play out, but we sort of have that kind of conceptually mapped out. And so this just gives a few examples of what things will look like. This gives what we call the T-comp set, which is basically running standalone CESM within CESM. And so the main difference here is that in the comp set name, where you would have had something before like T1850 capital G, you'll now explicitly specify which ice sheets. And so with a lowercase g for Greenland, a lowercase a for Antarctica, or an AG for both Antarctica and Greenland in the comp set name. And then similarly, we envision for the resolution doing something similar. And so then the scripts, and building on the kind of update to the Python infrastructure, the scripts will be able to recognize which ice sheets you are running with and generate your configuration files for you based on that. I also want to note in this context, the forcing data for these standalone CESM runs within CESM. So for these T-comp sets, we are updating those to use output from some of the CMIP6 pre-industrial control runs. We'll update that both for Greenland and for Antarctica. Those CMIP6 runs did include forcings over Antarctica that are needed to drive these comp sets. And so, yeah, another piece of this that is largely in place at this point is being able to specify different configuration settings for the different ice sheets. And so there's two pieces of this. One is allowing the configuration settings to differ per ice sheet out of the box. And so we'll specify in the XML files that as a user, you don't really need to be aware of what defaults are the same for Greenland and Antarctica, which ones differ. But the other piece of this is, as a user, being able to override settings for particular ice sheets. And so that second piece is not yet implemented, but we've kind of conceptually mapped out how we want to do this, which is within your, if you've run CESM, you're familiar with these user NL or user name list files. So within your user NL CESM file, you will have sections that apply to all ice sheets at the top, and then these separate sections that apply to each individual ice sheet, as shown on the right here. So and finally, the final set of changes needed that's still kind of ongoing. We do need to change some of the Fortran code. This includes both some changes in CESM's parallel module, which Bill Lipscomb is working on, and then some of the code at the interface between CESM and CESM, which was work started by Brian Kaufman a few years ago, and then we're bringing that into the latest code base. CESM itself was set up initially, as I understand, to allow the capability to run multiple ice sheets within a CESM run. And so a lot of the infrastructure on the Fortran side has already been there, although this hasn't been exercised and tested recently, as far as I'm aware. So we might run into some other challenges at the end there. But we believe and hope that within the next couple of months, this capability will be fully in place, and you will be able to run multiple ice sheets in CESM run. So with that, I'll just take any, be happy to take any questions or comments on this.
Thank you very much, Bill. Would anyone like to ask Bill a question?
Yeah, Bill, could I ask you a question? Suppose you want to run an ice sheet, say Baffin Island alone. Would you then have just a third have to do it all as just another system, or could that be incorporated in Greenland in some weird by giving it some kind of configuration?
Yeah, good question. I mean, I think the answer is you could do it either way. Right, you could kind of use the Greenland, if you'd say, well, this is I basically want to use the Greenland settings and just specify a different grid. You could do it that way. Just let it be called Greenland in the system, and it'll pick up the Greenland defaults. The other way is that you will be able to introduce a different named ice sheet, and so that is particularly for sort of paleoclimate runs where someone might want to model the Laurentide I think the ideal way to do that would be to introduce another ice sheet into the system, and so we'll try to document what that will involve. The way that we're setting it up, it will take a little bit of addition to the scripts, but not too much. So it shouldn't be a huge undertaking.
Okay.
Okay, I have two more questions. First, Bob Hallberg, and then Adam Harrington.
Thanks. I really appreciate all the science that this enables. But one of the questions that this raises is how much backward compatibility and how long is there a promise to keep things around? So for instance, older versions of CESM, you talk about the changes that will be needed. Those are for future versions. Is anybody talking about actually deleting older versions?
So no, I mean, so, and let me be clear. When I say we're dropping support, what I mean is that, so I think you're referring to things like the new coupling infrastructure. And when I say dropping support, I just mean that in the latest code base, if you want to run, there will be a point where within the latest code base, you will be running with the new coupling infrastructure. The support we have a support policy for CESM versions that, like for CESM 2.1, which was a big production release, I believe we say we'll support it for at least, I might be getting the numbers wrong, 5 years, or at least a year past the next sort of major production release. So we will provide, we'll continue to provide support for people running CESM 2.1 for a longer period. Does that address your question?
Yes, and the reasons why I'm asking have absolutely nothing to do with NCAR, as you might have guessed.
Yeah, okay.
Thank you very much for that clarification.
Okay.
Adam.
Hey, Bill. Thanks a lot for this work. This is great. So one, I have a clarification question and then a question. So you're saying that for every CESM nameless that exists, you can specify it to be different for different ice sheets. So you're generalizing it like that?
Yes, that's right.
Okay, and so here's it would be nice to be able to have that same control for the surface mass balance calculation in CLM.
Mm-hmm.
And I'm wondering whether that's a reasonable goal, or if you foresee a lot of obstacles in offering different surface mass balance nameless for different ice sheets.
Yeah, good question. This has been raised. I don't know if you're on the emails. This was raised recently in an email thread. The answer is that is possible, sort of. That there is some, there's some code changes that would be needed to support that for a given variable. But I understand the desire to do that, and it's not too challenging. As I think you might be aware, there, the way CLM delineates its ice sheets is not exactly the same as sort of a CESM ice sheet, but so it's sort of left to you as a user to make sure that CLM's notion of different glacier regions of the world actually corresponds to the different CESM ice sheets. But if you've done that step, which is in place out of the box, but just needs some tweaking if you're sort of introducing new grids, if you've done that step, then we can allow you to change
right.
A handful of variables per ice sheet. I think we just need to have some discussion about exactly which variables those would be.
So you're saying that's already kind of done, is what you're saying, based on you have these vectors of nameless.
Right, the general infrastructure is in place for it. There's only a very small number of variables right now that do differ by sort of glacier region or ice sheet, if you will. But that could be extended. Yeah, that could be extended, is what I'm saying. But it sort of is a variable by variable thing. There's not an easy way to just say, okay, take this whole suite of variables and make this possible. It will need a little bit of code work for each variable that we want to do that with. So we'll need to have some discussion about what those variables are.
All right, yeah, thanks for answering that. And but again, what has been done already, I think, is very impressive and useful. So I just want to make that clear. Thanks,
Okay,
Bill.
Thanks, Adam.
And I wholly agree. Thank you, Bill. We'll move on to our next speaker, Gustavo Marquez. Also at NCAR, he is the science liaison for the Ocean Model Working Group, and will be giving us an update on the CESM MOM6 effort. If you'd like to go ahead and share your screen, great.
Okay, thanks, Bill. I just want to say that my connection is really unstable this morning. If I get kicked out by any chance, Frank Bryan has my slides and he will take over. So I apologize in advance, but hopefully it won't happen. So I'll mention the efforts that we've accomplished over the last 6 months or so in terms of bringing OM6 into CSM and performing experiments. I want to acknowledge all the people involved: Alper Altuntas, Carl Batman, Frank Bryan, Gokhan, Danam Pashoglu, Ian Grooms, Bill Large, and Keith Linson. So first, MOMSIC has been released as a functional component starting in CSM 2.2. If you have CSM already ported to your machine, you can start using MOM6 in less than 5 minutes. All you need to do is download CSM MOM6 using this fork, and then check out the CSM 2.2 tag, which includes MOM6, and that's a branch inside Alper's fork of CSM. I'm putting it in the slide here. Check out the external libraries, and all of that will take approximately 3 minutes. And if you want more details on how to use, modify, and so on, here's the link to some quick instructions on how to do all of what I'm showing here, plus run MOM6 and making modifications. This table shows the available configurations that we currently support within CSM MOM6. If you're familiar with the CSM terminology, the C ComSets are ocean only, the G are ocean and sea ice active, everything else is via data stream, and then the B is the fully coupled. So we support, we have 3 grids that we're working on right now. The TO61, which is our workhorse, so that's the 2/3 degree, which I will talk about today. And then we have 2 other grids. This is the one all the way on the right is the old POP grid. And the one in the middle is the 1/4 degree from GFGL, which you use for testing purposes. And most of the ComSets support all of the 3, with the exception of the fully coupled we just do for the workhorse, as well as the G ComSets with GRA and the C ComSets with GRA. Now moving to our workhorse configurations. This table shows side by side what we have for both POP and MOM6. I'm listing a few parameters here, starting with the horizontal grid, which in POP is a nominal 1.1 degree with a dipole and equatorial refinement, while in MOM6 is a 2/3 degree with a tripole and equatorial refinement. Then in terms of vertical grid, POP has a Z coordinate with a vertical resolution near the surface of 10 meters and 60 levels, while in MOM6, by default, we have a Z-star coordinate with 65 layers and 2.5 meter resolutions near the surface. And everything that you see in blue here, those are optional configurations that you can enable. So for example, we also are working with a hybrid coordinate system. It's a hybrid between Z-star and isopycnal. And it has a resolution, 85 vertical levels. And is near the surface is the Z-star grid with the same type of resolution as the Z-star itself. Then in terms of freshwater boundary conditions, in POP is a constant volume, virtual salt flux. In MOM is variable mass, natural boundary conditions. Vertical mixing is the same in both. We're missing the Langmuir component in MOM6, which we will add soon. For the GM and Reddy, we have the n-square scaling from Marshall et al. While in MOM6 we use the Mickey plus geometric scaling with an option to enable the GME backscatter. POP uses an anisotropic Laplacian for horizontal viscosity. In MOM we use isotropic Laplacian plus biharmonic, and both are controlled via Mickey. Solar penetration, POP is Ullmann 2003, MOM6 is the Manitza 2005 scheme. Advection, 3rd order for POP. For MOM is piecewise parabolic in the horizontal, and in the vertical we're using third order remapping, but you can go anywhere from second order to fifth order. All the parameterizations, POP has the overflow and the estuary box model or EBM. We don't have none of those in MOM6. We plan to add the EBM. It's unclear whether or not we will need to add the overflow. And then finally, both have been coupled via MCT and UOPSI. And again, UOPSI is not the default. If you start using MOM6, you start using with MCT, at least for now. I'm going to show some vertical coordinate exploration that we've done over the last few months. So we forced the model. So this is a G-comp set, so ocean and sea ice, and we're using size 5. We forced the models with the GRA 55 version 1.3, which was run for 1 cycle. This version has a 58 cycle length cycle. The initial condition comes from the World Ocean Atlas 2018, TNS, and we apply restoring also from the same climatology using a piston velocity of 60 meters per year. These are the experiments that we have done. The very top one is the out of the box, so the Z-star with 65 layers. And then I ran a case with Z-star and 75 layers. Then I hybrid Z-star isopeak with 75 layers, and then finally a hybrid with 84 layers. And all the average fields I'm going to show were done over the last 30 years of the simulation. I've also looked at a POP to simulation that's very similar to the ones for MOM6, different initial conditions though. And just I'll try to use as a comparison for the next set of diagnostics. So this is the global mean potential temperature drift for all the 4 cases. You can see that the Z-stars case, the 2 on the top, are together and they tend to show a warming, while the hybrids, as the green and the red, tend to show overall cooling. There is some differences whether you use 65 versus 75 or, 75 versus 65 or 85, but it's not significant compared to the choice of coordinate system. So it's really remarkable, and it's in agreement with other studies that if the hybrid coordinate system, you get way less ocean heat uptake. This is as a comparison, this is a much longer run with POP, but if you focus on the first 50 years or so, you see that it's doing something similar to what MOM is doing with the hybrid coordinate system. In terms of potential temperature biases with respect to the World Ocean Atlas 18, this is at 700 meters. And again, it's average over the last 30 years of the first GRA cycle. The top plots are the Z-stars, the bottom ones are the HICOM ones. Left is smaller number of layers, right is higher number of layers. Between the Z-stars, they're really, really similar. Same for the hybrid coordinate system. So this metric doesn't really catch much the number of layers. It does get influenced by the choice of coordinate system. You see that the MAD-C seem to be detraining at that depth in the Z-star realms, while the HICOM one does not show that same warming signal near the MAD-C outflow. I just plotted on top of the top right panel here now the POP minus the PHC2 climatology, which is what was initialized with. And there is a lot of similarity, especially with the Z-star case. You can see a little bit of the MAD-C2, and but overall the RMSs, area averages, are larger for POP than with MOM6. I should say with the Z-star MOM6. Oh, rather the HICOM one coordinate system. Sorry. Now changing to the winter mixed layer depth. This is using the 0.03 meter kilogram per meter square criteria. Sorry, there's a typo in the units here. The top, again, the panel on the left is the Z-star out of the box. And then on the right, I'm plotting the climatology from De Boyer. Again, the wintertime mean. We see that overall, we're capturing the patterns of mixed layer depth. There's some differences at high latitudes, but presumably the climatology doesn't coverage very well those areas. Now, I'm plotting all the other experiments minus the out of the box. So if we increase the number of layers with Z star, we don't see much of a difference. Between the HiCom1 coordinate systems and Z star, we see a lot of differences. And overall, like, we get deepening of the mixed layer pretty much everywhere where the mixed layer tends to be deep. The regions of bottom water formation and the Southern Ocean region. Between the two HiCom1 cases, there isn't much of a difference. In terms of forward heat transport, all the thick lines are the cases with MOM6. So blue is the out of the box. This yellowish is the 75 layer with Z star. Green is the HiCom with 75, and red is the HiCom1 with 85. And then I'm plotting the POP case in purple and the heat transport that we expect based on the GRA forcing. So it's the mean plus minus 1 standard deviation using the 58 years. In addition, there's this point showing what the has been inferred using observations. So what we can see is that the Z-star cases are kind of on top of each other, especially in the Northern Hemisphere. And they tend to be weaker polar heat transport than the HiCom1 cases, which are also kind of on top of each other, but have much stronger heat transport. And overall, the HiCom1 cases is the one that's closer to what we expected in the Northern Hemisphere. Same for the Southern Hemisphere, although if you compare against the POP case, we can still improve the strength of the polar heat transport in this region, in the ACC region. Switching to the AMOC, again, the top panels are Z-star, bottom panels are the HiCom ones, left is less levels, right is more levels. Overall, there isn't much difference between the two Z-star cases. I'm showing here the maximum AMOC at 26 north, it's around 13-ish Sverdrups for both. When we switch to the HiCom1 coordinate system, we get a way better AMOC representation. Notice that it's pretty shallow. We've seen this in many talks, with Z-star in particular. It does get better with the HiCom1 coordinate system, but it's still not changing sign as deep as we would like to, but it is a significant difference between the two coordinate system. And the strength, 2 minutes,
Gustavo.
Thank you. And the strength is also much closer to what we expect at 26 north. So now this is shown in this time series. The line on the top, the black line, is the mean from the rapid array. So the HiCom ones both are much closer to the OBS. For the interest of time, I'm going to go quick. A major thing that we need to do is to reconcile the energy exchange with the other CSM components. As I mentioned, MOM6, you have variable mass. So every time you have like liquid precipitation, like rain, or solid, like frozen from the land ice, or vapor, every time the mass changes, there is a associated heat exchange associated with that mass. So for example, if you were to add frozen runoff, there's the latent heat associated with frozen runoff, which is the mass times the latent heat of fusion. And that is done even with POP, and it's already implemented in the couple. However, there is a sensible or enthalpy part associated with adding or removing mass, which is done in MOM6, but is not done in the CSM level. And you might wonder how important that is not to account for these enthalpy terms. And I ran a 1 year long fully coupled simulation. And if you combine the enthalpy of all the mass terms, it can lead to a difference of 0.22 watts per meter square. So it is significant, very significant and important. And we'll start working on this this week. In summary, we have a preliminary version of MOM6 that was released in 2.2. The same code base is being used for a wide range of applications I didn't mention here, but there's a simplified version of CSM OM6 for aquaplanets and quasi-aqua experiments. Regional configurations also has same code base, and then global in the workhorse and the high resolution. In terms of MOM versus POP in CSM, overall the quality of forced solutions with MOM6 are comparable to the ones with POP. However, locally there are some places that are better or worse with MOM6. Vertical coordinate exploration, there's a significant reduction in the heat uptake and TNS biases when using the hybrid coordinate, which is consistent with other studies, for example, from Alistair, 2019. And then other metrics, pore heat transport, AMOC, mixer depth, etc., are also better represented with simulations using the hybrid coordinate system. I'm just going to go super quick here. What we're doing next, again, we're going to reconcile the energy exchange between the components, and this is right now. We plan to add additional parameterizations, so coupled with the wave model, this will be our next parameterization that we'll be adding. And then the EBM, estuary box model parameterization, which is somewhere in the summer, hopefully. Unclear whether we're going to do a gravity current or overflow parameterization. We'll always be experimenting and tuning the model and try to reduce the bias. Possibility for adding additional resolution, low resolution for BGC, Eddy permitting. We showed yesterday on the CGD seminar, we're using a high resolution already, leveraging the work in the CPT. Then finally, in terms of CSM, MOM6 coupling, we have possible 3 strategies for coupling sub-shelf melt rates. I'm not going to go into the details, but no, we have these 3 that we kind of have in place right now. The third one is the ideal one, which is now computing basal melt rate in the coupler rather than in the ocean model. And then we plan to participate in the MISOMIP2 experiment that Nico described earlier this morning, and we will leverage the work from a PhD student from Utah. Thank you. I'm happy to take any questions.
Thank you, Gustavo. Frederick, would you like to ask a question? And then after that, Steve Griffiths.
Yeah, Gustavo, just so hybrid coordinate are often seen as a way to have like similar quality using less level. In your exploration of the hybrid, apparently you are using more level than in the Z coordinate or the Z star coordinates. That sounds counterintuitive to me. Can you comment on that?
So we have one case that we have 75 in both, right? So that's why we did, we have these 2 cases that have 75 layers. Because that was a question like, no, we were using, the hybrid cases were better, but we had more degrees of freedom. And so let's have the same degrees of freedom in both and see what happens. What you're saying is that you can go even lower vertical layers with the hybrid case and presumably get as good as a result. Is that what your question is?
Yeah, well, that's what people often argue. Yeah. Like if you ask Eric, I don't know if he's on the call, I think ICOM is using like typically 31 label, for example, with the hybrid. So
yeah, we ran with the Navy hybrid coordinate system in the target values, which is 40-ish layers, and we got really good results, but it doesn't have great resolution in the deep ocean. So like for climate simulations, was not ideal. We didn't run for that long, but we did.
I guess maybe my point is for like a more fair comparison, you may want to have a Z star with like more level than your hybrid.
Yeah, that's a good point. Yeah, we can try that, or we can do the other way around. We can have a hybrid with less layers than this star, which we already have it.
All right, Stephen.
Gustavo, thanks. That was great. Very revealing. I want to go back to the heat uptake question because I was intrigued by what appears to be the MOM6 with the hybrid vertical coordinate cools in a way that you mentioned is similar to POP, which uses a Z coordinate, whereas the MOM6 with the Z star warms. Yeah, so are you is a cart, you know, from this picture it looks like MOM6 with hybrid looks like POP with Z. Does that lend one to think that the MOM6 Z star coordinate is problematic in some way, or you know, like a lot of spurious mixing, if you interpret that as a spurious mixing signal, or do you think of it as something else?
If I can jump in, this is Frank.
Okay.
The lateral closures are completely different between this POP case and the MOM6 cases. So
Okay.
I don't think we can assign it to anything about the discretization at this point.
Okay. So you think that you might be able to change the lateral closures in the MOM6 to look, the Z star to look like? Is that something you're going to bother doing, or are you just fully invested in the hybrid now?
Well, we're still exploring it, but you know, obviously there's a lot of activity on lateral closures right now, and I'm not strongly motivated to go back.
Yeah.
I'd rather move forward, but
okay, thanks.
Thank you again, Gustavo. We'll now move to our last speaker of the morning, Baylor Fox Kemper. Switching gears a bit, Baylor will be talking about AR6, The Reckoning. Go ahead, Baylor.
There we go. Unmuted now. So I guess the point I wanted to make here is there's a lot of stuff that I can't talk about, which is all the stuff that everybody would like to know, which is what big updates are. But I thought that at this moment, rather than waiting till next year, or maybe the summer meeting when the results would get in the way, I think there were some lessons learned about things that were particularly difficult in pulling this assessment together that were useful from a perspective of this audience. So I just wanted to ping a few of those pieces out there and let people know a bit about how that process went, and then have some questions. I don't think this will probably take the whole time. Oops. So first of all, let me say thanks to the many of you who've written papers that were contributing to this effort and that were pulled in, or who reviewed drafts of the AR6. It's really critical, and all of that effort really improved the end product, or will improve it when it comes. For a scope of what the challenge is, you know, these are some early classic climate change papers that you might have in mind. We go back to the mid 1800s. The Charney report, which I hope lots of you have read, only had 19 references in it. And there was no ocean or cryosphere in any of the models that were used, although they did helpfully point it out as a key uncertainty. So if you plot the number of references and the number of pages that are on these reports going back to the 1850s, you see that there's a sudden and very alarming increase. Or maybe more to the point, if you just pay attention to the ocean, cryosphere, and sea level references, also a highly alarming increase. And I will just tell you that we have not broken from that cycle. We're pulling in at about 1,900 references in the chapter on ocean, cryosphere, and sea level change. So that would fit to this extreme pull. So that's a scope of the kind of number of things that we were thinking about.
Looks like the hockey stick.
Looks like a different kind of hockey stick. Well, here's a nice comparison that Reno Nudi put it together. That is actually the hockey stick versus the hockey stick, which shows that CO2 emissions and temperature is rising despite the number of publications. You could almost associate a causal relation between those things. The more publications, the more the CO2 goes up. But anyway, that is a, you know, maybe a meaningful thing to think about when you think about what the point of all this is. But I will tell you, it's too late now. If you've got a hot idea that you just came up with today, we're done taking new papers for this round. The acceptance deadline was the end of last month. So if you have an already accepted paper that you think we should be considering, please do contact us. You can send an email to me, or at previous meetings, I actually gave a more formal email, but you can just send it to me if there's something you think we might have missed. And so when I got into this process, I thought that we were going to be able to write elegant things like this lovely 1912 newspaper article that pretty much tells the whole story in one paragraph, which I'll leave up here for a second so people can take a kind of shocking result of how many of the details are right in this little blurb. But I was thinking that we would have more process detail, more regional specificity, new processes that we know from the kind of OMWG style work or LIWG style work contributes to the end result. And this is just a picture from a recent paper that is a collaboration between lots of us in the audience, led by Ching Li. And, you know, here's an obscure metric which makes sense in the context of that paper, and, you know, lots of detail and lots of different parameterizations all side by side for some kind of quantitative estimate. But in practice, the new structure of the IPCC was to have 4 global chapters that give you the kind of headline topics you're used to. What have we observed? Can it be assessed that it depends on humans? What do we project? And then a bunch of chapters that were focusing on that process level, of which the ocean, cryosphere, sea level chapter is one, and then regional downscaling for projections and observations, both in Atlas and chapters on regional processes. So enthusiastic to bring forward the process discussion into the IPCC. And what I realized was over time, the focus of the work kind of goes like this, where any cool process idea that comes up in the literature gets gobbled up by the regional chapters or the global chapters where it has the biggest impact. And it is very difficult to discuss processes at a level of detail that we would like to really reflect the literature of the process studies that support it. So that may just be a structural problem with the way the IPCC is set up, but trust me, that's what I've been thinking about for 3 years. So what can we do if we were going to try and elevate the level of process in this kind of an assessment? Some of the things are pretty simple, like using the DEC simulations or the IPCC scenarios as test cases rather than something that is similar but slightly different when we go out to test land models and ocean models and parameterization sensitivity effects. And the reason why is you really want the diagnostics to be applicable across studies to have a sense of how much of an impact it makes within that language. I know that's not always possible, but it really would have, it is really helpful to elevate papers into the assessment that have taken on those standard scenarios. Develop and share diagnostics so that lots of different studies can be talking a common language and you can get a handle on how important or how different the processes are in the same diagnostic framework rather than having to recalculate the diagnostics. I'll give a couple of specific examples of that in a second. And then, of course, using ensembles and multi-model ensembles so that we're not really, I mean, we all know that's helpful because it hammers down the internal variability. And so in the end, what we'd like to do is address the consequences in the essential climate variables that are the focus of a report like this. So 2 really nice examples of taking that diagnostic challenge seriously with a lot of authors in the audience, I'm sure. Are the OMEP contribution to CMIP6, where the OMEP diagnostics were laid out, and then the sea level concepts and terminology paper. This is critically important work because it gets everybody talking the same language. It really helps when it's in advance by a few years, so that everybody's already talking the same language, has those diagnostics coded, and you get the metrics right, and you get them clear, and you get them consistent across papers, and that enormously helps. I won't tell you the blind spots that we had in some of these papers, but we certainly should probably revisit what we did and learn some things and think about some of the things that were incredibly hard to calculate after the fact that we probably should have seen coming. But so this is an example from the Gregory paper showing the different ways that you might discuss sea level change. These are all of these words appear and get used in different ways by different communities, and particularly when we think about the synthesis between the prediction systems for sea level that involve things like waves and inundation and storm surge, together with the folks who are doing the land modeling, together with the hydrological modeling, together with the ice sheet modeling, together with the ocean modeling, to do something like this where we can translate among the different standards and make sure that we're comparing things and adding them up correctly is really, really valuable. So I talked a few Ocean Model Working Group meetings a long time ago about developing a diagnostics package to make this system work in CESM, especially when we're running both the land ice and the ocean model together, so we can do sea level as an easy output. I think we should reprioritize that. My experience with the IPCC is that that really would have been very helpful to have had that capability. And the last piece I'll say is the MIPS are really valuable because they are building these consistencies and those kind of things, but they come or at least in this schedule, they came very late in the game because many of the MIPS waited for the completion of the original scenarios to 2100 before they even started, or they built upon them. And so what that meant is that the analysis of those MIPS is either just published last week or not yet published. And so rather difficult to pull into the assessment process. For the essential variables, the kind of coupled runs, that's fine. But when we talk about the ocean and cryosphere impacts, and particularly sea level, which takes a lot of post-processing after the MIPS are done, that is a significant challenge. Here we go. What would it have been great to have? Would have been great to have lots of runs beyond 2100. When 2100 was the cutoff 40 years ago when the IPCC process started, it seemed far away. It's not that far away anymore. We probably should be going to 2150. It would have been lovely to have more coupled ice sheet AOGCM runs. So I'm glad to hear about that in this meeting. That would have really strengthened the connections across those pieces. More on the impacts of ocean cryosphere interactions and how that impacts these essential climate variables. All of that is great work and really will make the next round of assessment, whatever that looks like, a much more solid piece of work. And similarly, parameterizations, numerics, resolution impacts to be done the way that we like to do it from a process level, but also to think about whether we can get those impacts back into branch runs that allow us to translate into the large scale essential climate variables would be really helpful. There's some details about the dates, but I'm happy to take any questions.
Thank you very much, Baylor. Any questions for Baylor?
Yeah, Baylor, I have a comment on what you're saying. I think you're trying to search, what did we learn now and we could make things better, but you did show some nice examples of the review kind of papers you were using. And what do you see the role of those, the actual assessment reports themselves, and the authors of the assessment reports getting involved after the fact, say the MIP papers, the big review papers? How can we, so that we can build in an orderly way, and timing wise, there seems to be maybe more of a role for different kinds of papers, especially that don't need AR kind of review, which you're about to get into what those reviews look like when they come, right? So what's your thinking on that?
We've already had over 10,000 review comments.
Exactly my point.
Yeah, I know what the reviews look like. Yeah, that's a mess.
But those review papers
are really important. Those papers are really important. And so, a few examples like the ice sheet MIP, the ISMIP process, and the OMIP process allowed the community to get together with many more authors, dozens of oceanographers or dozens of ice sheet modelers, and really kind of hash out what's going on, so that the handful of ocean modelers or ice sheet modelers who are on the chapter had a much broader perspective about what was going on. And I think that's really valuable. But in order to do that effectively, we have to be careful about the design of those kind of MIPS so that they aren't waiting for the scenario runs or the latest version of each of the coupled models to come first, because that part really limited how effective those pieces would be. And some of the observational products, which are less tied to the MIP schedule, the ones that are really helpful are ones that were produced a couple of years ago, and then they have had lots of other follow-on papers and refinements done to draw on. I mean, a lot of the questions you have come up, and it takes years and more people to comment on before it gets to the assessment report to be ready to include. So I think that kind of multi-institution project on both observational products or on modeling kind of advances is really valuable. So I hope we do some of those in the next few years rather than waiting closer to the deadline for whatever the next assessment looks like.
So one more question from Bob Hallberg, and then we'll go on to general discussion. Bob?
Thanks, Beller. That was a very nice, if discrete overview of some of the things that are going on. I had a little bit of a slightly instructive experience by working on the special report on the oceans and cryosphere, which is out and which I therefore can talk about a little bit more. One of the things that we realized in writing something that deliberately spanned the working groups is that there are some quantities that are very predictable from physical models that are so predictable that they're very boring for us, but are critical for people kind of in the downstream reports. Specifically, the one that really came up for us was changing upper ocean density stratification, because that's the big driver of a lot of the changes in the supply of nutrients to marine ecosystems and fish and stuff. Is it worthwhile after this process kind of going back and looking at which are the metrics that we should perhaps be writing about a little bit, because they're useful downstream, even if they are scientifically boring for us?
Yeah, I think that's exactly kind of what I'm proposing. Is I think we should revisit the OMWG variables very soon, while this is still fresh in our mind, and while we are thinking about how to link up between the coupled cryosphere ocean models. And so we have some new variables we'd like to do. It would be very nice to have those pieces while they are fresh in our minds and run them by some working group 2 people, run them by some cryosphere people, run them by some sea level people, and make sure that we've done that a little better. The sea level one is maybe the easiest one to think about. We probably should have been saving out thermosteric, steric, stereodynamic, all these pieces of the puzzle that are obvious in the model when we have them, but they're not part of the CMIP archive because we don't think they're that interesting to do most of the time. But having them all in a multi-model comparison easy rather than having to recalculate them from scratch would have been really valuable. New science too, I think Laura at least was in the audience before, ocean heat uptake science has really taken a surge which is related to the stratification question. And a lot of diagnostics of ocean heat uptake that could have been more directly comparable to Argo data, for example, would have been really helpful to have had calculated in multi-model way. So I think that diagnostics paper really is waiting to be done in the near term. And maybe the OMWG or something like the CLIVAR OMDP or something like that is a good place to start having those conversations. But I agree, it's definitely needed.
We're in our general discussion time, but we're getting good questions. So let's just go ahead with Stephen, and then after that, Zyler.
Yeah, thanks, Baylor. And one comment in regards to variables that we want to save, diagnostics we want to save, having sat through numerous CLIVAR and WCRP meetings and getting feedback from the atmospheric people who always say the ocean people want to have too many variables and too much archive stuff saved. We as a community, you know, and I know we're doing our best in the Calaveras Ocean Working Group, we need to be writing the papers that use these diagnostics and showing the science value of those diagnostics. And I'm not saying you're not, I'm just emphasizing that to this group. There are lots of variables and diagnostics that are being saved, even with the incomplete archiving of the CMIP6 ocean fields, that I know that there's a handful of very interesting science papers that can be written. So I just encourage the community to pick that up, because we can keep asking for more and more, but these are all, you know, they have a carbon footprint. These archives have a carbon footprint. So we need to show their value scientifically in order to keep saving more and more data.
Yeah, totally agree. Thanks, Steve.
Zyler, did you have a question?
More of a comment. So it's interesting because it's almost the opposite of what Steve just said, in the sense that talking with colleagues very recently, one of the things for Antarctic research that seems to be missing is basically the ocean bottom temperature and salinity, which are pretty important in feeding into ice shelf cavities and are not directly part of the output and have to be sort of figured out from the full 3D data set. But because bathymetry is represented fairly differently in these models, it's not always interpolated well onto the reference meshes. So that's one of the worst quantities to try to recover in terms of Antarctic ice shelf research. So it would be really nice basically to add another field, the bottom temperature and salinity, that seem to be missing for our community.
Well, Zyler, I think the point that Steve was making is exactly that, is if it's scientifically valuable, we should be making that list. I think that is, it's easy to argue that that's extremely scientifically valuable, but we just didn't think about it the last time around. So I think the assessment of what's scientifically valuable is a broad community. We should have a broad community input, and we should really think about how to do that and boil that list down as best as we can. But if we can't get to as few variables as the atmospheric people would like, then maybe we have to think about other community solutions, like other data archives where the extra variables are saved or something like that. Go ahead, Steve. I think you have a follow-up.
Zylar, SOB and TOB are requested in the Griffiths et al. 2016 paper. That's the salinity at the bottom of the ocean and temperature at the bottom of the ocean.
Okay.
If you don't see them in the archive, it's because the people didn't save it. So okay. I think that there are a lot of fields that are requested in the Griffiths et al. Paper that are just not saved because it's a lot of work for some groups to save these fields. But if we show the science value of them by writing papers and keep saying what you're saying to groups like this, eventually we'll get those fields saved out.
Yeah, that makes a lot of sense. And I mean, having put together the fields for E3SM, it's hard to remember what you did and didn't do sometimes. So I can imagine that's true for any groups. And I'm sure it matters much more for some models than others. Basically, ours is an unstructured model, and that's where it got especially tricky to go to the regular grid. And so I could imagine that might be true for other models that have very different grids than the sort of standard comparison grid.
Laura, you've had your hand up. Would you like to ask a question or comment?
Sure. So I kind of a bit forgot. It was a while back when Baylor actually kind of mentioned my name about heat content. I think, and Steve follow up on that as well, which I think as a community, we also need to realize what we can and cannot do, right? There are a lot of variables out there. And so there's a bit of a decision we need to make, and doing it again, hand in hand as modelers with observationalists, so we can actually have, comparisons that are useful for the community. It's something we need to think about, early on. We all do it our own way, and it gets tricky. But when we compared, for example, heat and carbon uptake and all these kind of metrics, we're doing it our own way, but it might not necessarily be useful for the readers or the audience of the IPCC, while it might be useful scientifically. So I think they are, at the end of the day, two audiences to some extent, and there are two steps towards that. And so that definitely requires some thinking and being proactive again before the report is due.
Yeah, and I think to follow up on Bill's point from before, one thing that those review papers can do in advance is help you translate among those different diagnostics. So even if the different model studies are all using different diagnostics, if there's a table or an approximate functional relationship between them that says, to within good approximation, this is equal to that, then you don't have to use the same diagnostics. But we don't do that science, that kind of integrative science always or consistently. I think that would be really helpful to have. I mean, it would be helpful from this perspective that I'm speaking in right now.
Gökhan.
Yeah, just to expand upon what Steve said and Zyler's comment, OMWG document, and it's a pretty comprehensive document led by Steve, and it includes many, many variables that are not necessarily adopted by the modeling centers. I mean, at the end, you're at the mercy of the people who are actually running the experiments and their storage restrictions and all that stuff. But regarding the bottom, for example, temperature and salinity, some groups did not provide them because they're already available in their three-dimensional TNS fields. And I guess how readily available a field should be, that depends upon, I guess, storage limitations and duplication of the field. So that's another thing that we need to consider. They are all readily available, likely. It's just a matter of for the user to drive them or use the model bottom topography to extract that. But maybe that extra step is not being done by the user.
Just quickly on
And
that.
Gökhan, I think the other question is whether Pangeo style, if we're making just those fields available, but then there's code that we know that will accurately do the other diagnostics from it. Yes, we don't have to calculate a whole long 100 diagnostics of all the 2D fields that are interesting and complex integrals of the temperature and salinity field. But in the absence of that, having to do that or having to figure out how to do that and having to do that in different models with different discretizations is a mess. And so you end up making approximations you would not like to do because you can't access the original version and correctly manage the 48 different discretizations.
I mean, a prime example is the overturning circulation, right?
Right.
Some groups provided, some groups did not. They just provided the velocities, but the velocities are not usable by themselves either because of the distortion of the grid, especially at high polar latitudes. You can't get the true northward transport. So that's another thing that, I mean, despite our requests, some groups did not do that.
It's not the worst thing in the world, though, if you have different numbers of models for different diagnostics. What is the bigger problem is if the diagnostic doesn't exist at all. If you have 0 groups or only one paper that has one model's version of that diagnostic, then that makes it a very limited use. If you have 6 groups, not 40 groups, that's actually not so bad. It's fairly easy to frame the conversation around this is a limited sample size, but we have no reason to expect that these models are anomalous.
Stephen.
Yeah, just as an example of that, if you recall the talk yesterday by Jan-Erik Tesdale about water mass transformation, if you're interested in the role of salinity, like with sea ice and the brine rejection, unfortunately, as far as we can tell, nobody provided the salt flux in CMIP6 from their climate models. So even GFTL. So I was very disappointed that we didn't do that. And so we can't look at water mass transformation from salts exchange. So yeah, these are 2D fields. So we all as a community need to just be watchful and watching that.
And I do think that there's room for a non-CMAP repository where we would say, oh, we have a bunch of other variables that we think are oceanographers variables, and then we have a much longer list, and we are not fighting the battle in Clivar. It's not a large amount of data storage. We could slap them all up on a web page somewhere with just a 10 terabyte drive if we're talking about all the 2D fields we would love to have. That's to build a separate system for our own purposes might not be crazy.
Yeah, that's a good idea.
Bob, one more question before we wrap up.
Yeah. So one of the things this conversation really drives home, for me, the metrics that we would often use as scientists are much more precise but not always calculable. But there are often proxies that are not so bad that are readily available just from kind of the boring limited set of fields, right? So the example of summertime stratification, which might be something you really care about for nutrient supply, may not be something that you can get directly, but you could probably do a pretty good job of looking at annual mean, just three-dimensional profiles. If somebody would just write the papers about whether one is a proxy for another, then that becomes citable and usable for people like Baylor writing about what its consequences are. So I think maybe there's kind of a whole subset of papers about easily derived proxies without new diagnostics using single models, or maybe just one or two models, not the whole community, that then allow us to get at these more subtle things that we'd all like to look at as scientists, while at the same time addressing the questions that the end users downstream are maybe interested in, without having to mobilize and persuade all the herds of cats to do the same thing.
Yeah. No,
well, I think this gets onto the idea of this. We seem to be missing a broader array of these kind of papers that are more, and only to our own reviewers, and not. And that, of course, are the projects that create these data sets we've just been talking about, right? The 2D data sets, maintain, describe them. So there seems to be room for that kind of thing somewhere, that you don't have to take everything to the AR, which has its own set of rules and timing, and as I see Baylor nodding. So that seems to be encapsulating quite a bit of what I've heard.
Yeah, and I think, if these community papers, like the Griffey's et al. Paper, is a really big step in that direction. I think we should be thinking of that as the group work that we do together when we get together at these meetings. Is think, are these kind of comparisons or diagnostic things that are really missing from our community that we should be getting together to advocate, that our community is sure that these are scientifically important, and we think we can write them down. We think we can clean up all the definitions. That would be a really valuable kind of review paper, which isn't the kind of review paper we normally write, which is like, what's the cutting edge of ocean model development? And then it's kind of hand wavy and it's great and people love to cite it that don't want to know the details. We're missing a kind of review paper of the details side.
They're great for young people because you get a lot of citations.
Yeah.
I mean, it's okay.
I think we made the point, Bill. Thank you very much, everybody.
Yeah, I think we're going to draw things together, draw things to a close now. So I want to say thank you for a very interesting and diverse set of talks from all our speakers. Also, thanks to the 80 or so people who have joined the call. Terrific turnout. And from communities who, at least in the CESM context, have not often gotten together in one place to hear each other. The talks from Gustavo and Bill Sachs and others show us that we're on the verge of doing some extremely interesting coupled science, which few, if any, researchers in the world have been able to do. I don't know where things are going to go from here, but I hope we'll have more sessions like this. And if anyone heard something today and you have an idea about the kind of research project you'd like to do, about people you'd like to collaborate with, about anything you thought was missing that we should perhaps think more about, please join the conversation, let us know, and we can follow up future Zoom calls or future meetings. And if anyone would like to just hang out and talk about these things for a few minutes afterward, or simply visit, I plan to stay online for a few more minutes. But everyone else, of course, is welcome to move on with your day or your evening. So again, thanks very much to everybody for joining, and I will see many of you at the Land Ice session tomorrow, and of course the ocean meeting will continue. So thanks again.
On the same Zoom link for the ocean meeting? Yeah, okay, thanks.
Tomorrow for the Land Ice, we have a different link tomorrow than this one we had today. So just to be aware of that.
Elizabeth just wrote something in the chat to remind everybody that the YouTube stream would remain open today. So,
all right.
And the ocean meeting this afternoon will use the link you used this morning.
So we'll see how many people decide to stay a few more minutes.
So can we start talking yet?
Yes, absolutely.
Okay, Gunter, it has to do with this, the idealized experiment you showed.
Yes.
Okay, which has been shown elsewhere. Now, it looks to me that it is absolutely symmetric across in Y. And I'm curious to why you did that. I mean, you shouldn't, what, you know, depending on Y at 40, I think 40 kilometers, it's the topography is identical. I think is it a wind thing or what sets the asymmetry? Does something break the symmetry across in the Y direction? Because you have this absolutely parabolic, nicely shaped trough, no difference one side or other. I'm just curious, what breaks the symmetry in that configuration?
So why do you want to break the symmetry? I guess I'm not fully understanding.
Well, because then you can get more information from one model run.
Oh, so well, this
I mean, or the wind might, or is it the forcing or something?
Okay, so there's no wind in this experiment because this was a standalone experiment, and this was a test case that was used in previous intercomparison project, and because some analysis had already been done on that exact, framework, it was easy just to reuse to just look at a very simple parameterization experiment. So I'm not saying like this. What I didn't say is that this experiment is like fully inclusive of every single possible scenarios, but it's a start.
Yeah.
And the main reason for using this framework is because there's a paper written in 2018 that used that exact framework, and with the same melt, with applying the same melt, and it led to very different results. And so this is why we just redid the experiment to compare results to that paper. And what is interesting, and so this result was this other paper was from CERC and 2018, and they use ISSM, the JPL model. And when we do intercomparison project, like idealized cases like this, CESM and ISSM typically, fall in the same ballpark of prediction, but not in this case. So that, yeah. I hope that answers somewhat of your question.
Yeah. Oh, it's just curious. It looks like there won't be much difference one side of the center from the other.
No, especially since the melt, is just follows the bottom topography of the shelf.
Yep.
But I agree. We need to test it in more like an idealized setting, and we'll work on it. Baby steps.
Bob.
So if I could change to something completely different, one of the things I'm really proud of with MOM6 is we've done a good job of pulling together the oceanographic community towards something resembling a community model that is as open as possible, as available as possible. Is there an analog on the ice sheet side? Is the field kind of mature enough to kind of have that kind of open community modeling? Is it already happening?
I would say there's 5 or 6 ice sheet models that are considered among the top ice sheet models. And the communities who develop those models are rightly proud of their models and want to see them used by a lot of people. And we're not yet at the point of having, say, the equivalent. We don't have the equivalent of, let's say, MOM6 and NEMO, which are now used by almost everyone. And I don't see how we go from 5 or 6 ice sheet models to a couple of models without how do you choose? I think we're just going to see in the next few years which groups kind of push along to the next level and improve the physics, and models that are able to do things that other models can't do will then be used more.
Are all of these open development, or some of them proprietary? I mean, I think that was really one of the big breakthroughs, was the realization that open development and transparency was really the gateway for a lot of the good things that followed.
Generally, yes. I was just thinking, when I was at Landell a few years ago, I remember a conversation where someone said, you know, MOM6 is a community model now and anybody can use it. And at that time, DOE was much less open with its models. And I think that got people thinking. At that time, I was arguing that our ice sheet models should be open source. And then, of course, there were differences of opinion, but now CESM and the DOE ice sheet model are open source, and ISSM and PISM and Elmer Ice, I believe, are all open source. As far as you know, Gunter, or let's see, Zeiler's still here? No. As far as you know, Gunter, all these models are open source now on the ice sheet side?
I believe so. And if they're not open source, it's you know, by now we know the main developers of these models, and as far as I know, none of them would be against you using their models. So,
and it's a pretty close community, friendly community. People publish ideas, share ideas. There's a lot of fertilization of each other's models by different things we do.
What we don't know is, like, you can what I believe it's true, you can use their model as much as you want, whether, you know, how much you're willing to support you in your effort. That's, you know, it depends on their time, of course. But
well, I think for us, one of the breakthroughs, so earlier versions of MOM were open source going back 30 years, 40 years. I guess 1989 or 90, about then was when MOM 1 came out, and that was when we just put out a tarball and said, have at it. But for a long time, if you wanted to make changes and have them come back, the process was kind of painful. Going from open source to open development. So right now, if Baylor, for instance, had a student with an idea who wanted to make a change, we've tried to make it as easy for that student to do that as it is for somebody sitting at GFDL. And so, you know, open development, we've seen the number of people contributing go up really dramatically. And this cuts in a couple of different ways. One of them is you don't have the trusted expert taking care of making sure that they believe in everything that goes in. On the other hand, a lot of good ideas don't come from those trusted experts. And so there's a balance there that gets tricky. Are any of them open development?
Well, CESM is nominally open development. We use, we're on a Git repo like all the other components of CESM, but in practice, we haven't built a large community of developers in the way that MOM has. In practice, it's mostly Gunter and me. Heiko Gelser, who was on the call today, is quite a skilled developer, and he's planning to add some things. But I think most of these models have still been developed by a fairly small group of people. And again, I'll ask Gunter, are you aware of any models that have more than a handful of people who are committing code regularly?
No.
So I mean, our ice sheet model is called a community ice sheet model, and community is sort of the brand, but it's not truly a community developed model yet, and we would like to get there. And if you have experiences to share to help us get there, we're very much open to hearing that.
Yeah, I mean, we would be very happy to do that. I think one of the things that really we found overdoing it on the testing, and a lot of it is kind of simple self-consistency testing and things like that anybody can do anywhere, and it's either right or wrong. Because I don't want to get into the business of debugging. Again, I'm going to take up Baylor's hypothetical graduate student's contribution. Instead, I want Baylor's graduate student to know how to do the tests to figure out when they put in something that's dimensionally inconsistent, or if you have the ice sheet flowing this way instead of that way, one of them blows up and the other one is hunky-dory, both of which are real things that we've seen with student contributions. So the testing that we've got is really valuable. It's also one of the things that I think has really helped us going back and forth, for instance, between GFDL developing stuff and NCAR developing stuff and people at EMC developing stuff. We all have our own particular configurations and we all make sure we're happy with them. But having this kind of basic set of tests that everything has to pass, we've actually found that detects most of the kind of the obvious bugs. And if you take care of the obvious bugs, then the things that are left are things that are worth paying attention to. And so it really has helped us out a lot. Now, we spend a lot of our time rerunning these little tests. And in an ocean model, you have some waves that bounce around for about half a day, and that's usually enough to detect any of these kind of obvious things. I'm not sure that you can do the same thing with an ice sheet on very long timescales, but there may be parts of it that would translate usefully.
Well, there's a lot of useful tests. We do have a testing framework and a test suite for the standalone ice sheet model, and similar tests for CESM run in a couples setting. Our standalone test suite is getting long in the tooth, and it doesn't currently test as many things as we'd like it to. So one of the things Gunter and I want to work on in the next few months is expanding that suite and bringing it up to standard so that anyone can do just what you say. Run, let's say a suite of 10 tests you can do in 10 minutes for when you're just kind of moving along and doing some debugging, and a more sophisticated suite that might run overnight before you let's say bring in a pull request. But that is something that's on our list, and I agree that we need to do better with that before we can take on developments from more people.
Yeah. So the good news is that there are now a number of people at NCAR, Gustavo in particular, who really get this, and so if and when you're back in the same building again at some point at any point in the future, you have local expertise that you can draw on. Otherwise, I mean, we're happy to talk about it, and anything that we found that useful that you would like to hear more about, we're more than happy to talk about it. And Gustavo, are you going to give that thumbs up to being the local resident expert who gets it?
Yeah, I'll say I have Bob's number. I'll call you because I know you don't answer emails, so I'll call you.
Yeah, Bob, one thing I recall though is when you started your open development, you didn't start with everybody. You started and learned a lot with the Australians, I think.
Yeah.
I mean, you did sort of build it, so maybe you could comment on whether that's not a bad idea. Get a couple people going rather than everybody until you learn what you're doing. So I don't know what you feel about that, but could you have opened it completely up to start? I'm not so sure.
That's a good question. The people we opened it up to at first, you're right. They were a bit selected. There were folks in Australia. There were folks at NCAR. We had former postdocs scattered around the world who had students who could kind of act as a buffer, right? So like Malta Jansen at Chicago. Well, one of the people contributing a bit earlier in the process was Hailu, who we heard from yesterday, but he had Malta there, and Malta had been at GFDL. So it helps that you had enough people that kind of knew their way around a little bit. And we made mistakes. we made a lot of mistakes where things slipped in, and every time something slipped in, we figured out how we could have prevented it. It also helped that Alistair and I had been kind of bouncing things back and forth for a few years and had come up with a way without talking to each other to evaluate what the other one was doing. And we have, I mean, one of the policies we have is that no person ever accepts their own pull request, ever. And for a long time, that was mostly me or Alistair, although you know, Steve made some contributions and others as well. And so you sort of by definition, you need to have a few people who kind of get the system. Now that's expanded, and I think we have probably a dozen or so people who kind of understand how the system works. And we have 5 different, these kind of main forks that are all doing their development simultaneously for different purposes. And we kind of trust that anything that's come in from one of those, a user contributing via one of those 5 forks, it's gone through enough testing that it's almost always going to work. It's just, you always do your tests because we do different runs than NCAR. We deliberately are choosing different physics packages to use, right? I mean, and the reason for that is because the world doesn't need one climate model to estimate the PDF of what will happen. We need different ones. And so there are things that can happen, but it's always gone through this kind of vetting. And so the number of times that we found we had to push back on something that had come in from NCAR has been pretty small, pleasingly small. And so it's this kind of two different, the realistic tests you care about, and then the quick consistency tests that we all can do. And they're not even physically sensible in some cases. It's just create a case where the gravity waves bounce around in some crazy adjustment process, and that's good enough. But you're right, Bill. We did have to kind of ramp it up a bit, but I think a lot of what we learned in ramping it up could save a lot of time for other people trying to do it without quite that same ramp up.
Are there any other things people would like to discuss today? Bob, do you all have any interest in participating in MESOMIP 2?
Well, I think we have the tools that might be useful. It's just that the very good postdoc we had, who kind of was getting us sped up to speed with the original MESOMIP, had talents that were recognized by NCAR and got snapped up. So it's not for lack of caring, it's lack of having the right person to be willing to take it seriously and do it right.
Well, given that we have someone just as you described, would you have any interest in being part of a larger effort that includes both of us?
Yes, I think we'd like to look at that. Yeah. So I'm speaking for myself, and I need to get buy-in from some of the other folks in the group, but I think there's certainly interest in joining in something. I don't know that we would be. So we at GFDL, I suspect, like you at NCAR, are still kind of suffering a bit of the exhaustion from processing all of the data and everything from all the MIPS we were involved with, and just it's been a lot. And taking on something new is in terms of working up the data sets and regridding them to the same grid. And I'm not sure if there's an appetite to take on something new like that at the moment, but.
Well, I hear you. At this point, things are, it seems like the protocols haven't really settled yet. And I'm not sure what exactly we're going to do, but when I hear people talk about running spin up your global model in some sort of steady pre-industrial steady state with your ice sheet model, and then let things go forward, and then around 1990, the system should be in a state that matches observations. I don't know how we do that. And we certainly need to think about how we get the global model to talk to our nested model or our parameterization or whatever we have for ice shelves. And I mean, I don't even know where we run MOM6 in cavities and have that be the cavity circulation, and where we have something else to do things under cavities. And anyway, there's a lot of big questions that it might just be nice to brainstorm, which doesn't require all the more time intensive data processing you're talking about.
So we do have a global eighth of a degree model where our plans are very much to put in ice shelf cavities and carry it through with a kind of a series of different approximations to the ice sheet and the ice shelves. I don't know that the timelines are going to match up with what would be needed to have it there in time for the initial write-up of MESOMIP2. But definitely this is something we'd like to pay attention to and see what we can do, but I can't promise anything on
oh, sure,
be available to do it by when.
Well, let's just keep in touch.
We'll keep in
Gustavo has your phone
Yeah,
number.
I know how to find Bob, and yeah, I don't want to make any promise, but there's a bi-weekly meeting on regional MOM6 that Charlie is leading, and Bob and others are always there. And I've been working on a Pan-Antarctic simulation on my weekends. I've managed to run ocean only with the ice shelf enable. Bob made a lot of changes to the ice shelf code, so did Matt Harrison. It's working well. I need to now couple to the CIs, everything via CSM. I think it's going to take a little while, but maybe over the 2-3 months, we'll have something. It's a 1/4 degree resolution, which is not ideal, but to start with, I think it's good enough.
One question for us. I mean, we've been talking now for years about coupling with a a full ice sheet model. It doesn't strike me that the world needs yet another ice sheet model if there are 5 or 6 and they're all open-ish. Any recommendations on what GFDL might want to do for fully dynamically interactive ice sheets?
Work with us.
CESM is a good.
CESM is most likely the best.
Okay, so let's see. I was missing some words in the middle, and all I got was CESM is the best.
I'm somewhat biased, but yeah, work with us.
Okay.
If I could offer some argument or rationalization, it would be that more so than most ice sheet model developments, we've been thinking about coupling for a long time. That's been part of the philosophy from the beginning of what we want this model to be able to do.
Okay.
And just to go back to one of your questions, I've been checking all of the ice sheet models that typically participate in intercomparison models, and from what I can see, they're all open source.
Open source, but open development.
So, sometimes the way I think about open development is that you can even you can fetch a model and develop it on your own, and then say, "Hey, look at what I did with your model," and then you go see the developers and say, like, "Oh, that's great," and then they integrate it. But
yeah,
there is a great deal of work that goes into spinning up an ice sheet model with a given forcing data set. Most people use forcing data sets, and then spinning up with, let's say, output from a climate model is something that's different and generally harder than that. And that is something we're already working on and will continue to work on. So to the extent that it's helpful for you to have an ice sheet model that already plays well with MOM6, then I think that makes sense.
Okay.
So anything you would add there, Gustavo? Is Gustavo still here?
Sorry, I was checking the grill. I'm making lunch. What was the question? Can you repeat, please?
Just talking about when people spin up their ice sheet models, they typically have a forcing data set like surface mass balance from RACMO and so on. And people generally have not used output from Earth system models as part of ice sheet spin up. But that's something that we're now, I guess, enabled to do and starting to do more seriously. And I was just thinking that if the GFDL folks are looking for an ice sheet model that plays well with MOM6, then CESM obviously will be a model that already not only is technically compatible with MOM6, but has parameterizations and tuning that are appropriate to forcing with MOM6.
Nothing to add.
And that's using the new OPSI coupler mostly, the one that we heard Bill talking about?
Not yet.
It will be using the new OPSI coupler.
Okay.
For now, we've done just offline coupling.
Okay.
Well, we have a couple of MOM6 and CESM with MCT too.
Right. Yeah. Right.
But yeah, I believe that there's work underway right now, I think by Mariana Bertenstein to bring that over to new OPSI.
So yeah, so we're still using an older coupler from GFDL, although there are other people in NOAA using new OPSI coupler as their operational. EMC is 100% in on new OPSI. We're just a little bit of a throwback, in part because we're still kind of exploring how to do the coupling and this in a way that kind of blurs some of the boundaries between components. For the sea ice in the ocean, the blurring is really obvious. For the ice sheet and the ocean, the timescales are different enough that it's not so obvious that you need to kind of blur the boundaries. So like sea ice, if you take a bucket of water and you toss some ice in and you slosh it back and forth, you get gravity waves, and you can't say whether those gravity waves are the ice moving back and forth or the water moving back and forth. But so maybe the ice sheets are easier in that sense, in that you have dynamic modes that are clearly a part of the ice sheets or clearly part of the oceans, and maybe, although I guess ice sheets move up and down with tides. So what I just said is a complete lie.
Not entirely, because we haven't, on the ice sheet side, we haven't done anything with tides yet.
Okay.
So the scales we've been looking at have been, month to year to decadal scales of motion. So as far as that goes, there would be a clear separation.
Okay. I mean, what we had been planning to do was actually couple the ice sheet every 2 hours, just because that way you're just using the same couple time step, and it might be incredibly inefficient because that means you're taking a 2-hour time step for a component where the fundamental time scales are really long, but you just figure this, okay, you do a few iterations, nothing changes much, maybe.
Well, our typical ice sheet time step is maybe a couple of weeks or a month. And as you go to higher, the ice sheet model is really cheap compared to the rest of the model. But if you went to a high resolution ice sheet and started taking time steps every couple hours, it might actually start to get expensive. So I mean, Gustavo has given this some thought. We want to couple things on the small spatial scales of the ice sheet model, but the small time scales of the ocean model. And I think, Gustavo, what you'd like to do is compute melt rates often, but do some time integration and just pass them to the ice sheet model on the time step of the ice sheet.
No, so what we did is we compute the melt rates within the ocean coupling time step, so forcing time step. But as you said, ideally we want to compute the melt rates in the high resolution of the two, which most of the time is the ice sheet model. So I think ideally we want to do that in the couple level. So the couple can do every ocean time step, because you need to force the ocean with that meltwater and accumulate that and send it to the ice sheet model every ice sheet time step.
Yeah, so that makes a lot of sense. On the sea ice side of things, we actually have our sea ice model split up into kind of 3 different phases. There's a fast thermodynamics, and that's mostly responding to the atmosphere. A slow thermodynamics that's melting, and then a dynamics. And the dynamics might actually be faster than the slow thermodynamics. The slow thermodynamics is the melting, the ridging, the transport. The dynamics might actually get to involve internal gravity or external gravity waves in the coupled ice ocean system. And so maybe that's a way to think about, and then all 3 of these kind of different aspects of the sea ice have to be made to be reconciled with one another.
I think that's analogous for ice sheets. For ice sheets, we put our fast thermodynamics, which would be our snowfall and surface melting in the land model, coupled to the atmosphere.
Okay.
And then so the ice sheet model only handles what you might call the slow thermodynamics, the slow basal melting, and then surface mass balance applied on say an annual time scale.
Okay. Makes a lot of sense. So thanks. This has been a really useful conversation. I don't want to monopolize our time. I know that other people have stuck around, and I hope we're not overly monopolizing. I take pretty seriously the commitment that when we signed on, that senior people in especially should not be monopolizing the conversations, that we should make sure there's plenty of space for everybody to participate. So, great. So at the risk of monopolizing the conversation, what do you do with icebergs?
We nothing sophisticated. The ice sheet model has a calving flux in each ice sheet grid cell, and we deliver a solid flux of ice to the ocean. And the ocean, I always forget who does what. Bill Sachs, the solid flux that goes into the ocean, is that heat taken out of the surface or out of some vertical profile of ocean depth? And is it spread? And is the freshwater spread over some radius, or is it mostly local?
The ice is spread over a radius. I'm not sure what the ocean model does with that in terms of the vertical profile. There have been hooks in place for sending ice calving to the sea ice model. We have not enabled that because up until now the sea ice model has not had an iceberg parameterization. I was under the impression that CES6 maybe there was something that was at one point being developed in there, and at that point we could route it that way. But I'm not sure. I don't know, Bill or others, if you know whether that's come to fruition.
I don't know the current status of that, but I guess the simple answer is we don't do anything sophisticated. We don't advect icebergs in the frozen state. We just deliver the ice to the ocean, have the ocean deal with the heat and the fresh water in a sensible way that won't make things blow up.
Yeah, so my understanding is that there's a frozen runoff, right? And then there is a mapping file that controls the area over which that will be spreaded. And then I don't know if the frozen runoff gets propagated the same way as the liquid runoff for rivers with the EBN parameterization
It-
POP.
It does not.
It does not. So then it does it. It then is at the surface. It gets injected at the surface, and the ocean will melt that ice, and there's the latent heat that the ocean will lose heat for melting that ice, and then advect as fresh water. Well, in the case of POP, it would be virtual salt.
Okay, so that's one area where so we've had this Lagrangian iceberg model for a while, and one of the things we're trying to move towards is keeping the information about not just the mass flux of ice, but also things related to the thickness of the ice and the area of the ice, the icebergs. Because the lifetime of the icebergs, once they're out in the ocean, it really matters quite dramatically whether you're looking at big icebergs or whether they become small icebergs, just because the wave erosion around the edges is such an important mass loss term. And then the thickness, of course, helps to determine where they go, where they melt, what temperatures they're experiencing. If there's a lot of times you have kind of a cold surface halocline, but then warmer water below, if they're penetrating down into that warmer water, they can be melting even though the surface water is essentially at freezing and they're in a pack of ice. And we're also looking at, well, somebody mentioned the iron fluxes, I think, yesterday. I can't remember who it was. It was a really nice talk. Oh no, it was Dan Goldberg today. Right, so thinking about other things that icebergs do in the Earth system. So that may be something where a kind of a conversation at some point could be helpful.
Well, I think Bill had the point. I think the idea was that eventually that could be just a big thick ice category in the ice model. And therefore it'd have all the thermodynamics of ice and things and snow on it and whatever and what have you. I think that was the plan. It would go in CESM as a very thick ice category that would then advect around and be blown around, et cetera, et cetera. I don't know where that is though. Do you, Bill?
I don't know where that is. I don't think Bill
Or Bill Saxton,
I don't know either. Yeah, neither.
But that
Bill
was
knows.
that was the design when let's keep it simple now, because that would be the ultimate way to go.
Yeah, so we've looked at that. In CIS2, we only have one velocity for sea ice. And when we looked at this, one of the challenges is that icebergs, because they're experiencing different currents and they have big sails and
that's right,
directions that they go are not the same as sea ice. So you
and but I think the other idea was that wasn't our biggest problem.
Okay.
I mean, and that's why it's nice to have these co-developments, because somebody takes on something that other people say, oh, we're not ready for that, but then they can show it's important or not. And that's part of the advantages, I think.
Absolutely, divide and conquer.
So Bob, you do icebergs in MOM6 or in CIS2?
There's a separate iceberg component
a whole different
to the sea ice.
And
so the thing is that the sea ice plus iceberg occupy space. So you can't have more sea ice than the icebergs allow. And then the icebergs kind of move. And Gustavo can tell you a lot about this. He was involved with some of that with Alon Stern when he was at GFDL. But what we have been doing for a while is having these Lagrangian point icebergs, which don't occupy space, don't change the albedo and other things, but they do hopefully transport fresh water away from the continent before they melt, which can have a pretty big impact on bottom water formation. And this is a result from Torger Martin and Alistair Adcroft going back more than 10 years now. But there's a kind of a newer Lagrangian iceberg model where you keep track of these icebergs as Lagrangian objects. And this is the work that Alon Stern was doing, and Gustavo was involved with this a bit, and Alistair. And then the way that you would handle icebergs that get bigger than your grid cell is, instead of having kind of isolated objects, they become a lattice of connected objects, Lagrangian objects. that drift around, occupy space, can have snow and albedo and other things. And so this is something that we think is important enough to work on. I agree with Bill that between the various institutions putting a lot of effort into this, making sure that somebody is covering everything is more important than everybody covering everything. And so that may be something where at some point, so Alistair, I think, has a postdoc who's actively working on this. I'm not sure what the recent status is on that particular project, but it may be important, especially if we start thinking about wave-driven flexing of ice shelves and things like that, that if you have grounded icebergs out in front, they can act to break up waves. Olga had a paper a few years ago about tsunamis triggering calving events. But if you had a big grounded iceberg, and that's the other thing is these Lagrangian objects, they can become deep enough and big enough that they can ground and stick in place for as long as, well, I suppose they're always melting and they're always being kind of eroded. They don't ground forever, but they, kind of, you hear stories about icebergs the size of states that break off and then they ground, and they, all sorts of fun stuff that probably plays a non-trivial role in the Antarctic environment.
Bob, I have a question.
Yes.
So what happens to tides then? And also, not just waves, right? And the other thing is, how do you treat currents when you have these as Lagrangianly, advected as if it's a Lagrangian particle?
Well, that's why we're embedding the ice into the ocean. If they're small enough, they are mass, they participate in gravity waves. When it comes to tides, you're absolutely right that having these grounded objects should affect the tides. If you're explicitly modeling the tides, we resolve the timescales of the tides, we resolve the astronomical forcing of the tides. We're working with some folks who are working on better ways to deal with the self-attraction and loading parts of the tides. So instead of projecting it into, and this is, Brian Arbick is the right person to talk to about the details on that side. But also Hee-Wong is now working with Brian and with Eric and Alan. And so explicitly modeling the tides is something that the Navy has been doing with HICOM for a while now. They use it mostly for internal tides. And so we have active work trying to make sure that we're able to model the internal tides explicitly in MOM6 if you turn them on. The challenge is if you turn on the internal tides, then you get the fields that you get back, the flow fields have tides. And so what you have to do is detide them exactly the way you would with an observational data set. And it's really annoying. It's a lot of work. And so it's a little bit of a challenge to say whether you want to try to include the tides explicitly because that's maybe the best way to do it, or whether you want to try to parameterize the tides effects just so you don't have to take them back out again when you're trying to answer questions with the model output.
Yeah, that is a good point that you have to detide them, but as I understand, that is just one of the main reasons why you would have to detide them is to do model data intercomparison. However, if the altimeter retrieval has the tidal contribution, you can pick and choose. You can say, well, I do want the tidal contribution, and here is that version of the product, and of course the regular version which has the tides taken out. So I'm actually a couple of months ago I had this chat, and Richard Ray, who is our local Goddard tidal expert, yeah, he suggested that we talk to Brian and his he and team, and so yeah, that's what we were wondering, whether we could actually turn on the tides and see what happens, because Richard can actually come up with a version, not of course his own, not from a VISO, which has the tides in them.
Yeah. So the big challenge there is if you're not doing data assimilation, but you turn on the astronomical forcing and the self-attraction and loading, you will get tides. They'll look pretty reasonable. You can tune up maybe some drag parameters so that you get about the right overall amplitudes, but the phases are never going to be quite perfect. And so I think a naive comparison with direct astronomical observations in a non-assimilative model, probably you're going to find, even if you have about the right amplitudes, that there's slight differences in the patterns of the amphidromes and the phases. And so I think it's a tricky thing to do. Now, if you're doing the data assimilation, you can make it work, but then that's something that's kind of dominating that signal. You're challenging.
Yeah, I mean, the internal tide can be the biggest heat content signal in the ocean, right? And it's huge. So you've got an 80, and it's adiabatic mostly. So then you have to put it in, then you have to take it out. And if you don't quite get it right, you leak a little bit of a big number. So yeah, but somebody should look at this. Don't get me wrong, but maybe not everybody.
Well,
but it's a huge signal.
Yeah,
can be.
It can be enormous, and you can't always, because the internal tides are really tricky because they're not monochromatic in the way the external tides are. If you change the stratification, Sonic analysis doesn't let you just pull it out. And so there are a lot of people who've looked at sea surface height signals, and it's very tricky to differentiate strong non-coherent internal tides from eddies.
Yeah, and it can also be pretty close to the Coriolis frequency too, at certain latitudes, and that gets to be a mess. And so, yeah.
And similar spatial scales.
Yeah.
So this is a real challenge. I think for those of us on the climate side, where it's the heat budget that we care about first and foremost, probably we're going to err on not putting the tides in explicitly, but trying to parameterize them. Just as you say, you don't want to alias the tides into your climate change signals. But for some questions, doing the tides is exactly the right thing to do. And in fact,
yep.
So for a lot of consequences, changes in the tides, coastal consequences, might be one of the biggest signals of climate change. If you have an estuary, the flushing of that estuary depends on the tides. If you live next to the coast, mean sea level may be less important than high tide, high spring tide sea level. And so,
well, you start changing the resonance of the Bay of Fundy, and you can flood Boston.
Well, in the Bohai Sea, coastal development on the Chinese side has changed the tidal patterns on the American side.
Correct.
And all sorts of interesting questions.
Well, I got to go.
Or even Annapolis, for that matter, right in our backyard. So a similar thing along with all these things would be what you were telling me, Bob, was the pressure loading to sea ice. Do those have any impacts on the way you guys have been dealing with icebergs?
Well, when we first put in the icebergs, we were putting in their pressure effects, and we found that they were surfing on their own echo lagged by a time step at the speed of a jet plane. It's an external gravity wave mode.
Yes, yeah.
You have a little well, and the iceberg is not right in the right position in the well. Sometimes these propagate in just the right way that they can catch the wave. And so that was the thing that just sold us that at some point we're going to have to deal with this ice ocean gravity wave instability and do it right. And we're not quite there yet, but and so for now, the icebergs are still kind of levitating, and it gives us all sorts of heartache. And it sort of works, it sort of transports things, but that's yeah, it's a big deal. And if you calve off the front of an ice shelf, right, you take it, and your ice shelf, the whole point of the ice shelf is it's displacing ocean.
Mhm.
Otherwise, why bother? If you calve it off and you say, okay, let's take the 100 kilometers at the tip of this iceberg, 100 by, a Rhode Island sized iceberg, the one that will make the news, and you say instantaneously it stops displacing water and starts to levitate, then you have a 500 meter deep Rhode Island sized hole that makes really wicked tsunamis. There are all sorts of tricky things that, right.
Yeah.
I'm going to sign off now, Bob. I'm going to go get
Bill,
some lunch.
it was great talking to you. Thank you very much.
Yeah.
I think this joint session was a lot of fun.
Hope we can do it again sometime. So thanks everybody.
It's 1 o'clock. I think I'll give it just a couple minutes for folks to show up. It looks like our participation numbers creeping up a little bit. Okay, why don't we get going? We have 20 minutes scheduled for discussion, and it's fairly open-ended, but I thought there were a couple of things we could follow up on from this morning's session. And then I'd also like to bring up some issues of the only real resource the working group has as an entity is computing. So I thought I'd bring you up to date on where we are on that. And then we have, let's see, 5 talks starting in about 20 minutes, 19 minutes now. So we do this one of two ways. I guess I noticed that there were a couple of questions to Gustavo in this morning's session that didn't get called on. So I wanted to give those folks, if they're back, an opportunity. And I'm not saying Steve Yeager or Justin. Justin, you had a question for Gustavo.
Yeah, I'm here. So if Gustavo's there, I just had a question about the mixed layer depth, because I've been looking at that in Southern Ocean, and what I noticed was the huge difference between I think the Z-star and the hybrid coordinate levels. And I wondered if that was a known feature of using the different vertical coordinates, or if anyone's looked at that before, or is it just something about the way the vertical levels are defined that you get such large values with, I think it was with the hybrid case.
Yeah, I got your email. I was actually looking at the OM4 paper. They do not provide a comparison for the mixed layer depth between the Z-star and the HICOM. I don't know if any of the authors.
Alistair and Bob are both on, I think. So if either one of them wants to chip in here.
Yeah, it's Alistair here. I was actually thinking the same thing. Think there is a change primarily because of the effective vertical resolution near the base of the mixed layer, but we didn't see very much of a change because the EPBL scheme that Brandon and Michael and Bob Horberg built kind of put a lot of effort into trying to make sure it wasn't resolution dependent. So it could just be a matter of the resolution in the critical regions being different in the different coordinate systems. And there was a suggestion during the discussion a question of Gustavo about maybe using comparing with many more levels so that the resolution is more comparable.
Right.
And maybe if you designed your Z coordinate to have the same resolution in different places, you might be able to figure out what's happening. Because we've also wondered, and I think it was Go kind of suggested this in the summer, whether the physics responds to the parameterizations are changing on different grids, and maybe that's the cause of the change in heat uptake. And there's something we haven't yet figured out.
Right.
I'll add that our first attempt at using the hybrid coordinate used the OM4 density list, but with our physics, and that was a complete disaster. The big problem area was the Western Pacific warm pool, where you have relatively deep, light mixed layers. And there were not enough Z-star layers to fill up that mixed layer. So we were getting, 100-meter deep or 100-meter thick layers near the base of the mixed layer, and the whole thing fell apart.
Right.
Our 75-layer list is not the same as HICOM 1. So we sort of moved some resolution in density space out of the deep ocean up into the mixed layer.
Right.
So we have a somewhat deeper Z-star layer there. And we found that we were doing some mixing and matching that, we sort of swapped in OM for vertical physics and our lateral physics and back and forth. And it really was the combination of EPBL and the parameters the difference in the parameters you guys were using in FFH versus what we've been using. So that your vertical physics seemed to be more stratifying in the upper ocean and keeping a somewhat shallower mixed layer than what our physics wanted to do. So that's sort of where we wound up with our layers. And we've tried a very small number of options here so far. So there's still a lot of exploration on our part, at least, to figure out what works best and most economically.
So what physically happens when you go to the isopycnal layers in the deep that improves the simulations?
Well, it's hard. Yeah, I'll let these guys have looked at it a lot more than I have, so I'll let them fill
Is
that
it
in.
the fact that there's less spurious mixing because you're along isopycnal coordinates?
That's one thing, the representation of the overflows, although we've talked about it in a not terribly satisfactory context. The representation of the overflows in a density-like coordinate is much more forgiving. So right. We have the kind of the overflow parameterization that Gökhan and others, folks at NCAR, have been using in POP for about 10 or so years. That I remember when they kind of first brought this in with the CPT back in about 10 years ago, it had a pretty big impact with the Z coordinate. With the density coordinate, because your coordinate surfaces are kind of flowing down, you get less of that. We're struggling, I think, from the talk yesterday with trying to understand. There's a bit more mixing there than we think is proper with the kind of the newer variants of the hybrid coordinate. But the other thing we're doing in the abyss, and I think Alan noted this, we're not running with pure isopycnal coordinate. We put in a little bit of compressibility deliberately, so it's a little bit stratified. And going back to the original question about what's going on with the mixed layer depth in the southern ocean, if it's the southern side of the southern ocean, there's this very delicate halicline, but it makes a big difference in how deeply you can mix. And if you do anything that erodes that halicline, it's actually unstable in sigma 2. It's stable in sigma 0. And it's just that delicate, but it's enough to make a difference. And if in one case is eroding it or not, then that can have just big consequences that carry on forward in terms of the mixed layer depth. I haven't looked obviously at the details of what is differing between the two cases Gustavo showed, but when we were trying to use a more nearly isopycnal coordinate before the one that we finally settled on, we found that eroding that high southern ocean halicline was giving us big biases, and we tried a handful of different things quickly before just saying, okay, let's keep it in Z space. We don't care about sigma 2 in that context. We don't. But there are aspects of this that are tricky.
Right. So there's better representation of the overflows, then produce better TNSs in the deep ocean. That's 3 to 5 kilometers.
Yeah, so that's part of it, and then part of it is also the reduced mixing that you noted.
Yeah.
So that the total heat uptake, I don't think we've shown it in the last day or so, but we have these plots that we'd like to do of heat uptake over time as a function of depth, which is a very broad metric, but that one just shows a really dramatic difference between the two different vertical coordinates with identical physical parameterizations. And that, I think, is published in Alistair's 2019 paper.
Okay. Nice.
Yeah, I think it looks like Gustavo might be looking for those plots from ours, but we do see a different depth dependence of the evolution of the bias in hybrid versus E-star, and not just in the Southern Ocean, but even up in the Pacific, you see it quite different. we're running through our time. I wanted to, Steve Yeager, you also had a question left over from the morning session that didn't get called on. Did you have something you wanted to bring up? After Gustavo's talk, I saw you had your hand up. I see he's on. Maybe he's not at his machine. Okay. There we go. Yeah.
Yes.
Yeah. So these two are the Z stars. This is POP. This is hybrid with 75. You can see reduced significantly. And this is hybrid with 85, which reduced even further. One question that I have is going back to Eric's talk yesterday, and he mentioned the fact that MOM is targeting the interfaces while HICOM is targeting the layer, and that could be some kind of a spurious mixing happening in MOM. That kind of goes against what we just talked about of having reduced mixing in the hybrid coordinate system.
Why is that? Why wouldn't it just mean that you might get even less mixing if you go to the HICOM approach? Did I miss something?
No, but yeah, so it's like just a level of spurious mixing. Like then you seems like with Z star we have way more, and then between MOM6 with HICOM 1 or HICOM 1 or HICOM, MOM6 with HICOM 1 has more than HICOM but less than MOM6 with Z star.
Yeah.
Bob, maybe you can clarify. Eric was talking about interface versus layer remapping, right?
Right. So in the way that HICOM works, if you're in the density space, you say, I want the average property of a layer to match a target. And we did that for a long time with gold, with one of the predecessors of MOM6. And in that case, we found we had very low levels of mixing, consistent with what Eric was describing with HICOM. One of the things that we did when we went to MOM6 is you define pressures as the pressures at interfaces and other things. And so when you're hybridizing based on the same definition, it makes for a very graceful mathematical description of what you're doing. And so what we're doing now in ALE mode with MOM6 is you try to match the value of the density at interface from a profile. But if you have gravity waves that are kind of causing stretching and dilation, even though they're perfectly adiabatic, where you find the position of that interface can evolve just due to the kind of the dilation of parts of the water column. And so what Eric is speculating is that those sorts of motions might be causing us to do more remapping than we might do if we had only done remapping to reflect the diabatic changes in the properties. And that's where, by filtering out, by doing it more slowly, as Eric was doing in some of his experiments, you can reduce how aggressively you're chasing those interfaces. And so there's some really good ideas. In terms of the numerics, we can do anything you want. I mean, it just say, come up with some rule for where the interfaces are going to be, and then it can remap to that. And so the real limitation here is just creatively trying to figure out what is the right definition for where you want the interfaces to be. And maybe it's something that becomes kind of a hybrid between tracking the interfaces on longer time scales, but keeping this kind of adiabatic nature of not chasing things on shorter time scales. And this is something where if there are any students out there looking for an interesting project to play around with, this could very well be one.
I think we have about 5 minutes left. Let me just share this. Let's see. I can't tell what you guys are seeing right now.
In your page.
You're seeing a PowerPoint?
Yes.
Okay. Does it look full screen now?
Yep.
Yeah, so let me just quickly, between the summer meeting and now, we've gotten a new allocation, 2-year allocation on this NCAR computing systems. This year we have 20 million core hours. That's split about evenly between development and production, and all of our development is dedicated to MOM6. So we have about 10 million hours of time to explore things and continue to tune and develop our MOM6 models this year. The new system has been mentioned is being installed late in this calendar year. And as I understand it, will be made available to the full community in springish 22. And we'll have a somewhat larger allocation on that system, but that system also is, now I'm forgetting the number, something like 20% of the nodes are GPU based. So, you know, not all of that new system will be available to CPU codes. Another opportunity that will be coming up at the end of this year is whenever NCAR buys a new machine, they have kind of an early user period where they allocate the entire system to maybe 4 or 5 projects for about a 3-month period as kind of friendly users to help them shake out the system with high capacity jobs. So there is an opportunity for us as a community and working group, if we have an application that would fit well in that opportunity, to propose something together. And over the last couple of days, for example, I've been talking with folks, and the kind of thing that Scott Bachman described in the seminar yesterday with the machine learning tools developed by this, so our new system will be an HPE Cray-based system. And that's what Scott and his collaborators, Gustavo and the HP guys, have built this online machine learning system, which in fact requires the GPUs. So that could potentially be an excellent basis, technical basis for a proposal for this ASD period. And those are typically 20, 30 million hour allocations. So it's sort of the same amount of time we would get in an entire year in a couple month period. So that's on the horizon. So we should be thinking about that. And, you know, maybe by June, I would expect that there will be some kind of a call for proposals this summer. So we should be thinking about that, and you know, maybe by the June workshop, kind of be pulling together a plan for what we might propose, if people want to do that. The other thing I thought we could just spend the little bit of time we have left. Gustavo had it on one of his slides, sort of what our near-term plan was, but that is malleable to a certain extent. You know, we have this, we have a small human resource and a large computing resource to use over the next 6 months. Our default plan at the moment, you know, we're exploring these hybrid coordinates. We've got a couple cases now which we're fairly comfortable with as a basis to then sort of branch out and start exploring some other things, but we certainly still want to pursue those. As Bob said, it's a wide open problem here. On our kind of default plan was the next thing we were going to start doing with our MOM6 implementation is bringing the waves in. We have not yet coupled to the wave model. Then, you know, there's all sorts of other things we've talked about in previous working group meetings. So I'd like to just open the floor up to any thoughts people have on what our priorities should be in, say, the next 3 to 6 months. Steve, go ahead.
For the wave work, Brandon Reichel at GFTL has done a lot of work on that. You probably are aware, but just to let you know that a lot of the work is, you know, is with MOM6, so you can build from that. But he's worked
yeah. And we have a fair bit of experience. And in fact, there's some, I think a talk tomorrow from King Lee that, we've been using WaveWatch. We have WaveWatch 3 coupled into the CESM, and it interfaces with KPP through the Langmuir parameterization. So we at least want to get back to that point. But then a lot of the work Bill Large has been doing over the last year and a half also builds beyond that.
So one thing to note about that is that WaveWatch is only just after Brandon did some work in the last few months global. You couldn't have an Arctic with WaveWatch, an ice-free Arctic. So there's a WaveWatch version that needs to be brought in if you're going to do like ice-free summer studies in the Arctic with waves.
Okay. Thanks for that input. I don't know, King Lee, do you want to come? Do you have any input on that point? Are you there?
Yes. So I think there's I don't know whether we want to get a new version of the WaveWatch. I know the new version can do the Arctic ice free, but yeah, I guess the first step is we want to get the Langmuir turbulence already in POP, that version into MOM6. That's my understanding. Is that right?
Well, that's certainly a starting point. And I know as part of this computing proposal, there was, unfortunately, Baylor's not on the call right now. Part of this proposal was actually a fairly big chunk of time for Baylor and CC Bits to work on ice wave coupling, I think with the very latest versions of WaveWatch. So there's kind of a couple of different threads going here. Okay. So anyway, I think we're pushing up to the time we should be starting our talks, but if anyone has input on these sorts of issues, certainly feel free to email Ian or I with your thoughts, and at any time about what's going on with this, the development, and if people would like to have more frequent sort of rendezvous about where things stand with our MOM6 solutions, then sort of the twice a year CESM workshop schedule, we can certainly talk about doing something like that. So let me stop sharing. Did anyone else have any sort of open discussion, general questions they wanted to bring up right now?
Yeah, Frank, I think somewhere in the next, the ASD runs have to be shovel ready.
That's right.
So you need to have, and if you're thinking along the lines that Scott had, for example, one of the big things is haven't really figured out how to use a high resolution model to do any parameterizations because it didn't look like just degrading the input variables worked very well. And he was asking for thoughts on that. So that might be something to really work with that working group and figure out how to really do that in general. And we heard other things about Antarctic things about how to use high resolution and learn out how to parameterize. Well, they didn't seem to know how to do it yet because the eddies affected the mean. And so they weren't able to just degrade. At least that's my impression from yesterday. So that could be a very high priority if you're thinking about getting ready for shovel ready by the fall. All that stuff has to be in order before you put an ASD proposal together, because that has to go.
Yeah, I understand. I think Scott can chime in, but I think what I took away from the talk was that the machine learning based parameterization was effective if you had some sort of a seed of the eddies in an eddy permitting case.
Correct.
It was not successful if you had no eddies whatsoever. So a proposal for, just to throw things out there, that a proposal for ASD might be doing something like an eddy permitting fully coupled run.
Well, I would say it did better, but it didn't do that well either.
Well, we haven't.
If
really
you
looked
look at
it,
I think he'd agree. There needs to be some more work done on that.
Okay.
How do you do that whole problem?
Well, we have another day and a half of talks on eddy parameterization, so
Yeah, we'll see.
Plenty to hear about. I think we should get going with the talks, and Ian is gonna run the show from this point out, I think.
All right, thanks, Frank. So we're going to start with Takaya Ukita. I am going to try and give everyone 25 minutes. That's 25 including questions. If I have to give you a 2-minute warning, it means we're 2 minutes away from 25. But I will try, even though we're starting a little bit off schedule, I'm going to try to give everyone the full 25. So why don't you go ahead and take it away, Takaya.
All right, thanks. So can people hear me and see the screen?
Yes.
Okay, cool. So it's 9 p.m. here in France where I am, so it's a bit late to talk about eddy parameterizations, but I hope this will like get some interest. So I titled my talk as Towards a Potential Vorticity-Based Mesoscale Closure Scheme. This is my postdoc work that I've been doing with collaborators listed here. And yeah, I'll just start. So I'm sure the audience here doesn't need reminding this, but the ocean interior is stratified and quasi-adiabatic, so much so that we infer the global ocean circulation from tracer distribution along isopycnals. So yeah, what I'm showing here is just like the Atlantic transect of the potential temperature on the top, where you can see like more or less the stratification of warm water at the top and cold, dense water at the bottom. And then I show the salinity transect, and from this, we can infer like the mid and bottom waters of basically the overturning circulation. So what the other side of the coin is, it's essential to get the isopycnal placement correctly in global ocean simulations for estimating global heat and tracer transport. And I'll dive into this a little bit later, but the thickness weighted average framework provides us with a path forward. So before going into that, I'm just going to give a very brief conceptual overview of like the most common mesoscale closure schemes that are used. So I'm sure everyone in the audience also knows this, but it's the Jet-McWilliams and Reddy parameterizations. So conceptually, what these two parameterizations do is that, for example, you have the isopycnal on the left, and you can kind of imagine like the hump being due to a mesoscale eddy. And then the red squiggly arrows, I intend to just describe the eddy enhanced stirring of tracers within an isopycnal layer. And what Jet-McWilliams tries to do is it tries to mimic the part of the baroclinic instability cycle of the loss of available potential, like the adiabatic loss of potential energy, which I show schematically on the right, where like basically the isopycnal hump is like spread out through the isopycnal layer. And again, the red squiggly arrows are the Reddy tracer diffusion. So it's my personal belief that although GM and Reddy have historically been developed separately, it's my personal belief that they should be related to one another. And also the GM captures only part of the baroclinic instability cycle. So the question arises whether we can capture the full eddy feedback and not just the release of available potential energy. And the question arises because we know that the eddy momentum feedback energizes the mean flow. And there's a lot of studies out there that show this, but here I'm just showing a study from Alui et al. 2018. And basically the blue colors show eddies fluxing momentum back into the Gulf Stream region. So mesoscale eddies, the takeaway is mesoscale eddies energize the Gulf Stream. And the question becomes, can we say more on how and where? And if you were here yesterday, there was an exciting talk using machine learning by Scott Bachman. But here, we're going to try to push this question a little bit further in the framework of old school GFD. So that's where the thickness weighted average framework comes in. Unfortunately, we don't have the time here to go through the derivation of this. So the equations, you're just going to have to trust my word for it. But the point here is that once you, well, if it's in a geopotential coordinate model, you first remap all the variables onto isopycnal coordinate into isopycnal coordinate system. You thickness weight it with the thickness of the isopycnal, and then take the ensemble mean. And you get the hat variables, which are on the left. And so these are like more or less the mean thickness weighted average variables. And on the right is basically the eddy terms, and the X and Y are the forcing and viscous terms, all of them together. So the key here is that in the theory, this thickness weighted averaging is based on an ensemble mean, because it allows for the cleanest way to commute like derivative operations with the commuting derivative operators with the averaging operator. The rest, if you forget about the hats and bars, another point is that it looks very close to like the regular Navier-Stokes equation that we are very familiar with. And if you want to know more, there's a great paper by Young, 2012. And if you want a more recent paper that implements this thickness weighted average framework, I'd recommend a paper by Ringler et al. 2017. So we want to do this thickness, well, I'm going to say it as TWA from now. So we want to do this TWA framework using realistic simulations, and that's what we attempted here. So we have 24 ensemble members. We have a 24-member ensemble of the North Atlantic Ocean, which will run for 50 years. The spatial resolution is 1/12, so it's mesoscale permitting. The model is MIT DCM, basin is North Atlantic, and the surface boundary condition is partially air-sea coupled, and the laterally boundary conditions will relax toward a climatology. And on the top figure, I just show basically the time series, the domain averaged time series of potential temperature in red and kinetic energy in black. And the thin squiggly lines are like each ensemble member, and the thick dark lines are the ensemble mean. So just starting off with the mean field of what this ensemble looks like. On the top left panel, I show the ensemble mean mixed layer depth on January 3rd, 2008. And on the right, I show, this is all on just a snapshot on January 3rd, but on the right, I just choose a random isopycnal layer. I show the ensemble mean depth of it, basically. So what you see here is that, well, the subtropical gyre has darker blue, meaning it's deeper, and there's this drastic shoaling across the meridional transect where the Gulf Stream situates. And you can see also the Gulf Stream signature in the mean kinetic energy field, which I show on the bottom left. So you see the yellow line extending off the US East Coast. And just to avoid confusion, we configured the domain so that it wraps around zonally. So like Europe is like on the left upper top. It was configured this way to save computation and memory allocation. So we want to use this ensemble toolset to look at the eddy feedback onto the mean flow. And like I said briefly earlier, basically all the eddy terms are encapsulated in at least in palm flux divergence term, which I highlight in this red box on the equation at the top. So in the context of eddy closure schemes, it shifts the focus from the buoyancy equation, which GM is formulated on, to the momentum equations. And phrasing it another way, if we can parameterize this, at least in palm flux divergence term, we have a physically consistent eddy closure scheme, which represents the eddy buoyancy and momentum fluxes, basically the energy backscattering part as well. So the question becomes, can we actually do this? So in the TWA framework, another nice thing about it is that the Eliason-Pond flux divergence is directly related to the eddy Ertel PV flux, which are right here. And so this vector F with pi as a superscript is what I use to write the eddy Ertel PV flux. And this primes us to connect basically the Eliason-Pond flux divergence to the large scale Ertel PV. Meaning if we can parameterize the eddy Ertel PV flux, that means we have equivalently parameterized the Eliason-Pond flux divergence. So that was long, but I hope it was clear. So the method we attempted is we relate the eddy Ertel PV flux to local gradient flux of the mean Ertel PV via an anisotropic eddy diffusivity tensor, which I show on the bottom. So basically on the left-hand side, the tensor includes all the eddy fluxes. So the eddy flux of horizontal eddy flux of temperature, salinity, and the PV. And on the right-hand side, you have the local gradient flux of the mean temperature, salinity, PV, dot producted with this eddy diffusivity tensor. And what's nice about this framework is that, well, I write it in color, but for the Ertel PV part in blue, it captures the GM and eddy momentum fluxes. But for the temperature and salinity part, it brings together the ready part. So basically what this allows us to do is it brings together ready and GM in addition to the eddy momentum flux with a single tensor K. And so, yeah, the $1 million question is, does this actually work? So this is just we're using the same isopycnal layer on January 3rd, 2008, the date that I showed the mean fields. And on the top two panels, I showed the diagnosed actual eddy PV flux, which is F pi 1, F pi 2, well, left is zonal, right is meridional. And then the middle panel, I showed the reconstruction of these based on the mean PV field and eddy diffusivity tensor. And well, I would say it works remarkably well. It's, unless you squint, it's pretty hard to tell the difference. So, well, I would like to emphasize that at this point, these the diffusivities that I use here are diagnostic variables. So just to summarize, well, the Eliason-Pond flux divergence, which is directly related to the eddy PV flux, encapsulates the net eddy feedback onto the mean flow. The eddy PV flux can be related to the thickness weighted average field as an active tracer, meaning that we treat PV statistically in the same way as temperature and salinity. And the 2x2 diffusivity tensor K, which provides a pathway forward for closure scheme for eddy PV fluxes, single-handedly includes the information of eddy momentum fluxes in addition to bringing the GM and eddy diffusivities together. And future work for prognostic closure scheme, we would need to inform the kappas in tensor K via the thickness weighted average fields. So that's what I have. Thank you.
Thanks, Takai. Very interesting talk. We have plenty of time for questions, so I will monitor the chat window and the raised hands. All right, Hailu Kong has a question in the chat, so I'm going to just read that out. Do you have a map of diagnosed kappa?
Yeah. So that's the kappas on the top 4 panels. It's quite noisy, partly, and this comes from partly well, we would expect the diagnosed kappas to be smoother if we had more ensemble members. But I also argue that not all of it is noise based on like the spatial scale features that we get by calculating the inner angle of the eddy flux and reconstructed flux, which I show on the lower 3 panels, which is the phi terms. So these are like showing the inner angles between the eddy flux and the local gradient flux of the mean field. They more or less have like the same order of spatial scales. So I think there's some physical signals in the kappas that we've diagnosed.
All right, Steve had his hand up. Steve Griffiths.
Takaya, thanks. As you know, I'm familiar with this work. It's nice to see it's moving forward. I'm not clear from the presentation, and are you presenting here a theory for eddy parameterization, or are you presenting a framework for diagnosing eddy terms, eddy processes?
Right. Well, in order,
all you've shown, it seems to me, is diagnostics. You haven't given me how you would actually close the system.
Right. Well, I would say it's the first step towards a closure scheme based on PV. I mean, I think the first step is to be able to actually reconstruct the eddy PV flux from the mean PV field. So, well, what we've shown here is that you can do that. So, yeah, I would like to work more on, well, trying to inform the diffusivities in a prognostic manner.
Mm-hmm. Okay, thanks. And so, I'm sorry, just to follow up, if you show the map of the diffusivity again, is your closure going to, I know you haven't done it yet, but that seems like a fairly detailed field to be predicting from a closure scheme. Is that, though, what you're, if you can give me a theory for how you get the diffusivity in this map, that's your closure, or is there something more than that? And also the negative values for the diffusivity. Should I be worried about that?
Well, the negative values translate to part of the negative signals translate to upscale PV fluxes, which translates to basically energy backscattering. So if you want energy backscattering in this PV framework, you do want negative diffusivities.
Okay.
So that's one. In terms of like the spatial scales, well, in terms of actually trying to formulate a prognostic variable, you would probably want to further spatially smooth the kappas that I've diagnosed here. Yeah, that's a good question. I don't really have a good hunch at this moment.
Yeah. Okay, thanks.
I believe Gökhan is next.
Yeah, it's along the lines of what Steve was pointing at. In addition to the negative values, these amplitudes, or the magnitudes rather, seem to be roughly an order of magnitude larger than we are used to. Either yesterday we saw examples of from machine learning or what we use in the models. How do you reconcile that order of magnitude difference in these diagnosed diffusivities?
Well, I guess if we're going to compare to the diffusivities that we had yesterday, those are based on like I guess, eddy buoyancy flux. And also it doesn't consider any of basically the isopycnic tracer eddy fluxes. If you look at eddy diffusivities that have been diagnosed for tracers, basically specifically just the ready part, the eddy diffusivities can be, some papers showed eddy diffusivities even a magnitude order larger. So it is within the realm of the range of eddy diffusivities that have been shown in the past.
Thank you.
I don't see any other hands raised, but I had a question. So a lot of the talks from later in this session and tomorrow are using spatial filters to do eddy diagnostics. And to me, that seems natural. The thing that I'm trying to parameterize is something that's unresolved. There's a lot of problems with spatial filters, commuting derivatives, and not being a Reynolds average. You've instead opted to use an ensemble average, which has all the nice properties you would want, commuting with derivatives and being a Reynolds average. But at the same time, it's a bit conceptually different. It's a difference between something that's subgrid scale and something that's sort of eddy variability in an ensemble. Can you just comment on that difference?
Right, I guess, well, I'm sure there's a lot of ways to answer this, but one argument that I have to justify the usage of using ensemble is, at least for diagnosing the diffusivities, you want to be as close to theory as possible. Whether or not you can directly connect this to a prognostic scheme. And also, I'm sure people in the audience are much more knowledgeable about GM than I am, but I think the theory of GM itself is also based on ensemble means. But when GM is implemented in models, well, that is not what is actually done. So if in the future, if I do come up with a prognostic scheme for this like ensemble mean thickness weighted framework, I would like to test it for like a single realization of the ocean and see how that would work.
Thanks. I see that Peter Gent has his hand up.
So have you tried this in a domain that includes the equator? Because when you try to do things with potential vorticity, it's spanning the equator that is normally the difficulty and the problem.
That is a good point. As I show in the figure, I've only like diagnosed it north of 20. North. I mean, I do have a figure of the EP flux divergence terms over the whole domain, which does cover the Atlantic Ocean. Surprisingly, compared to the Gulf Stream, it doesn't really show up that much. Well, maybe it's not surprising. It just means that for the equator, most of the kinetic energy is in the mean field and not the eddies. But so I guess based on this figure, I would be surprised if like the equator all of a sudden popped out just for TV. Did I answer a question? Well, the answer is for diagnosing the diffusivity that I did not do for the equator region.
Right. Well, I think we're done for questions here. So maybe we'll move on to Jessica Kenigson is next. And we'll be getting a little bit closer to the original schedule.
Hi, everybody. Are you able to see my screen?
Yes.
Great. So, hello, I'm Jessica Kenigson. I'm going to be discussing with you a stochastic parameterization that we've been implementing and testing in a coarse resolution setup of MOM6 to reduce uncertainties in the horizontal density gradient. And so I'm working in the Ian Grooms group, but the implementation and testing of this parameterization has very much been a group effort and a collaborative effort. So I want to take a moment to acknowledge all the important contributions of my collaborators here. So to introduce you to the problem that we're attempting to solve with this parameterization, is this screen in the way? Let me move everyone. So in a coarse resolution ocean model that does not resolve mesoscale and sub-mesoscale variability, there are uncertainties in the large scale density field that come from the subgrid scale temperature and salinity variability. And to understand why, consider on the right here this schematic diagram of a grid cell in a coarse resolution ocean model that's not eddy resolving. And these smaller embedded grid cells represent a higher resolution ocean model, which would resolve some of those mesoscale and sub-mesoscale features. And here T bar and S bar represent the mean temperature over the coarse resolution model grid cell, whereas the higher resolution grid cell, of course, has temperature and salinity, which differs from the mean but is unknown and unresolved. So the coarse resolution ocean model would calculate mean potential density for the grid cell using the mean temperature and salinity, whereas in reality, the so-called true mean density is a volume average of this rho, the seawater equation of state, that's nonlinear, calculated using these unresolved temperature and salinity deviations from the mean. And so this gives rise to uncertainties in density on the coarse resolution grid. And the correction is approximately equal to the second derivative of density with respect to temperature here over 2 times the unresolved subgrid scale temperature variability. That's this quantity here. And if you're interested in learning more about this, please check out the recent publication by Zofia Stanley just this year. So for the remainder of this talk, what I'm going to be doing is discussing the implementation, excuse me, of a parameterization in MOM6 to account for this unresolved temperature variability. And I should say here that this parameterization neglects the unresolved salinity variability term, which was shown to be small. So Zofia Stanley and colleagues have estimated the unresolved temperature variability that would occur on a 1-degree coarse model grid by diagnosing it from a high-resolution POP model simulation. So essentially, at each grid cell, they've diagnosed the temperature variance by summing the temperature deviations over the coarse model grid cell from the high-resolution model. That's that equation that you see here. And this is the resulting field. Please note that it's on a log scale. And so you can see there's considerable unresolved temperature variability near these frontal regions, near western boundary currents, and in parts of the Southern Ocean. So what effect does this unresolved temperature variability have on the density field, and why does it matter? Here you see a plot of the correction to potential density that was similarly diagnosed by coarsening a simulation from a high-resolution POP model. So as you can see, the density at each grid cell was calculated by essentially averaging it over all the high-resolution model grid cells within that resolve this temperature and salinity variability over the coarse resolution model cell. And as a result, and please note also that this density correction is negative everywhere, and that has to do with the sign of the second derivative of density with respect to temperature. And you can see again that there are fairly potentially significant corrections to the density field in the Gulf Stream region near the Kuroshio Current and in the Southern Ocean. And because of these uncertainties, there are potential uncertainties both in the buoyancy force in the coarse resolution ocean model, and also potentially in the Jent-McWilliams parameterization, which depends on the isopycnal slope. So what are the effects of leaving this density correction out of a coarse resolution ocean model? There's been a little prior work on this problem by Bronkar in 2013. They implemented a stochastic parameterization in a 2-degree ocean model. Essentially, at each coarse resolution model grid cell, they took a number of random walks, sampling temperature and salinity, and calculating a density as the average of those. And though they didn't validate this parameterization, what they showed is that implementing it improves several known biases in coarse resolution ocean models. So for instance, this parameterization reduced the unrealistic northward separation of the Gulf Stream, the heat loss that results from the advection of warm waters too far north in the Gulf Stream, and also the difference in sea surface height between the Atlantic and the Pacific Oceans. This parameterization was rather computationally expensive in comparison to the one I'm going to be discussing momentarily that we've implemented in MOM6. So Zofia Stanley and colleagues have developed two parameterizations for the subgrid scale temperature variance. So there's a deterministic parameterization and a stochastic parameterization you see here. The deterministic parameterization is essentially equal to finite differences of T between model grid cells squared times a constant. The stochastic parameterization perturbs this with a stochastic quantity here, e to the chi, where chi is given by an AR1 process. To show you a validation of this parameterization, this is a figure from their paper. The colors represent counts of data from grid cells. On the y-axis here, you see this quantity unresolved temperature variance that was diagnosed from the high-resolution simulation. And on the x-axis, you see an example of the deterministic parameterization, which was calculated from the coarse and large-scale temperature field. And so it's a very good fit to the diagnosed temperature variance. The purpose of the stochastic parameterization is to capture some of the spread around this line you see in the plot here. So now I'll move on to show you my part of this work, which has been to implement and test this parameterization using a suite of model experiments. We're performing 7 runs to test it. Our configuration is MOM6 with the CEICE5 model. We're using 1 cycle of prescribed atmospheric forcing, JRA55, with a global domain approximately 2/3 degree horizontal resolution with a Z-star configuration. Of the 7 experiments we're performing, we have a control run. We also are turning on and off the parameterization in the pressure gradient force and in the Gent-McWilliams parameterization, and making those parameterizations either deterministic or stochastic, so all possible permutations. These runs are underway right now. This project is very much ongoing and the results are preliminary, but I'm going to be discussing with you today some results from the run with the stochastic parameterization on and the pressure gradient force. So here on the left, you can see a control run. This is a plot of the wintertime mixed layer depth, so JFM in the northern hemisphere, JAS in the southern hemisphere. If not otherwise stated in this talk, I'm showing you 30-year mean data. And this is the bias in mixed layer depth between the control run and a climatology product. So as you can see in the control run, we're representing relatively too shallow mixed layers in the Nordic seas, the Labrador Sea, and in certain regions of the Southern Ocean. In this plot, you see a difference in the wintertime mixed layer depth between the experimental run and the control run. So here I'm focusing on the Nordic Seas and Labrador Sea region. Here I'm showing you some results from the Southern Ocean. And as you can see, our parameterization is greatly increasing the wintertime mixed layer depth in the Labrador Sea, as well as somewhat increasing it in the Southern Ocean. So we're increasing deep convection, increasing mixed layer depths, and as a consequence of this, we also have changes in the overturning circulation. So here on the left, I'm showing a plot of the global overturning stream function from the control run. Again, this is a 30-year mean. And here on the right, I'm showing you the difference between the runs with the stochastic parameterization turned on. So here you can see sort of the maximum in the northern hemisphere between about 40 and 60 north. Our run is somewhat intensifying the overturning stream function. In addition to this, there are also changes in the pathways of western boundary currents with the stochastic parameterization turned on. So here I'm showing you a plot from the control run of potential temperature at 400 meters. And this contour line is the 12-degree isotherm, and that's been used at this depth to represent the north wall of the Gulf Stream. And if we zoom in on this region that you see here to look at the separation region, we see two plots of this isotherm representing the Gulf Stream, one from the control run, one from the experimental run. And as you can see, there's a clear southward shift in the experimental run. And so we have a more realistic representation here of the Gulf Stream separation and path. There are also changes associated with these of the meridional heat transport. So on the left here, I'm showing you some plots from the control run and also from data. So this red line here represents the northward heat transport in the control run of our simulation. The yellow line represents the same thing, but in a hot model simulation. And the other lines represent various reanalysis and observational data products. So as you can see, the control run seems to be somewhat underestimating the northward heat transport relative to these observations. Our experimental run with the stochastic parameterization seems to be correcting some of these biases. So here you can see the difference in northward heat transport between the experimental and control runs. This is a global domain, and this is for the Atlantic. And as you can see, in the tropics and mid-latitudes, the effect of the parameterization is to increase the heat transport and to slightly decrease it at higher latitudes. So this is the region of the simulation that I'm going to be focusing on for the remainder of this talk. Some other changes that we've observed with the stochastic parameterization. This is a plot of sea surface temperature in the Nordic seas in our control simulation. And this is the difference between the sea surface temperature between the experimental and control runs, again, over a 30-year period. And these gray lines represent bathymetric contours. So what you can see is that in the experimental run, the stochastic parameterization is causing cooling in the Greenland Sea, cooling in the Iceland Sea, and also in parts of the Norwegian Sea. And our question is, why might this be taking place? So recall in the prior slide, I showed you that we have a modest reduction in poleward heat transport at high latitude. So the Atlantic inflow to the Nordic seas across the Greenland-Scotland ridge advects relatively warm, salty water into the Nordic seas. We believe that the parameterization is slightly decreasing the heat transport from the Atlantic to the Nordic seas and the Atlantic inflow. However, we're not sure if that accounts for the entirety of this signal, and there are likely other mechanisms that we haven't identified yet that are also contributing to this signal. So here I'm showing some related changes in the Nordic seas. Here, a wintertime mean sea ice thickness. In the control simulation, we know that sea ice is exported from the Arctic to the Nordic seas and the North Atlantic Ocean via the East Greenland current here. And in the difference between the experimental and control run, we can see that there's an increase in the sea ice thickness with the stochastic parameterization in the Western Nordic Sea, so in parts of the Greenland Sea and Icelandic Plateau, or Iceland Sea, depending upon the nomenclature. And we're interested in diagnosing why this might be. So on the left here, I'm showing the wintertime sea ice growth rate from the control simulation. So this is only changes in sea ice thickness due to thermodynamic processes, not including the convergence and divergence of sea ice. And you can see this region of sea ice melt near the East Greenland current. And in the difference between the experimental run and the control run, the effect of the parameterization is to decrease the rate of sea ice melt in this region. So we believe this is consistent both with the cooling that I showed in this region in the previous slide, and with the enhancement of sea ice thickness in that region. We've also diagnosed sea ice exports from Fram Strait and the contribution to this signal due to sea ice convergence and divergence, and we don't think that's playing a major role in what we see here. So to summarize this study and to provide some conclusions, we've implemented and tested parameterizations of the subgrid scale temperature variance in MOM6. Some noted effects of the stochastic parameterization are to increase the deep convection in the Labrador Sea and Southern Ocean. Along with that, we have increases in the Mach transport. We have increases in both the global and Atlantic poleward heat transport at mid-latitude and small decreases at high latitudes. We have an improved representation of the bias in the Gulf Stream separation and path that's known to exist in coarse resolution ocean models. And we also observe cooling and an increase in sea ice in the Nordic seas. So thank you very much for listening. I'd be happy to discuss any questions or comments about this talk.
All right, we have time for one or two, and I see Gokhan had his hand up.
Yeah, I had a comment and maybe two questions. It's interesting that some of the impacts seem to be relatively large, such as the Labrador Sea mixed layer depth changes that seemed quite large, yet the impact on the heat transport is rather minor. I mean, it was only 2% of the total heat transport, yet the AMOC change or the global overturning changes are of the order of 5 to 10%. That's interesting. But I was wondering two things. Why not include salinity as well? And also, since it is a deterministic but stochastic parameterization, should there, if you perturb your initial conditions, would that essentially create, because of the stochasticity of the system, some spread in the response that you are getting? In other words, I'm getting into statistical significance of the response that you are seeing in your experiments, I guess.
So as for the first question, I would encourage you to take a look at the recent paper by Zofia Stanley and colleagues. They basically showed in there that the contribution due to the unresolved salinity variability was negligible compared to temperature. So that's why we left that out. And as far as the second question, perturbing initial conditions to get some kind of confidence intervals on these heat transport changes, is that the point you're making?
Yeah, since the parameterization is stochastic but deterministic, would that create spread, I guess? I don't know the answer. It's just...
I think we can continue to think about that. And
that's fine.
For the sake of time, we'll maybe let Nora ask a question. I think she was up next.
Yeah, thanks for the talk, Jessica. That was great. You showed that including the stochastic parameterization led to this cooling signal in the Nordic seas. It also looked like you got a warming signal in the Erminger current. So you know what, maybe you can bring up the slide again.
Sure.
Like south of Greenland. So is there some kind of redirecting of currents going on? So less warm water gets into the Nordic seas, more warm waters into the Erminger current. Is that what you're seeing?
Where did that thing go? This is the slide you're referring to, right?
Right.
So I don't know for certain what's going on in that region. I mean, we do have some changes in the path of the Gulf Stream whose effects need to be investigated. But I don't have a definitive answer right now.
Okay, thanks.
All right. I think, so Gustavo's got his hand up. Let's just go for one more question, and then we'll go to the next speaker.
Thank you. Thank you, Jessica, for the talk. Quick question. Are you planning to test the parameterization in the hybrid mode as well?
My understanding of our current plan is that we're not planning to do that right now.
Okay, thank you.
Yeah, we certainly could, but it's just more computer time.
Yeah, it will be interesting to see the same type of response in that regime too.
Yeah. For the sake of time, I would love to continue discussing this, but for the sake of time, I think we should move on to Lorzana, who's our next speaker. Thanks, Jessica.
Thank you.
Okay. Thanks a lot indeed. Thanks, Jessica. That was a great talk. I almost forgot it was my turn to speak. So I had a few questions, but we can leave it offline. So yeah, so thanks again to the organizers. It's been a great meeting so far. I've been very excited. So yesterday I had my hat as a CPT lead. So right now I'm going to talk about some work we're doing. It's not part of the CPT, but actually a lot of the parameterizations that I'm presenting will be evaluated as part of the CPT. So the work has been carried back when I was in Oxford and continued when I moved to Courant. And it was basically work with my PhD student, Tom Bolton, who now works for GitHub. And the idea is, can we discover equation? And when I mean discover, it's by using the term from machine learning, which is called equation discovery from data. So the idea is we're going to try to actually learn something from data in terms of equations when it comes to parameterization of subgrid mesoscalities. Okay, so with this audience, I don't need to say much, but I'll still say it nonetheless, right? So at the end of the day, we're trying to parameterize processes that are not captured in our current simulation. So, basically what we're trying to do is to represent those kind of, fine scales, here mesoscalities, in our climate simulation. So the way it's been typically done is we have a good theory and we come up with a mathematical representation of that process that is too small to be resolved in numerical simulation. But we all know that we still have biases, and even though we're working hard by bringing more physics and putting in more constraints and bringing in observations, there's still a bunch of biases around. So the question is not to replace what we've been doing, but is there something more that we can learn from the massive amount of data that we're generating these days? And so, as I said, I'm going to focus on mesoscalities. One, of course, they're important in setting large-scale stratification, circulation, and ocean heat uptake, so kind of important for climate, also because it's my pet topic for quite a few years, so there's a bit of bias here. Okay, so we're going to try to capture basically parameterization from the wealth of data set that we have. So again, we have a lot of simulations, some idealized, some globals. We saw a great talk yesterday from Scott and Gustavo and colleagues on how to do that, right? So we also have observations that we can use. And then the second tool we're going to use, so again, rather than starting from scratch by scratching our head and thinking what a process might look like, we're going to rely on machine learning algorithms. And so what it can do is those kind of a little bit of magic. They kind of algorithms that are extremely efficient and pretty good at capturing complex information from data. So there's a lot of hype around it. There's no doubt. But it's not just hype, right? They've been extremely successful at many applications. And so the question is, would it be useful for us? And so again, the output that we're trying to create by leveraging a lot of data, those machine learning algorithms, is to come up with a parameterization for subgrid scale processes. So Scott also mentioned a few studies yesterday. Same here, machine learning for parameterization have been around. Actually been around for 10 years. So the first study is from Granopolsky in 2010 for the atmosphere. And of course, those things have been populating our journals. There are a lot, both for turbulence, the atmosphere, and the oceans. So my group has been focusing on the ocean for quite a few years now, especially mesoscalities. But there's also a paper on vertical mixing, and I'm guessing Scott and Gustavo are also kind of moving towards the mesoscalities. So it's getting exciting. There are a lot more people now, so more people to compare notes and kind of leverage expertise. But again, as mentioned yesterday, people don't like machine learning, especially deep learning, because it's a little bit of a black box. The algorithm is extremely efficient, but usually kind of give you very high skill at reproducing things you're looking for, but it's very hard to interpret. It's not impossible, by the way. I'll come back to that at the end, but it's harder. And so there's been a lot of reluctance in the community by saying, oh, you're gonna remove all my great physics by this kind of magic thing. So people don't really like it, and I can understand because we were trained as physicists. Nonetheless, again, we still use them and I still love them. But there's something else that kind of caught my eye. And so it's a paper, so kind of a suite of papers that came out by trying to think of, can you learn governing equations from data? So there've been a few. Here's just an example where they take basically, Burger's equations or idealized Navier-Stokes, and they give the algorithm lots of data coming out of a numerical simulation. Again, something that you know the answer to, so you know the equations. So now the machine learning algorithm is a little bit different. It's not a black box anymore. They're trying to kind of match up patterns. It's what we call symbolic or sparse regression. So you give the algorithm a library of functions. You give them derivatives or velocities or shears, all this kind of stuff. You give the algorithm lots and lots and lots of function, and it's gonna try to identify basically the dominant terms that will match up this data, and of course, find coefficients in front of them. And so again, if you compare to the simulation that created a set of data, this is what the algorithm identified, it does a pretty good job, right? So in this case, life is good because you know the answer. So you know what you're looking for. So you know if you converged in the right way. So our idea was a little bit different. We decided to make our life a little bit harder and try to look for equations for which we don't really know the answer. And so what we decided to think about was, okay, can we use those ideas to discover equations, so mathematical expressions for parameterizations or for processes that are not resolved in climate models, or that maybe we never thought about. And so this is the way we kind of took those ideas forward, using data, using machine learning algorithm, but having something that is interpretable, or at least an equation. I'll show you that it's not necessarily interpretable at the end of the day. And that idea can be applied to any part of the Earth system, by the way. It does not apply just to ocean mesoscale. You can apply it to anything you want if you're trying to discover an equation for the process or or an interaction that you're looking for. So we're going to focus on the Eddy permitting regime for many reasons, and I can talk about that later on. So again, can we discover new physics? So it's kind of this middle ground between data-driven and kind of more traditional physics-based parameterization. We're just going at it backwards. We're starting with the data and we're learning an equation. All right, so now I'm going to take you through the process. And so again, the process always starts with data. So in our case, what we do is we start with an idealized simulations. So it's a double gyre, very idealized kind of double gyre, flat bottom, 7.5 kilometer resolution. And we're going to diagnose the subgrid buoyancy, momentum, and eddy energy, if you want, by filtering the data. So you plan a Gaussian filter, and then we're going to coarse grain it. So what that means is we're basically going to average over a certain number of grid boxes. So why we do that? We need to degrade the data. So that's going to be the part that we're looking for. This is the missing forcing that we don't have at coarse resolution, but we could diagnose it from the high-res simulation. So that's the first step, right? So we need to diagnose those missing terms, basically the things we're trying to parameterize. And we're also going to store, a bunch of other things because we're going to feed that into the algorithm. So what we're looking for, again, what we're going to optimize for in that succession is going to be eddy buoyancy, momentum, and energy. Then we're going to give the algorithm lots of functions. And so, of course, it's an algorithm, so you don't write down the equation itself. You give the algorithm, again, pictures. And you're going to give it pictures of, in our case, we're going to give it pictures of velocities, temperature, and also gradients of velocities and temperature, and so on and so forth. So and multiplications of them. So we're giving the algorithm a library of function, about 200 of them. Now, of course, the more library you give, right, the harder it is for the algorithm to converge, but also there's a memory problem there. But again, we can come back to it later. Oh, and for info, we did everything on a laptop, just to give you an idea. It's actually not that consuming computationally, but it's a very idealized problem. Okay, so now the algorithm know what it's looking for, subgrid eddy forcing, and it has a bunch of functions. And what it's going to do, it's going to do a sparse Bayesian learning. So the technique is called relevance vector machine. And what it does is basically going to prune through the library of functions until it finds the terms that best capture the subgrid forcing that we're looking for by using the different pieces from the library of function. So that means this is all the terms from a library of function. They're going to multiply, they're going to be multiplied by a weight. Now, the beauty of that method is that the weights are based, again, on Bayesian learning. That means they have an error bar around it. So you can capture actually the error associated with it. Kind of in the essence of Jessica's talk, we have some uncertainty associated with the parameter around the parameterizations. This method is extremely robust and actually was the most robust method that we found when we looked at discovering equations from data compared to any other algorithms out there. Okay, then what happens is the algorithm basically, gives you an answer. It gives you a set of functions with a coefficient in front of them. And of course, the more function you capture or you keep, the more of the variance of the data you're gonna extract, right? So there's a bit of a decision of how many of those terms you want to keep in and how many you want to throw out. And again, there's a human decisions there. I'm going to show you a few results. Okay, so in this case, so the model was, as I said, double gyre, very idealized kind of bioclinic simulations. So we looked at momentum, buoyancy, and energy. So the first one is the one I'm not going to talk about a lot, just show you a couple of slides, because we understand it pretty well, and we're kind of happy about it. So the algorithm gave us a set of functions that we could rewrite, in this form. So what do we have? We have one term over here that is a symmetric tensor, and then an additional term that is basically just diagonal, so that basically just project onto pressure. So it doesn't basically, at the end of the day, this contribution over here in terms of vorticity, shear, and deformation is very similar to a parameterization we came up with a few years ago, and Scott mentioned it yesterday, deformation-based parameterization, also very similar to the nonlinear gradients models of turbulence from Nadiga and Boucher and many others before. So actually this expression, we could explain a lot of it physically, and we could understand what it did and what it might do to the fluid, again, because we can understand all bits and pieces of this equation. It could reproduce 70% of the variance. So again, really good skill overall, but offline and online performance are not always the same. And so I'll show you that in a second. So offline, it was doing a great job. Online, we had to tweak things. So I'll just again flash just some results. So we implemented it in a very idealized shallow water model. That was the course resolution, which was 30 kilometers, and we're looking at zonal velocity and the standard deviation of zonal velocity. Over here is our truth. So it's a 3.75 kilometer. Again, same thing, zonal velocity and the standard deviation of zonal velocity. We implemented this, equation discovery parameterization, if you want. So basically whatever we discovered from data, and this is what we get. So if you compare it to the truth, does a pretty good job, kind of matches up, or at least it improves, energizes the flow, increases the amount of variance, rectifies the jet. Not a huge impact on the mean, but again, it's a shallow water model, so kind of hard to do very well, but definitely does better than the 30 kilometer with no parameterization at all. It doesn't do as well as what you would call the black box machine learning. So here, it's kind of a fancy neural net, convolutional neural network in which we embedded physics. Actually, we put a physical constraint on it, so it conserves momentum. So the neural net actually does better, but the neural net had to be tuned because the neural net was a little too efficient at generating energy into the flow. So the model was not blowing up, but it was over-energizing the flow, literally kind of creating a massive eddy that was the size of the box, the size of the domain, kind of forgetting that it was reinforcing. All it was doing was basically a very efficient inverse cascade. Should mention that our equation-driven parameterization also had to be tuned, even though it was momentum conserving, because actually it's not exactly energy conserving. And we think that's one of the issues. And hopefully with quite a few people on the CPT, we'll be working on that to actually have an energy constraint. So for the momentum, we could understand it, we could implement it, does a great job, we could evaluate it, and that'll be next. Now I'll show you the downside, but for me, it's actually kind of exciting. So then the algorithm came up with a buoyancy parameterization. And so here's my disclaimer. We don't really understand what we've got, but we're working on it. So, I'm happy to, I'm kind of presenting it more for, people to talk to me offline if they're interested. And I know already some of my colleagues have ideas for what we're getting. Okay, so let me show you kind of step by step what we get. So the algorithm gives you a suite, of functions. We stopped at 4 terms. We just capture 4 terms. Because kind of, basically with 4 terms, you get about 50% of the variance. So you're halfway there if you want in that equation discovery. So again, each of the term, as you can see, is a multiplications of kind of derivatives of velocities. And again, each one has a given weight in front of it, which is, your parameter in your parameterizations. The numbers are over here. So let's just look at its performance. This is depth, latitude. So at the bottom, we're looking at the buoyancy forcing, if you want, so whatever we're trying to parameterize in the buoyancy equation. This is the time mean, and this is the variance. So obviously we have a jet over here, as you can guess, and we have sharp gradients on each flank of the jet. This is the prediction. So, if I were to plot the correlation, it does very well. But of course, you can see that it's lacking some of the variance, again, because we stopped at 4 terms, but we still capture about 50% of the variance. And those are the first 4 terms that we've got. So let's look at a few other properties. If you look at each one of those parameters, you can see they're very close to one another, right? So what we decided is basically take an average of them and rewrite this expression in a slightly nicer way. So now we have the divergence of this flux over here that still depends on horizontal gradients of velocities. And hopefully by now you're probably scratching your head. So we're looking at eddy buoyancy parameterization. There's no buoyancy in there. So that still puzzles me pretty deeply because we did give it gradients of buoyancy. The algorithm didn't like it, apparently. So at least it's not the first kind of expression it wanted us to get out of it. We're still unsure why, but again, something we're working on. So what we decided to do was to, play a few tricks. How interpretable is that expression? Can we make any sense of it, even though it didn't give us anything in terms of buoyancy gradients? So first, we know that we're still trying to parameterize something that is in geostrophic balance. We have a wind-driven gyre, flat bottom. It's pretty simple. So pretty much geostrophy rules everything at that resolution of 7 or 10 kilometers. So doing a little bit of math, you can use thermal wind balance. We write that expression. So now you end up with something that has buoyancy gradients in front of it. And so again, manipulating that operator a little bit. So what do you get? Okay, so we get a coefficient over here. And the divergence of a flux, now we do have a gradient of buoyancy. And it's modulated by basically, gradient of velocity. So it's basically modulated by shear and strain and vorticity, which is still a little bit puzzling. That means it's not always down gradients, can also be up gradients. On the other hand, we had eddy permitting regime. So, what does that tell us? Does that tell us that there is actually a different flux at that regime that is best captured in addition to GM or in addition to whatever, GM is supposed to do at that resolution? So again, this is work in progress. We tried another trick and we use residual mean theory, which again, you can play the tricks with the parameterization that we got. And so here we can rewrite the eddy buoyancy parameterization in terms of what it will do to the momentum. And again, if you rewrite it, what you end up with is basically a diffusive or anti-diffusive vertical momentum flux, kind of equivalent again to a buoyancy term. So all of that are kind of, open questions and kind of show them exactly for that reason, because they help me scratch my head actually. Am I discovering something new or no? Is it completely ridiculous? But it's still pretty exciting because there's a lot of information in data that we don't necessarily know how to use, and we still have biases in model. So can we find a good way to move forward? And so this is what I want to kind of close on, is that we still need parameterizations, right? No matter what, we still want to improve predictions. We still want to understand the climate system, in a better way. So let's try to use some of the data and some of the new algorithm that we have around. I'm still using deep learning, and you'll see Arthur's talk just after me, where we use neural networks and so on and so forth. You can build physics constraints, hard to interpret, but there are ways, and feature maps and Jacobians and so on and so forth. There are many routes. Scott showed you a different route as well with the eddy energy. So again, there are many ways that you can try to build something based on data. Equation discovery, I'm definitely a big fan of it. I kind of like to add this kind of, discovering something new that looks mathematical. So I get excited, so I can play with equations. And it's generalizable, or at least we think it's more generalizable, because again, we can see that everything is scale and flow aware. And that's something we're pretty excited about. Computationally, it's also very cheap to implement because it's just a couple of derivatives that you put in your code. And of course, again, for those of us who get excited about discovering new processes and new physics, it can be a lot of fun, and you can apply it to many other parts of the Earth system. So, maybe philosophical, but I feel, it should not be physics driven versus data driven. I think, trying to combine both might give us the best path forward. I'm also a big believer in diverse approaches from different people. And so, using traditional and emerging tools to accelerate science, I think is important. But maybe I'm an optimist. I don't know. But, I'll just close on that, we have a pretty big project that is kicking off this month with many amazing scientists from many places, many of them at NCAR, GFDL, and so part of the CESM community with domain scientists, machine learning, computer scientists, and model developers to kind of try to bring interpretable machine learning to improving climate models. So I'll leave it at that and hopefully have time for comments and questions. Thanks.
Thanks very much, Laura. It's a very engaging talk. Tony Rosati has his hand up. Do you want to go ahead, Tony?
Hi, Laura. Tony here.
Hey, Tony.
Listen, you've probably thought of this, but how about the data coming from an assimilation, particularly during the Argo period? How would that come out?
That's a great question, and this is part of our new project over here that I just mentioned. So this will be a large chunk of the work, and it'll actually be carried out with Alistair as the lead. So yeah, we think there's a lot of potential there.
All right, well, chat with me sometime about it.
Absolutely.
All right, I got a question in the chat from Hailu Kong again, so I'm going to read it. Thanks, Laura. I'm wondering, how does the choice of coarse graining affect the discovered equations? E.g., can it be that under a different grid size, people may get something different?
That's a great question. My favorite topic, especially for those on the CPT who know that. Yes. So what is the true forcing, and at what resolution should you do it? So great, absolutely great question. All right, so let me start in two ways. We tried a few different, coarse graining or filtering, if you wish. So in terms of scales, so, if I do 30 kilometer or 60 kilometer, I get the same answer. And that's because we're in the Eddy permitting regime. If I go coarser, then I get a different answer. Because again, what you would put in a model at coarse resolution when you resolve nothing compared to one where you resolve something, the parameterization will be different. So I think there are some regimes, at which the algorithm will, pick out what's best to implement at that resolution. So I think we need to think about this. And so that's very important. Now, what is the true forcing? I think it's almost a philosophical question, right? Because we're assuming that the model data we're using is the truth. And so what's the truth that you're learning from? And so that's a big open question. So yeah, thanks. I hope I partly answer.
Yeah, so Olga, do you want to go next?
Yeah, thank you. Great talk, Laura.
Hi, Olga. Thanks.
Would you mind commenting on particular forms, not necessarily forms, but qualities of functions that you use in your library? Because an example of what you give over here, it's pretty much derivatives. What if your process is an integral differential or an integral function? It's much less unique, if you wish. Any thoughts on that?
Oh, yeah, it's also phenomenal questions. Yeah, great questions all around. Having fun. Okay, so here, that's true. What we did was giving basically snapshots of velocities, squared of velocities, and multiplication of them, and nonlinear terms, and so on and so forth. No integrals. I'm a big believer in memory, so which kind of relate to what you mentioned. If you have something that is an integral, so you integrate over memory. So what we're thinking about doing right now is actually thinking about giving previous time steps, and that will give you, if you want, this kind of integrated view of the process.
I was actually thinking spatial integrals rather than temporal, but yeah. So
all right. So that's a good point. So we give first, second, and third derivatives, I believe, up to that point. Again, we stopped just because of memory, to be honest.
Okay, great, thanks.
All right, I think Andrew is going to have the last question here before we move on.
Hi, Laura, great talk. That was really interesting, and I'm glad to see that you've kind of taken it further than what you presented at UVic a year-ish ago. The one question I have is, what does it look like for the equations that comes out with that are just that fail or aren't as good? Like, do they look crazy, or do they kind of just look like random noise and random terms? Like, that's part of that I'm kind of curious about, is like, you've shown some very interpretable ones, but what about some of the more convoluted ones that it's like, this is great, explains 95% of the variance, and it's meaningless?
Yeah, no, that's a great point. So one of them, again, one of our favorite quantities in the CPT, which is the eddy kinetic energy. So you have two possibilities for defining eddy kinetic energy. And so in one of them, if you do it as the u squared plus v squared, kind of, you know, positive definite, then the algorithm did converge to an equation that is only about the transport of eddy energy. So it's literally just moving the energy around, it's kind of advection of it, that's it, nothing else. Which was interesting, but a little surprising, you know, I mean, again, for everybody who works with Mickey, I mean, it kind of, you know, relate to the work that Ian does, where there's a lot of transport of eddy energy, but we're a bit surprised that was the only term. And if you define it as the residual between the mean and the eddy, where it's not necessarily positive definite, the algorithm never converged, never wanted to settle on anything. So there is definitely, again, you know, does it depend on the data that we give it? The model was too simple. Good question. All of that, you know, something that worth pursuing, I think.
Thank you.
All right, thanks, Laure. So we're going to turn it over next to Arthur.
Yes, hi. Thank you. So share my screen. Right, can you see this?
Yes, thanks.
Okay, great. So I'm going to present some joint work with Laure on the stochastic deep learning parameterization of ocean momentum forcing. And as it has been discussed already extensively through this meeting, the goal is to account for non-resolved processes via an extra forcing term on the right-hand side of PDEs. And the standard approach is based on closed-form parameterizations, and this has already led to huge improvements in GCMs. Now, there are still some stubborn biases that remain, and the goal is to see if we can kind of use the available data from that is simulated or observed, and machine learning and statistical tools to further improve. So there have already been a wide range of approaches applied, machine learning approaches applied to this problem, ranging from random forests to neural networks. But when it comes to neural networks and deep learning, most of these approaches have been deterministic, in the sense that they don't account for uncertainty, and they only predict the mean forcing, which is not representative of the whole problem. Now, our goal here is to show that we can use neural networks in a fashion that will allow to account for its uncertainty of the forcing. And this uncertainty is kind of multifaceted. So it comes from the data itself. So this kind of relates to one of the questions that was asked to Laure, to the fact that we actually don't know what the true forcing is, because when we diagnose that forcing, we make some arbitrary choices that depend, such as the way we filter the data. Now, there is also an uncertainty due to the physics itself and to the fact that we're kind of trying to solve an inverse problem, in the sense that we are trying to predict the impact of the small scales on the large scales based only on some large scales quantities. And now it's been advocated as well that accounting for the uncertainty of the forcing becomes especially relevant in what has been called the gray zone, or the eddy permitting regime. And this is because in this case, you can't really apply the laws of large numbers anymore. So in terms of implementing those parameterizations in a numerical simulation, while neural networks until now have been doing quite well offline, quite often they've shown to be unstable in numerical when implemented in numerical simulation. So it's believed that there is potential that the stochasticity might improve this aspect. And the second point is that the stochastic parameterization could lead to more reliable ensemble weather and climate predictions. Now, the data we use in this work is the daily surface velocities U from a high resolution coupled climate model, CM2.6. So CM2.6 has nominal resolution 1/10 of a degree. And we applied to that data a two-step coarse data generation procedure. So the first step consists of applying a Gaussian filter with a bandwidth that is approximately 4 grid points. So we make that choice actually of using a unitless scale for the Gaussian filter in terms of grid points rather than in terms of let's say meters. And so that after applying the coarse graining with 4 points as well, we get a pattern, a grid which follows a pattern similar to that of ESM4 with a resolution that becomes more or less half a degree. And so now that we've done this, we can diagnose what we call the true subgrid momentum forcing, which we denote S. So the goal here will be to use U bar, so the coarse grained version of U bar, to predict the subgrid momentum forcing. And so the way we're going to do this, we're going to use convolutional neural networks. So convolutional neural networks have become one of the standard tools of deep learning, and they consist of a sequence of convolutional layers, where each layer consists of several maps. Each map is obtained by a convolution from applied to the previous layer with a given filter, and you have basically one filter per map. And the general idea behind this is to reduce the number of connections compared to a fully connected neural network, which leads to improved generalization and to enforce invariance with respect to translation of the input. Now, so how do we implement this for our problem? So we have those velocities. So we have two maps of the two maps that corresponds to the two components of the velocity at a given time t. So the input to our neural network is our tensors of shapes 2, nx and ny, where nx and ny is the size of our domain. Our neural network has 8 layers, and the target tensors that we use to train our algorithm are the true subgrid forcing at that same time t. Now, to come back to the fact that we want to account for the uncertainty, instead of doing point prediction, we're going to output the mean and standard deviation of a Gaussian distribution for the subgrid forcing at each location. And based on this, instead of using the standard mean square error, which would look at the difference between the mean prediction and the truth, we use the negative log likelihood of the Gaussian PDF based on the mean and standard deviations that are put by our neural network. So here, what you have in blue is the true value of the forcing for a given component and a given location. In orange, you have the predicted mean, and in green, the predicted standard deviation. And so by trying to minimize this loss, we're going to optimize jointly the mean and the standard deviation. So to show schematics of the implementations, what we have again at a given time t is two maps that correspond to the two components of the velocities. Sorry. If we were just doing point prediction, we would pass this through a convolutional neural network, and we would get two maps of the predicted components of the forcing, and we'd compare this with the true values of the forcing. Instead, here we have 4 maps that are put by our neural networks. The 2 first maps are the mean components, and the 2 last maps are the standard deviations. So now when we do the training, we use the global data. We actually use data from selected subdomains of the oceans, and taken from the control data set with the CO2 levels that correspond to pre-industrial CO2 levels in the atmosphere. And so here in this map, we've highlighted in gray rectangles the 4 domains that we use for training. And then we split the data chronologically into training and validation data. So now when we test, we actually apply the test on the global data. The way we do this is actually we pass the global velocity map to the neural network. And we get an output for that same time of the predicted forcing at the same given time. So we test on the whole oceans. We exclude data near the continents, which we leave for future work. And here what we show is the R-squared coefficient, which is a measure of the skill of our neural network, and which would be 1 in the case where it would be doing perfectly. And so here what we see in this map on the lower left is that we get most of the time an R-squared that is larger than 0.7. What that means is that we account for more than 70% of the variance of the forcing variance using our neural network. Now, to understand a bit why it can be useful to account for the uncertainty, on the bottom right, you have a time series of the mean prediction at a given location of the zonal component of the forcing. Now, if you just look at this time series, I mean, it's great, but it's a bit, it doesn't give you much information. You don't know how well you're doing, how far will the truth be, and so on. So here we can use the standard deviation and to predict a 95% confidence interval. And you can see that contrarily to what one might think, this confidence interval is not linearly dependent with the amplitude of the forcing. So for example, if you go around day number 800, you have a very large standard deviation, despite the predicted mean being not very large. And if we look at the actual realization of the forcing of what we call the true forcing, we can see that most of the time it's within the 95% confidence interval that we derived. Well, that the output neural network actually derived. So this kind of showed that we're able to generalize to the global to the global scale. Now another question is whether or not we can generalize to a new climate. And so we used another simulation data set, which corresponds to a 1% decrease of the CO2 level in the atmosphere until reaching double of CO2 levels. And so we use the 20 last years of this simulation data, where, if I remember well, I think it reaches the doubling of CO2 more or less in the middle of that data set of those 20 years. Yes. And so what you can see on the bottom left map is the change in the variance of the forcing between the two data sets, which is up to 50% in some regions. So for example, in the Gulf Stream, you can see that there is a strong decrease in the variance of the forcing. And despite that, if you look at the R-squared map on the bottom right, again, we can see that our neural network is doing pretty well, despite the fact that we didn't do any fine tuning of the neural network. And so we only trained it on the control data set, and we didn't use any data from this new data set for training. So now this is preliminary work, but we tried to implement this stochastic parameterization in a shallow water model. So the way we do this is that, again, we have two surface velocity maps. So for each component at a given time t, we pass them through a neural network. Then we get two mean components, and to this we add the standard deviation multiplied by maps of white noise. So this is obviously very basic, and I think there's a lot of interesting work that can be done to improve on this by adding spatial temporal correlation instead of using just white noise maps. But what's interesting is that already this has led to a stable implementation without tuning, for example, compared to Zana and Bolton 2020. And so here I just show as well the kinetic, the spatial mean kinetic energy over time from rest. So the blue curve corresponds to the non-parameterized model, and the orange curve corresponds to the one with the parameterizations. And so there's a 50% increase in 50% increase of the mean kinetic energy in the end. That's still lower than what Zana and Bolton got, which was close to 100%, I think. But the forcing that we used is different. So I think, well, this is preliminary work. I think this needs more investigation, but it's interesting to see that it's stable, and this kind of, we hypothesize that this might confirm the fact that the stochasticity helps in that case. Now to summarize, so we tackled the problem of prioritization through the use of data, and we saw that using convolutional neural networks, and we were able to generalize to different dynamical regimes and to a new climate. But maybe more importantly, we were able to do this in a stochastic way. And I think it'd be quite, well, this has been advocated a lot before, but stochasticity might improve the stability in online implementations, and it may also improve reliability in estimates obtained from ensemble simulations. And so I think the message from this is that this is a step to bridge the gap between the black box and physics. And I think we did this for, well, here we predicted, we used the neural networks to predict the mean and standard deviation of the forcing under Gaussian assumption. But I think there's many ways one could combine this kind of idea with other works that have been presented in these talks. So for example, what could force the algorithm to use a closed form equation for the mean, and only use the neural network to predict the standard deviation around that mean. And so I think there's a lot of work that can be done to combine these different aspects. But yes, the message is that we should, since we have so much data, we can probably try to use it to learn more than just the mean of the forcing. And thanks if you have any questions.
Thanks, Arthur. Very, very interesting talk. Anyone, any questions? Okay, I've got, I'm gonna go with Drew first, one from Drew and then Alistair.
Okay, hi, that was a great talk. I have a question kind of related to the methodology. So for your neural networks, you choose some architecture, and I'm just wondering like how the choice is made and how sensitive the results are to those choices, right? Like if you change the number of layers, or you change kind of the width of the layers and those things.
Yes, I mean, so I think we did this kind of in a like hand-fashioned way, in the sense that there are now some libraries that can help you do this by optimizing on those hyperparameters. But there's still this annoying bit where you kind of need to play around with the different combinations. And yes, in terms of what you'd get as a result, I think. I mean, if you have a Gaussian assumption, I think you might improve the results by adding more layers. I wouldn't be surprised if that were possible. But I don't think that you'd get a completely different answer, right? Most of the time, in terms of what is the mean prediction and the standard deviation.
Okay, and I have kind of a related question to the Gaussian assumption. Is that a fair assumption? Like, if you were to diagnose these subgrid fluxes directly from a high resolution model, do they look Gaussian?
So they don't look at all Gaussian actually, but here we don't. The Gaussian is if you just diagnose the forcing from the model, the distribution you'll get will be different from the. So here, what we try to the Gaussian assumption is not on the distribution of the forcing, but rather on the distribution is rather the conditional distribution of the forcing given the velocities, if that makes sense. But despite this, the Gaussian assumption is still a very basic one, and we still struggle a bit with extremes. So there are different ways you can try to deal with this by adding some additional modes to the distribution. Right? So yes, but yeah. I mean, it's still a very basic assumption. Yeah.
Thanks.
Alistair, do you want to go next?
Hi, Arthur. That was fascinating. I was under, it's a general question perhaps, I was under the impression that it was actually very hard to do learning of something which has a stochastic component because it just adds too much noise to the system. And I know that we use random numbers, or rather we do kind of a sort of randomness in the stochastic gradient descent approach. That was kind of one of the big breakthroughs. But I was under the impression it was hard to actually have a stochastic term. So clearly that's not the case because you're using it. So I was wondering how that works.
Do you mean it's based on it's based on the log likelihood. So I think this is quite this is something that is used a lot in the statistical literature. Now it has been used in the past in the deep learning community as well. So I didn't invent this, right? I mean,
okay.
It's been used in the deep learning literature, where you try to where the idea is try to use your neural network to predict some moments of a parametric distribution. And if in terms of training, I actually believe that it can sometimes facilitate the training compared to root mean square error. And so I'm saying this with I don't know how you say this with brackets, or well, with caution. But I think what can happen is that if you just use root mean square error with data such as the forcing that we consider here, you have very large, very different scales of the forcing. And if you just use root mean square error, I think one of the issues is that you might have a large bias when you look at regions which have very little forcing, because I think root mean square error might focus too much on the regions that have a large error, if that makes sense. So I think, so for example, I know that initially, actually, the reason I tried to add this standard deviation term was not to account for uncertainty. That is afterwards that we thought that's actually nice, but it was actually because it made the training easier for me.
Good, thanks.
Thanks.
Okay, let me quickly remind our speakers, if you could fill out the release form and send your slides to Elizabeth Faircloth, fair@ucard.edu. She's sending us the registration emails. And we can put them on the Google Drive and they'll be available later. So please remember to do that. I don't see any other hands raised or questions in the chat. So I think we'll move on now to Alistair's talk.
Thank you.
Thank you.
Okay, so since I'm the last speaker of the day, there is of course a session tomorrow. I'll just take the opportunity to thank the organizers behind the workshop and everyone who's running things behind the scenes, because it's been a great workshop so far. I am going to present some work that represents the component of the CPT belonging to Princeton University and NOAA GFDL. This work was done by Nirja Bhamitapati over the last 6 months. I'm presenting it because Nirja left us just a few weeks ago to go and work in the financial sector. And so I want to have a public thank you to Nirja for all of the work she's done over the last 6 months. As you'll see, it's quite a substantial amount and is laying the foundation for a lot of the research that's going to happen in the subsequent years. And you'll see some of the fruits of that tomorrow. Oops, I'm in the wrong window. So this is a description of an idealized model. And the goal here was to develop a test bed in which we could do some fair implementation and evaluation of all of the extant and future subgrid scale parameterizations that we will want to cover. And the reason for doing it, again, because everyone kind of does these studies when they're developing parameterizations, is to have a fair treatment and an equal treatment of all of these parameterizations. Why idealized? Well, it's somewhat fortuitous. We did propose to do this, but it turned out the pandemic kind of forced a hand on this at the beginning. We had access issues. But it has some advantages. One is that we can actually develop a ground truth. We can afford to actually make a calculation where we resolve, basically everything we need to resolve. And that's not true of a realistic global ocean circulation model. We just can't afford to actually resolve everything that matters. And so this is a world, an idealized world where we can afford to do that. It's also simpler to understand because we are going to simplify the physics. And it presents a kind of very convenient sandbox for developing analyses as well, which we can then apply to the more complicated system. I will emphasize, though, that it is just a stepping stone because we are planning, we want to evaluate this in realistic ocean models used for climate, because after all, the ambition here is to improve climate models. Why two or new? Well, this is actually an extension of an idea that an idealized model that we developed in Carney et al. And Janssen et al. The model is more than just a zonal average channel model. There's been the kind of bread and butter for many of the idealized studies we've done in the past, the zonal uniform channels. But the role of topography has become very apparent in the last decade, or perhaps we knew that before even. And so we wanted to make the system more complicated. Neverworld 1, as we're referring to it, was single hemisphere, and we wanted to actually have a two hemisphere spanning basin. And we wanted to revisit the way we designed the topography. We won't go into details on that, but that's something we're saving for a later date. We did consider more complicated configurations such as the Hoglantic and so on, but really simplicity is extremely valuable when it comes to actually understanding what you're doing. And we have opted to do a very unique thing that we can do here, which is take a purely adiabatic limit. And so there's not going to be the complication of temperature and salt, although of course, those are going to be very important when we return to the realistic configurations. So this is the configuration. This is the configuration we arrived at. There were many variants on the way. We did actually put a lot of effort into looking at what we need in order to get the degree of realism we need to get some interesting solutions. We have a purely zonal wind stress. The topography is fairly straightforward. It's analytically described, so we can change the resolution without having to generate files and so on. It's just, you change the resolution is some input parameters, and then you get this topography at whatever resolution you want. It has some large-scale topographic features. It has coastal shelf and slope. Importantly, it has a submerged ridge blocking the re-entrant channel part, which we now, we all know, I think now, and we saw this yesterday in Hailu's talk, is very important for setting the structure of the ACC. And we have a reasonably realistic stratification. We're only using 15 shallow water layers here. So it's fairly affordable, and it's on a spherical grid, just so we have some variation in resolution. So the model itself is simply the stacked shallow water equations, and this is how we're able to be perfectly adiabatic. There is no temperature and salt. It's just essentially a fixed buoyancy in each layer. It's kind of what's underlying an isopycnal model. And in terms of closures for the higher resolution, we are only using a dynamic hyperviscosity, viscosity, and vertical viscosity. And there is some question about whether that's sufficient, but we believe after some analysis that the data we're generating is perfectly good. Whether it's as best we could do if we wanted to have convergent solution in some sense, whatever that means, we certainly could consider something else, but we're using right now semaglutide hyperviscosity. It is a cheap model in the sense, and I'll show you how high fine resolution we've been able to push this. It does span the equator, unlike QG. So when you compare it to QG, which is probably the cheapest model we could use for studying mesoscale, this has some advantages. One advantage of this system is it is exactly the same dynamical core as GFDL's ocean component in CM4 and OM4, and in the future CSM 2.2 that you heard from Gustavo today. And the setup is actually being duplicated by Los Alamos with MPASO. So there's going to be some alternative viewpoints on these solutions and the study. As I said, it's strictly adiabatic. And one of the advantages of that is that there's no complications from not just TNS, but things like mixed layers and choices of buoyancy and forcing. We could add those to this model, but I think in all likelihood, we'll actually just jump straight to the realistic models when we start wanting to think about interactions with mixed layers and so on. So this is what the solution looks like. This is a 1/32 degree grid, spans 70 to 70, south to north, and 0 to 60. So it's quite a small segment of the sphere, which makes it affordable. That 1/32 is incredibly fine resolution. You've seen these sort of solutions coming for, just say, in the North Atlantic. It's very rare that you'll ever see. You've seen global solutions like this, maybe with the MIT cube sphere and so on, but. If you look at vorticity, as I'm showing you for the whole domain on the right, it's just noise. It just looks like noise. But in fact, if you zoom in, there's a huge amount of structure. There's an awful lot going on in this model. And I'm showing you a zoom in down on the far left here. In fact, I can show you just here, this region here. These filaments would be still sub-grid scale if this was a 1 degree grid. So this stuff that we're interested in is still sub-grid scale here. So there's an awful lot of dynamics going on in this model, and it provides us a huge amount of data to do the study we want in this CPT. So here's a kind of a summary of what we're trying to do. I'm just using the continuity equation as an example, but we have this high resolution data at 1/32. And we can use this in several ways, as I'll mention in the next slide. But there's a snapshot there showing you the eddies. You can see the important features that you expect. We've got an ACC and the bowls of gyres and so on. And here's a section of the Troy. This is at 7 east, going through that ridge. And the idea is we want to actually find a parameterization of the submesoscale here for continuity, but for the whole system as a whole, including momentum equations, that would render a coarse resolution model, which I've labeled here as HC, say at 0.5 degree or 1 degree, whatever model coarse resolution you want, that we're trying to find the parameterizations that render these variables looking as similar to the coarsened version of this model as possible. There's an awful lot in that statement. We have to define similar. We have to define what we mean by coarsening, whether it's coarsening and filtering. That's what a lot of the rest of the CPT has been looking at. And in this evaluation, we also have to put some thought into what we mean by the metrics to actually make the statement to define what we mean by similar. So this is ongoing work. We haven't got haven't finished all of the decisions here. You'll hear about some of the decisions and work going on in the filtering discussion. And then there's this other question about, what is the form of these parameterizations going to be? What are the inputs? And one of the focuses of this CPT is we think that Eddy energy, unresolved and resolved, might be very important. So we can use this data in 2 ways and have been doing so. One is what we refer to as a sort of an offline analysis, the more traditional approach of how you'd use an LES data, which is you process that data, you coarsen it or filter it, and then you try and develop a parameterization. And so here, I'm just showing you a very simple, on the left here, a very simple scatter plot of what a fixed constant coefficient GM closure would do with those high resolution thickness fluxes. And we've got a scatter plot of the model and the coarsened data. And we're finding here kind of a correlation, which is of 500 meters squared per second. And the residual looks very nice and Gaussian. And so this is an offline approach, and there's the huge 1/32 of a degree. If you're coarsening that to 1 degree, you've got a lot of data available to you. And this is actually the data sets which other parts of the CPT will be using. So we've generated a lot of this data, and that's all there for analysis. And the other approach to use the same setup is to actually then run a coarse resolution model on, and actually evaluate the parameterizations online. And so this is basically the same. This is the same code. We've got a fixed coefficient, and we're just going to vary the coefficient. And we're just showing you. I'm just showing you here that 2 endpoints where we've got 5,000 and 100, and you see that the solution changes. And then we can form metrics about which one is best. And so this is very similar to sort of approaches. Both of these are fairly have been done before, and we're just going to go through and systematically do this in the context of this new model. What was I wanting to say here? I'm sorry, it's been a while. Oh yes. So one of the consequences here is we can see straight away that the models are imperfect when we do have the parameterizations. And the thing which is nice about the Eulalia's configuration when you have a ground truth is you can actually start identifying the difference between systematic biases due to the large scale, presumably lack of inadequacy of the parameterizations, and features which are due to clearly due to things like standing eddies. And so you can identify these features in these plots, for example, where you can see the standing eddies as a retroreflection as things come through our kind of model Drake passage. And then there's a large scale bias just because the eddies aren't actually flattening the isosignals in the right way in the global sense. So one of the advantages of the adiabatic approach is that when we start looking at the role of the ready scheme in the shallow water equation, there is no ready term, there's no neutral diffusion term for the active dynamic variables. But if we add some traces, Acker, Bachmann et al., or Bowada and Smith and so on, where you just put in these passive traces in with various structures, and here I'm just showing one, you can then look at you do exactly the same thing as we did for the continuity flux, just the thickness fluxes just a moment ago, and diagnose the traces fluxes. And you can either do that offline or online. And here I'm showing you on the right an optimization, or just as we did for the thickness flux, an optimization of the long layer diffusivity of a passive tracer of 10 passive tracers here. And you see that there's kind of an optimal value, which, and if we zoomed in a bit better, we might find that it's the optimal value is somewhere between 1,000 and 2,000. And so this is there's the reason this is an advantage of the stacked shallow water adiabatic limit is that there is a complete independence of the circulation from this parameter, which makes it a lot easier to actually find to optimize. In our realistic ocean models, the neutral diffusion affects temperature and salt, as does the thickness flux from Gentwick-Williams, as does any momentum fluxes. And so changing diffusive parameter along a signal of traces complicates the solution because there's this nonlinear feedback. And here we have a complete isolation. So it's kind of nice and one advantage of this setup. So to date, we have done an awful lot of what I would say the heavy lifting of designing and Neverwinter 2. Neverworld 2, sorry, Neverwinter 2 is a game. I shouldn't say that, reveal that. NW2 we're very comfortable, we think, with it. And we also have some ideas about how we might add on to it if we want to add some more detail, but that's not in our immediate plans. We've analyzed this to the degree that we're very comfortable with it. And we have been developing a series of analyses and checking the diagnostics, making sure all of our budget's closed. And we're kind of ready now to pass off this model as essentially done and move on to the online evaluation of a whole load of parameterizations, which go all the way back to the 90s with constant GM, a constant coefficient GM and Visbach and so on. And our plan is to try and cover, we really do want to try and cover every parameterization that's been proposed in order to have a fair evaluation of them all. And we can do, we feel we can do this very, very efficiently in the coarse resolution Neverworld 2. and then we will probably select from those the most likely candidates for the evaluation in the realistic model. One advantage of our approach right now is we can actually vary the resolutions we're trying to project uses for, and so this will kind of allow us to span the coarse resolution to intermediate resolution Eddy permitting regimes. I just want to finish by saying Neerja did leave us. A big thank you to Neerja for all the work she did over the last 6 months. There is an open position now, and if you would like to apply for it, please apply by the 15th. Thank you very much.
Thanks, Alistair. Very interesting. I think some of us in the CPT are a little more familiar than others. Takaya has a question, so we'll go to him first, I think.
Hi, thanks for the great talk. In your previous slide, you showed the diagnosed tracer diffusivities, but
no, these are actually, this is an evaluation of online. I haven't, I'm leaving the diagnosed of stuff to Schaefer and the NYU group. They're going to be doing the diagnostics of the offline diagnostics, because they're going to diagnose the full tensor. Okay. Whereas I'm just using here we're just using a constant tracer diffusivity in the conventional neutral diffusion mode. It's just a long isopic isotropic diffusion. Sorry.
Okay, then can you explain? Maybe I missed it, but the point of this diffuse, calculating like passive tracers.
So it's really just a tool to allow us to continue to evaluate the I'll refer to it as the ready term in our parameterizations, because the term is missing in the dynamic. You know, it doesn't affect the dynamical solution. We needed to have some way of actually evaluating that term in our parameterizations in this idealized limit. So we added tracers, passive tracers, in order to do that. There is the side benefit that we can do this kind of diagnosing of the diffusive trace tensor, but the real main purpose here was just to be able to evaluate whether, do an evaluation of whether the implementation is correct, and also do this optimization and evaluate ideas about what the diffusivity forms might do. So there's these various ideas about the relationship between the GM and ready diffusivities, for example, and we can try that here and see what it does to these traces and see if it does a good job of actually modeling these passive traces.
Right. Okay. Sort of related to that. Do you think the diffusivities that you basically use for passive tracers would carry over to like active tracers?
Good question. And you know, it's one of the open questions, I think. For example, we could see what would happen to the PV equation in this system. You know, it's a good question, and I really don't know the answer to that. You asked me if I think. My suspicion is that they aren't related, but I have no justification for saying that, so I shouldn't say it.
Okay, thank you.
So, Alistair, can I ask you a question?
Always.
You did a very nice job about how you're going to use this setup to actually evaluate parameterizations, and that's great. But if I go back to the talks we've just had, Scott's yesterday, about some of these machine learning and things, it would seem this setup is is almost the ideal way to try and learn how to use these high resolutions to develop parameterizations, not just evaluate them. Are you guys talking? I mean, it seems like it's got so many advantages, this whole setup.
It does have many advantages. I mean, it does have the disadvantage that it's not complete because it doesn't have all of the physics and complications of the real world, but it has the advantage that it's affordable, very rich, and this data is available. And our fearless leader happens to be the leader, as she just advertised, of this machine learning project. So I think there's going to be some crossover. And the stuff that Scott and Gustavo and Andrew have been doing definitely seems very applicable. It has not been in our plans to date because we do have a plan of action. We have some tasks that we have to complete. And it would be a distraction at this point if we were to suddenly drop everything and jump onto machine learning across the CPT. But I can very much see how it's going to materialize.
Yeah, you seem to hear a lot about let's use high resolution to learn how to parameterize for the low res. But then we saw in these last talks, it's not so straightforward. But this really does seem like a way, this tool you have of learning how to do that. And the simplest, the better to start with. So I like it.
Thank you.
Great.
Drew.
I have two questions. The first one was related to your setup. I think I kind of missed it, but is there a restoring some vertical stratification?
There is no need for it because the system is adiabatic. So these layers are immiscible. And so all that happens is that they outcrop. Right. And in fact,
beautiful.
You can see some evidence of that in the vorticity plot. I won't bother going into details, but basically these layers are immiscible. They're perfectly conserved. The volume of each layer is perfectly conserved. And so the stratification is maintained. I mean, the worst thing that could happen is if you blew a 500 Newton, well, I forgot the units of wind, I'm sorry. If we quadrillion times the wind that you normally have, the worst thing would happen is that you'd have one layer that's exposed on one side of the jet and everything else compressed in the other. But so you wouldn't have stratification there. But basically, we've chosen enough layers that we have stratification and enough degrees of freedom everywhere under these sort of typical forcing conditions we've got. So there's no need to restore stratification. Now the tracers, on the other hand, there was a restoring term there in the tracers because they're passive. If we didn't have that restoring, effectively they would mix, and this is stuff you're very familiar with, I know. So so it's basically the sort of system that you've set up for the tracers.
Okay. The second question is, I think it's related a little bit to Takaya's work. So in this case, since you already have a layered model, have you thought about maybe trying out some, even just like basic parameterizations of the PV fluxes rather than going with the GM?
So yeah, so I think, no, I haven't got him on that list, but when he was talking, I was writing down on make sure that his scheme is there. Right now, as I think in the questions, it was a diagnostic as much as a proposal for parameterization, but we are truly wanting to evaluate everything systematically. We're going to do this as well as we can, as systematically as we can. If we forget something, it will not be for lack of trying to find everything. So we will try to.
Thanks.
Keith Lindsay.
Great presentation, Alistair. Thank you. Could you briefly describe the formulation of the passive tracer that you're using?
I should probably ask Schaefer or Scott or even Drew to respond to this. Basically, we have a tracer equation with a restoring that is a function of to the initial conditions of that tracer, which is prescribed as a function of space, not of layer. But it's a function of X, Y, and Z. So for example, this tracer I showed, I believe the function was sine of longitude. Oh, goodness me. I have just lost everything.
You're still on, just keep talking.
It's just sine of longitude, I believe. And the initial condition, the initial condition in this thing we're restoring to is the same. When there is a function of Z, it's a function of Z and not layer position. So we calculate the average depth of each layer in order to do the restoring term. And there are, in fact, so far to date, I've used 20 traces by accident because I misread Schaefer's notes on this. The idea is to run with 9 traces with 3 different time scales, where there will be a tracer varying in X, a tracer varying in Y, and a tracer varying in Z, and then each of those with 3 different time scales. So, I mean, it's pretty straightforward. I believe that the restoring term does mean it's not going to be conservative. Actually, that's not true because there's no, yeah, I think it would be, but in global sense. So, I mean, it is straightforward, and it's what these tracer people like to use for diagnosing their these diffusivity tensors. I believe they know what they're doing. Does that answer your question?
Yes, thank you.
was my timer. Drew, did you have another question? I think we can do probably one more.
Yeah, just related to that. So at some point, do you hope to take the diagnosed diffusivities and put them back in to your online model and see how that'll work?
So that's actually exactly what we were doing with the continuity fluxes, is that we actually did the offline analysis first just to get a ballpark idea of what diffusivities we should try for the online evaluation. And that was just, just a simple test of whether the idea works. And in fact, what we found was the offline diagnostic suggested 500 meters per second for the thickness flux. And yet online, we found the best solution, I didn't show this, of 800. And the fact that there was a difference is interesting, and the why of it yet to be discussed. So the idea is to try and do this both ways, but our focus will be on the online evaluation from here on.
Yeah, I guess my question was a little bit more, since like in the diagnosis, you get a full tensor. And if you're trying to put the full tensor in rather than a scalar value.
Yeah.
All right. Well, I would love to keep talking, but we're going to probably keep doing that tomorrow.
Malta has his hand up.
Oh, did someone have a hand up?
Malta.
I'm sorry, I missed it. Malta, go ahead.
Sorry, I just lifted it up and then you were gonna shut it down. This is just a comment. I guess this is mostly for the CPT people. I think we should talk probably at some point and think about how exactly this tensor. Well, the problem is we're looking at a stacked shallow water model here, which is actually it's weird that this tensor is basically diagnoses all the Eulerian properties, and thinking of a stacked shallow water model as filtered in Eulerian space is a little weird. It's not how we usually think of it, and maybe it's not how we should think of it. And so it's actually not quite clear to me right now how exactly the quantities that come out of this tensor will relate to what exactly we need to parameterize in the stacked shallow water model. This is somewhat related actually to some notes that 89 Scott and Nora are some writing up right now. So, but we should talk. We haven't thought about it in the context really about this passive tracer problem, but we should probably talk about that too.
Just pipe in, I agree. And we had a long discussion between Scott and Baylor via email, and Baylor had a very distinct opinion about this, but I don't think it's all been resolved. I agree with you. We need to discuss it.
Yeah, probably a lot of us have a lot of opinions, but we should discuss it.
Agreed. Well, I don't want to keep people, and we're starting up tomorrow at 9:30. We have 2 full sessions, morning and afternoon. So get some rest, be ready, and I'll turn it over to Frank if you have something to say.
Nope, I was just going to say just what you said. We reconvene at 9:30 and have a good evening and see you tomorrow.
All right. Thanks, everyone. Thanks for all the speakers. Remember to send in your talks, your slides.